And we have about 600 participants in this workshop. And, I would like to start with introducing the program. We start in 8:30 to 8:40 to present the speakers and the title of their talk. The keynote talks start at 8:40 to 9. Our first distinguished speaker is Professor Morteza Gharib from Center for Systems and Technologies from California Institute of Technology. Professor Gharib's talk is on Introduction to CAST, Center for Autonomous Systems and Technologies. At 9 o'clock, 9:30, we have another distinguished speaker, Dr. Marco Quadrelli from Jet Propulsion Laboratory. And Dr. Quadrelli will talk about JPL Robotics and related applications. Dr. Quadrelli allowed me to briefly talk about our collaborations during his talk, and I will also present during his talk briefly about our work that is related to robotics and quantum. We have 9:30, a distinguished speaker, Professor Alan Willner from University of Southern California. The talk is on free space quantum communication links using Orbital-Angular-Momentum encoding. At 10 o'clock, Professor Paul Kwiat from University of Illinois, Urbana-Champaign will talk about quantum enhanced and quantum inspired metrology. Then we have about half an hour, 30 minutes Q&A. We may also have a short time to answer some of the questions during the talks after each talk, but because large number of participants, we may not be able to answer all the questions, and the question will be in Q&A section of the Zoom chat, not the chat actually, in the Q&A section. And we will be able to answer some of them, but if we not, then please feel free to email them, and I will be happy to follow up for you and answer your questions and communicate with the speakers later. At 11 o'clock to 11:30, Professor William Oliver from MIT will talk about quantum engineering of superconducting qubits. At 11:30 to 12, Professor Alexander Lvovsky from Oxford University will talk about machine learning as symbionts. In the afternoon, after a 30 minutes break, we will have Dr. Clarice Aiello from University of California, Los Angeles, talking on quantum sensing and communications. At 1 o'clock, we have Professor Enrique Galvez from Colgate University, and the talk is on quantum, photon, quantum mechanics and education. At 2 o'clock, Dr. Alan Migdall from National Institute of Standards and Technology will talk about multiplex single photon sources, metrology using photon statistics. Then we have Dr. Kathy-Ann Brickman Soderberg from Air Force Research Laboratory Information Directorate, talking about quantum information science at AFRL. at 3:30, we will have Doug Fink from Quantum Computing report on a tour through the quantum ecosystem. At 4:30, we have a brief introduction to remote hands-on photon quantum, which is partly from what Professor Enrique Galvez does in his teaching, remote teaching of photon quantum experiment. And then we will have more Q&A after that. I would like to make an announcement for future events. We are also going to organize another event in quantum engineering as a conference workshop, which will be online in February. And this is sponsored by International Association of Science and Technology for Development. And we will accept papers in that conference. And some of selected papers, which is related to quantum and engineering applications, will be published in the Mechatronic Systems and Control Journal. And the editor-in-chief of the journal is one of the authorities in mechatronics area, Professor Clarence de Silva, who has many publications and over 20 books in the area of mechatronics and related areas. Okay, so this is the overall view of the morning presentations. I stop here. I try to answer some of the Q&As, and we will start at 8:40 with the first keynote talk by Professor Morteza Gharib from Caltech, Introduction to CAST. Hi, Professor Gharib. I think we start in 1 minute. I will introduce him.
Can you allow me to share my screen, please?
Sure. You should be able to do that.
Do you see my screen?
Yes.
Is it in a presentation mode or?
It is in the presentation. Okay, Professor Gharib. Let me. It is my great pleasure and honor to introduce Professor Morteza Mori Gharib. Mori Gharib is Hans Lippmann Professor of Aeronautics and Bio-Inspired Engineering, Booth, PRESA, Leadership Chair, Center for Autonomous Systems and Technologies, Director of Graduate Aerospace Laboratories, Director of Center for Autonomous Systems and Technologies. He received his BS degree in Mechanical Engineering from Tehran University in 1975 and his MS 1978 in Aerospace and Mechanical Engineering from Syracuse University and his PhD in 1983 in Aeronautics from Caltech. He joined the faculty of the Applied Mechanics and Engineering Sciences Department of UCSD in 1985. In 1993, he joined Caltech as a professor of aeronautics. Currently, he is the director of Graduate Aerospace Laboratory. Professor Gharib's current research interest is conventional fluid dynamics and aeronautics, include vortex dynamics, active and passive flow control, nano microfluid dynamics, autonomous flight and underwater systems, as well as advanced flow imaging diagnostics. Dr. Gharib's honors and affiliation include member Academy, American Academy of Arts and Sciences, member of National Academy of Engineering, Charter Fellow, National Academy of Inventors, Fellow of American Association for Advance of Science, and Medical and Biomedical Engineering. He received the G.I. Taylor Medal from the Society of Engineering Sciences, the Fluid Dynamics Prize from American Physical Society, and 5 New Technology Recognition Awards from NASA in the field of advanced laser imaging and nanotechnology. In 2008, he received R&D Magazine's R&D 100 Innovation Award for one of the best inventions of the year for his 3D imaging camera system. Additionally, Dr. Gharib has published more than 250 papers in refereed journal and has been issued 116 US patents. Professor Gharib's talk is on Introduction to Center for Autonomous Technologies. The Center for Autonomous Systems and Technologies promotes interdisciplinary research and exchange of ideas in the expanding areas of autonomous systems. It serves as an arena for ideas to translate into reality and be demonstrated to academic and industrial researchers and the general public through educational outreach. It's my great pleasure and honor to invite Professor Morteza Gharib to talk.
Thank you very much, Professor Khoshnood. Give me a great pleasure and honor to welcome all the virtual attendees to this conference that co-sponsored by Center for Autonomous Systems and Technologies. And I hope and I wish that we could have met physically here to host you at Caltech, but maybe that's for another time. So I take this opportunity to introduce the new exciting center that we established it in 2018 at Caltech. Excuse me. And the main idea, as Professor Khoshnood in his introduction introduced, was that a center that we are going to basically use it to bring minds and ideas from different aspects of divisions and departments and fields into looking at systems, and that going to benefit us in the areas of autonomous systems. Our approach was from beginning to look at the whole concept of autonomous systems, not just as developing softwares, as you can see, the Google's and likewise, or making gadgets, if we call it body. So idea was that we should be able to develop these systems in a sense, in a way that from day one, as we design these systems, mind and body together work in order to achieve systems that are smarter and in terms of achieving autonomy or autonomous applications. And that's where basically CAST stands for in order to achieve those goals. So as I mentioned, we like to bring the mind and body together and not only have educational aspects to what we're doing, also advanced research. And to really stimulate this process, we set ambitious goals in terms of moonshots that designed to show practical application and benchmark and produce benchmark platforms. So CAST moonshots in general are going to serve as inspiration as well as source for solving many of issues facing autonomous intelligent systems. And as I mentioned, the whole idea is that not just build gadgets or just develop software, but educate a generation of the students and researchers who can basically bring the AI, machine learning, and mechanical electronics designs into missions of autonomy. So I will go through some of these moonshots, and here it's a poster of all the 5 moonshots that we have designed. And these moonshots, basically, we arrived at them after almost 8 months of interviewing different, the users of autonomous systems to developers of autonomous systems, from surgeons in the surgery room to NASA, the scientists and engineers. And we thought that we set up these moonshots, not just for Caltech or JPL, but also for the whole community. And because it's quite obvious that not one institute or one group can achieve any even portion of these goals and moonshots. And it's required that for us to really cooperate and collaborate with other centers and agencies. So these moonshots are for all. So we've basically picked up these fancy names, the explorers, basically for planetary underwater space exploration, guardians for dynamic event monitoring and first responders, transformers for swarm robotics and that can change shape and functions, and transporters for towards systems that can be autonomously delivered people and goods, and partners, which is very important also, robotic help for in medical field and being partners with people. So the Explorer actually has very ambitious the goals. In this case, basically we are looking at how multi-agent systems and from drones to submarines to robots can basically explore the environment, or actually learn and the design the learning process themselves. So it basically, as it says here, robotic mobility and teaming to navigate unknown and complex terrestrial environments, and also for planetary science, explores survival and also operating remotely on land, in water, and in space. So initial project is led by Professor Aaron Ames here. And the idea is that to have a team of these robots and drones go to through a short mission within Los Angeles, say from Santa Monica to Griffith Park, and the process to observe and report, and not to interfere with the nature of what's happening, but basically gather information and help each other to reach from point of the start to point of destination. By itself is a very challenging. Eventually, they want to have such a mission when we actually explore the nature and try to use these kind of missions to help to save the environment and gather information, be ready for the actions. The next important moonshot is Guardians. Guardians are basically designed to be some sort of dormant observers that they can be strategically planted in locations that we expect disasters to happen. And of course, for California, fire is very important. And so we're basically designing systems that autonomously can sense the changing environment and predict using machine learning and AI, and actually quickly respond by deploying the sensors and deploying the sensors and report back and get the environment ready for the first responders as they arrive. And this is very important. The first project that actually we are working on with Department of Geology at Caltech is the basically monitoring a remote island in Turkey and Caicos, where once in a while hurricanes they arrive and basically destroy one of these small islands. Destroyed by, I mean, they change the whole microbiology of the whole island. And but the nice thing is, after 6 months, the whole life comes back, and the geologists are very interested to see how nature repairs itself. So it's important that you basically image and map the whole island, and frequently. And this process is very time consuming. Every time a graduate student flies there, it's not really a resort, it's just a deserted island. So idea here is that how to basically monitor this thing automatically and send the data back to Caltech in an autonomous way. So what we designed was a system that basically it consists of a drone with multispectral capabilities, imaging, and then this drone is housed in a box that is in part of the island. And whenever a hurricane passes by, the box opens up and the drone flies out and images the whole island and then sends in. This is a short video showing that the concept of this island, the surveyors, it has the solar panels and the wind turbines for charging the drone. Here we see this box, one of its typical operation during the testing here in our center. And what you see in the background that you will see later is a very unique wind tunnel that creates different flow environment that important for kind of reactions that this the drone will have during the takeoff and landing. And it's totally complete autonomous. And our scientists in the center develop a neural system that allows this machine to learn as it encounters new environments and to be able to take off and land very safely in this box. Here is showing as the wind tunnel starts, and this the drone is trying to get out of the box under very turbulent conditions. And it does it all autonomously without endangering anybody or itself. And this process by itself, some of you that work in the linear and nonlinear control system is quite challenging, and how these drones can actually handle. And this drone actually learns as it flies into turbulence and how it goes back and lands under such violent conditions. Again, this design, the drone designed by thinking from day one that how AI and machine learning can help such systems. Um, I'm trying to. So basically, this mission is underway, and this summer actually going to be deployed, and in order to survey this island, and as I mentioned, in multispectral, the wavelengths for looking at microbial to larger scale vegetations. Because of the time, we are going to go look at the transformers. Transformers basically is a swarm robotics, the technologies that developed at Caltech. The Center for Sunju Chang is the leader in this moonshot, and his lab is very much involved in how to design the missions that involve multi-satellites, and in order to form synthetic apertures, basically for we call it basically the telescope information, and also they look at the other applications where as a swarm of this the robotic satellites here can actually approach the objects in the space and collectively decides whether the object is worth imaging or not, and then do their mission without having any command from Earth. The last, not last one, the next one is transporters that, again, we are very interested in autonomous systems for carrying, in this case, mainly patients. It's a flying ambulance is the goal of the moonshots. But in the process, also we're developing many technologies and approaches in terms of from aerodynamics to mechanical aspects to the control, and also the how to have connectivity while these machines are flying around the cities, and the whole aspects of the safe delivery of patients from point to point. This is a concept that we think that it's very important in the time of disasters, where you need to have the delivery or the getting patients out of the situations, the areas that the ambulances cannot arrive or be operational. Also, the technologies developed under this projects can be used for other applications, of course, but the main goal at this point is the delivery of the patients. The last one is partners. Partners are very important aspects of the CAST operation, or goals and objectives. And the whole idea is that to have systems, in this case, you can see the artificial leg, that is not just an the introduction of foreign object to human body, but basically, after a while, this machine learns how to actually be part of the whole body's system in terms of reducing the stress, the whole body, not just being helping one aspect and damaging the others. And again, in the labs of Dr. Aaron Ames, the systems that are designed to be part of the, say, the safe walking for people who have lost their limbs. And but the sensor systems is in communication all the time with the other sensors that attach to the person. And this way, we also learn for a patient or object a specific way of walking or controlling the posture or balance. And for some of you work in this area, this is a really challenging problem, because just sensing where you walk and where you put your foot down, and how to respond in correspondence or collaboration with the other parts of the human body, it's a big challenge, and it's a fascinating area that we are working. So that includes also even the drug delivery system that you can be implanted for cancer treatment, for diabetics, and other applications that autonomous systems are required. And also in this one, cybersecurity is very important because it's a big problem if these systems can be hacked into. As I mentioned, the Professor Aaron Ames's group and his labs are heavily involved in this operation. Also, Dr. Joel Burdick's group. Again, as I mentioned, that we need to really get this process of the machine learning and AI, and also the next generation, to be embedded from the design point to the delivery point. And it's not just something that we just do it afterwards, after we have a mechanical system. And basically, as you can see that from reactive controls, if you walk from grass to asphalt, or just suddenly drone sees a different flow environment around buildings. So each case basically is going to benefit from this interaction with our groups on machine learning and AI, Dr. Isam Young, Anima Anand Kumar, and Katie Bauman, and several other faculty, plus the whole group and the structure that already working in these areas at JPL. And especially when it comes to the transporters and the
No. I'm at a Zoom conference. Or you're a Zoom conference.
Okay, so as I mentioned, these are all very hybrid operation in CAST, and we are really inviting everybody that interested in this area to contact us and work with us in terms of joint projects. We have several labs in the center. There's a lab that basically designed to be very mobile for different projects that come and go into this. And also the flagship the operation is mainly in the drone area with this wind tunnel that very unique. It has about, as you see in the next, it has about 4,000 fans, 2 layers of 2,000 fans, and we can generate basically any environment that, flow environment that you may imagine. And also the tunnel can be flat, so for takeoff and landing, and the whole area that has 48 IR cameras that they can basically show as part of the loop, feedback loop, or basically observe the movements of the objects, either robots or drones or other agents that we can think of. This technology also was very instrumental when we actually designed a similar wind tunnel for simulating the Mars the environment at JPL, and it was very crucial for developing the control software for Ingenuity. And as you know, that a couple of weeks ago was all over the news, and it still is flying around. This the wind tunnel that we cast in collaboration with JPL developed for Mars wind tunnel, Mars testing of the Ingenuity, as I mentioned, was very instrumental for development of the software for control. Now, with this, I know that time is short and we need to be on time. I would like to thank the audience. Again, welcome to this conference. Thanks to Dr. Kushnut and the group that actually put this conference together. We are very excited, and we are looking forward to listen to your talk. Thank you again.
Thank you so much, Professor Gharib. This was really an interesting presentation. And so it really is a great introduction to what is we have in the engineering domain, and then what really we can do to bring this domain to closer to quantum engineering and how we can really transition. And that's the main purpose of this workshop, because we already know that a lot of electrical and computer engineers are very active and very contributing significantly to the area of quantum computing, for example. But we would like really to promote quantum area to more mechanical and aerospace engineering. So that was a perfect introduction, and what is really required in the mechanical and aerospace domain. Now, next talk with Dr. Marco Quadrelli will transition this to more related to how we can connect maybe to quantum engineering, which is more specifically related to mechanical domain rather than what we see in other workshops or other conferences, which is more on focus on quantum computing, quantum computers, or quantum physics. So that's the main difference in this workshop, which we would like to bring mechanical aerospace also together with quantum area. We don't have time to answer the questions in the Q&A, but I would like to just mention one of the Professor Clarence de Silva said that controls is as important as sensing in these applications. And Professor de Silva said, are they mostly AI-based control, or are they conventional techniques applicable here? And I'm not sure if Professor Gharib would like to answer, but I'm sure that, to my knowledge, they are AI-based and plus conventional techniques. So it's a kind of a combined system, I believe. But if Professor Gharib would like to add to that, anything?
No, I think what you said was perfect. You know, again, we're trying to really promote the AI and machine learning as part of not only the design and control, but also as a means of how this machine becomes smart enough to learn as they enter unknown and unexpected environments that the challenge is how to survive. And in the process, we are developing many ideas and other applications that, again, requires real-time computation, real-time communications. And for example, we are looking at how to implement until the real quantum communication becomes more practical, using 5G at this point, for example. But these are all really precursor to ideal, the realm of where quantum communication would become a realization. Thank you.
Thank you so much, Professor Gharib. So yes, so that's the perfect introduction to the mechanical engineering and aerospace engineering domain. And the next talk with Dr. Marco Quadrelli will help to transition this to quantum engineering. And we would like to bring this area together. As I mentioned, not only we know that already computer and electrical engineers contributing significantly to quantum area, but we would like also to bring mechanical and aerospace engineering together with quantum and let them know about the opportunities. So thank you so much, Professor Gharib, again, for your great talk. It's my great pleasure and honor to present our next speaker, Dr. Marco Quadrelli. Dr. Quadrelli is a principal research technologist and the supervisor of the robotics modeling and simulation group in the robotics section at JPL. He is an expert in modeling for dynamics and control of complex space systems. He has a degree in mechanical engineering from Padova, Italy, a master's degree in aeronautics and astronautics from MIT, and a PhD in aerospace engineering from Georgia Tech. He was a visiting scientist at Harvard Center for Astrophysics at the Institute for Purpose Science Technology and a lecturer at Caltech Graduate Aeronautical Laboratories. After joining NASA JPL in 1997, he has contributed to a number of flight projects, including the Cassini, Probe Deep Space One, the Mars Aerobot Test Program, the Mars Exploration Rovers, the Space Interferometry Mission, the Autonomous Rendezvous Experiment, the Mars Science Laboratory, among others. He has been the attitude control lead for the Jupiter Icy Moons Orbital project, and he has integrated modeling task manager, the laser interferometer, space antenna. He has led or participated in several independent research and development projects in the area of computational micromechanics, dynamics, and control of tethered space systems, formation flying inflatable apertures, hypersonic entry, precision landing, flexible multi-body dynamics, guidance, navigation, and control of spacecraft swarms, pteromechanics, and precision pointing for orbital systems. His current research interests are in areas of multi-domain, multi-physics, multi-body, multi-scale physics-based modeling, dynamics, and control. He is an associate fellow of American Institute for Aeronautics and Astronautics, a NASA Institute of Advanced Concept Fellow, and a Caltech Keck Institute for Space Studies Fellow. Dr. Quadrelli's talk is on robotic space exploration and possible areas of application of quantum engineering. In his talk, Dr. Quadrelli will present an overview of robotic systems for planetary exploration being developed at JPL, the trends driving the current developments in planetary robotics, some of the technical challenges involved, and some of his personal thoughts on possible applications of quantum-related technologies in this area. It's my great honor and pleasure to welcome Dr. Quadrelli. Or maybe we need to promote Dr. Quadrelli to the panelists. Okay.
Hi, for both. Can you hear me?
Yes, I can hear.
Yes. I'm trying to share the presentation. Oh, okay.
Are you in the panelists?
Yes, yes.
Oh, I'm sorry. Yes, yes, I saw you.
Okay, thank you. Can you see the screen?
Yes.
Okay. So how are we doing with time?
We are about 10 minutes behind, but please don't worry, because
Okay.
when I give my part, I'll try to catch.
Thank you. All right. Thanks very much for both for the nice introduction. It's my pleasure to be here today and present this talk, which is actually divided in two parts. The first part will be what Forbot has summarized, kind of like an overview of JPL Robotics and the trends, at least from my point of view, the trends in space engineering that are relevant to this discussion, and then some thoughts about possible applications and at the intersection between quantum technologies and spacecraft engineering. Then I'll pass the mic to Forbot to talk about some of his recent experiments that we have collaborated together. So the vision here is that we are trying to, as I said, integrate emerging quantum technologies, at least to our understanding, with macroscopic robotic systems, and to see where we can find a niche to enable novel space exploration opportunities. So let me quickly give you an overview. JPL is part of NASA, is a NASA center, but is also a Caltech laboratory. And as Professor Gharib has mentioned already, and is a federally funded research and development center. There's about 5,500 people working, a lot of PhDs. a big area, but not as big as many other NASA centers. So we're a little bit tight, but we have a lot of labs and office space to do a pretty interesting technology development and scientific endeavors. As a data point, if you didn't know, JPL started right after the Explorer 1 in 1958, and this is a historic data point for JPL, where when the Van Allen belts were discovered, that's what kicked off a lot of the space projects that JPL started working on. Since then, we have the lab has deployed many spacecraft around the solar system and many instruments. In the left column, you can see some of the past ones, from earth science instrumentation to astrophysics to planetary exploration. And then on the right side, there are some of the current ones in development and future ones. Notably, the Europa lander, for example, it's been actively developed, and many other ones that you can see at your leisure in the JPL website. But the point here is to show that the great diversity of technologies and destinations primarily. As a subset of JPL, there's an organization called the Robotics Section, where so primarily JPL does a non-human related space exploration, so robotic space exploration, and we are the focal point. My organization is the focal point of most of those activities, and I kind of it's a dense slide here, but I wanted to give you a flavor of many of the areas that we worked on, from surface landers to extreme terrain, different mobility applications, balloons on Venus, also terrestrial robotics like military autonomous locomotion devices, to manipulation, teaming, and more recently the DARPA Subterranean Challenge, which is still ongoing, and it has the objective to develop a full system to explore and navigate in a GPS-denied environment underground. In all these ecosystems, I lead a small group, or modern simulation group, very small here, but I do my contribution with model-based, physics-based modeling and simulation for many of these applications, together with my team. As an extension of these, I wanted to cast a context here that we are spanning multiple mission regimes and multiple domains of application, from terrestrial to aerial to spacecraft to underwater, under ice, subsurface, etc. And when you're doing things like this, there is an increasing level of autonomy, a request for an increasing level of autonomy. Historically, and I'm pointing here to the diagram in the lower right, historically, we started doing planetary exploration with sending spacecraft to environments that were kind of within the reach of our understanding in terms of modeling the environment. And then we started negotiating more and more the uncertainty in the environment. And an example of that is the famous 7 minutes of terror when you enter the atmosphere of Mars, where there is a great uncertainty in the density of the atmosphere, and then you have to react in real time with the sensors in the spacecraft to ensure precision landing. Finally, and also Professor Gharib's presentation a moment ago indicated that there's a lot of unstructured environment that we are trying to approach with a much more complete management of the uncertainty and on-board reasoning or on-board machine learning and so on. So that's pretty much the trend in the since JPL started developing these technologies. And now we are in an environment where there's a great degree of autonomy in the devices that we deploy, which kind of lead the engineering development. An important trend in the recent years, at least, has been a great drive for miniaturized instrumentation. And this chart may have elements that are a little bit updated, but it kind of gives the idea that there's a lot of effort in fitting small instruments in small spacecraft, particularly CubeSat or small sats, with a form factor of 6U, 12U, things like that. So maybe 30 centimeters to half a meter scale length, more or less, of the order of 10, 20 kilograms maximum, and with larger and larger data rate, computer capacity, and in order to enable a variety of data types and in different scenarios, like I described, multiple domains. So this is kind of to give you a background. I will not spend much time on it, but in parallel, that has been also in the last years a lot of development in small spacecraft, and an example is the last year, in the last 2 years at least, we had Asteria, a CubeSat that achieved half arc second level line of sight pointing error and highly stable focal plane temperature control, which is needed to enable astrophysics missions, high quality astrophysics missions with CubeSats. So as part of that, and another one, for example, is the two Marco CubeSats that completed their mission during the InSight EDL entry, descent, and landing Mars phase 2 years ago, and where technologies like reflector arrays and compact solar array and reflector array were developed for this type of form factor. So there is a lot of development ongoing, and a lot of development emerging as well, and the expected performance in the near future is going to be very promising in terms of enabling more and more capable science collection capability and the next generation of missions. For example, the Deep Space Atomic Clock has achieved nanosecond level accuracy, is within reach, as well as radio frequency laser metrology that can enable, for example, possibly quantum applications. Professor Gharib also mentioned that Caltech and JPL have been working on distributed systems like arrays, and it is a fact that ambitious science missions can be realized if sufficient data is returned, namely there is enough volume of data so that you can do post-analysis on that data and extract the meaningful science, and large baselines or large apertures that are related to the resolution of the detector can be implemented. And this leads naturally to distributed architectures and arrays where you have multiple spacecraft working together. And here I want to make the distinction between, because you hear the words all the time, constellation, you hear the word formation, you hear the word swarm, and it, of course it depends on the context, but at least from a guidance, navigation, control point of view, they're all different. Constellation is, for example, the GPS constellation, where you have multiple spacecraft covering the entire planet to provide localization, each one in their own orbit. Formation is where several spacecraft coordinate tightly to synthesize a virtual instrument like an antenna made of disjointed array of spacecraft. And swarm is a large distributed system cooperating to achieve a goal, but with very large numbers, say 100 spacecraft or so. And so there are challenges for this. And the beauty about the arrays is that it enables a multitude of possibilities in terms of planetary exploration, astrophysics, as I will describe next. Another trend that has been emerging is that the cost and complexity of a monolithic space aperture, this is kind of related to what I just said about the arrays, is driven by the size and the mass of the primary aperture. So right now we are down here with the state of the art of the James Webb Space Telescope, which is not yet in space, but this is a 6.5 meter segmented aperture. And you can see here that there are bigger and bigger and bigger ground telescopes that are segmented with many, many elements working together. That kind of look like an array. Actually, they are arrays. They're not spacecraft arrays, but they are segmented telescopes. And with the intent of providing smaller and smaller areal density, so mass per unit area, more tenuous apertures, and larger, because the resolution is related to that and the complexity. So the bigger the telescope, the more complex the structural frame that needs to hold it together, the most precise it needs to be. There's a limit how much you can put in orbit. So you start then breaking the telescope into an array, but now you have to invoke other methodologies to collect the data, namely, for example, interferometry, synthetic aperture interferometry, and which is now we are approaching the techniques that are also used in quantum engineering. So by now, I hope I made the point that systems of distributed CubeSats or small SATs, they are indeed game changers. They have a great potential in many different areas, because they can offer possibility of distributed or heterogeneous measurements, not just homogeneous measurements, increased density and spatial temporal resolution from different angles, from different points, different orbits, more precise timing, ranging, and precision because of the large aperture, and in leveraging the availability of miniaturized.
Sorry for interruption. 3 minutes.
Okay, so I'll go quickly. So I'll skip the last two charts. So another challenge is the challenge of the small bodies, because they are very challenging from the point of view of the physics, and they open the opportunity to go and do sampling and of organics that are having great impact to science. So I'm going to pick this one. So let me put then in context what we are talking about, at least from my point of view. So far, I've discussed systems in the upper right corner here. So classical systems in the classical regime. There is a lot of work, and I'm not an expert, and I have to defer to the experts and many other experts I will talk today. But there's a lot of work on precise physics measurements. That's the top left side here, where there's a lot of development in this area. Quantum systems in the quantum regime is, for example, quantum machine learning, quantum internet, quantum computing, which is also another aspect. What at least we are looking at in this discussion is what we call quantum robotics, and Farbod will present after me some details about this, where we're trying to bring together classical systems, but with methodologies that are used in the quantum regime. And here I now have only 2 minutes, but there was a workshop that I wanted to mention that it was gave a lot of inspiration for, at least for quantum sensing and technologies. This is already 10 years old, but during this workshop that took place at Caltech, and you can feel free to go and download the report, there was a lot of brainstorming done, and the distinction made of what type of imaging, at least quantum sensing technologies, are more applicable in what areas of space technology. So this was already a first attempt to merge the two domains. And so for the area that we are talking here, there are many open research topics, naturally, for the high performance computing in modeling and simulation, where you're trying to merge the dynamics of the, for example, the multiple drones with the quantum sensing. You need to maintain state coherence to ensure, for example, entanglement, that also Farbod will talk in a moment. Possible acceleration with quantum parallelism in areas like guidance, planning, task scheduling, and hazard avoidance. We have not yet explored this. Quantum detector is an area by itself. There's a lot of work being done in this topic, and we'll hear more later today. And then quantum machine learning, and most importantly, area like the system engineering, like how do you verify, how do you do validation in the quantum regime? We know how to do verification validation for spacecraft in the classical regime, but not in quantum regime. So in conclusion, I want to tell you that, at least from my point of view, there's many of these emerging applications I have discussed. They can be enabled, but by the quantum technology aspects that we will also see more later during the day. And there's also the other aspect of the education that Farbod will touch upon next. So you want to take it over from here, Farbod, or?
Thank you very much, Dr. Quadrelli. I'm not going to take very much, maybe only 1 minute, just to would you like to, I can share maybe.
Yeah, you do, okay, you do that.
Thank you, Dr. Quadrelli, for the great presentation. The only reason I'm presenting here shortly is just a continuation of Dr. Quadrelli's work and also the transition from engineering to quantum. One of the aim of this workshop is to bring mechanical systems together with quantum systems. And because we already have a lot of good progress from electrical and computer engineers in implementing quantum technologies like quantum computers, but how about mechanical systems as mechanical engineers and aerospace engineers? So if you think about mechanical system and classical technologies, then we have the state of the art, or like autonomous systems and robotics. But the goal is now take the current mechanical system, advanced system, and then add the quantum technologies to this. And that's what we're trying to explore really, which is, we call them, for example, in robotics domain, we say, this is our Alice and Bob robots. So I don't want to take, so one of the initial work and the pioneers of this is the work by Professor Kwiat, who published the drone-to-drone quantum key distribution in 2017. Other people have followed his work. We are one of the first group who followed his work, and we are trying to apply. But physicists usually think about it from the quantum point of view, but we are, as engineers, we look at the mechanical, let's say, engineering side of point of view, and then see how we can take advantage of the quantum technologies. And especially, for example, in our mechatronics domain or mechatronics area, we're both trying to implement that in our education as well as actual systems. So we are looking at the interface, how we can combine quantum and classical. So for example, quantum entanglement, photon quantum entanglement for communication in robotics area. And we are using the same technologies that quantum physicists have developed. For example, photon quantum entanglement, and we are using the same facility, and we integrate that to engineering systems. These are some of the implementations that we have done. I would like to thank Professor Mark Beck for the detailed work that he has developed for setting up the quantum entanglement experiment setup. And I would like especially to thank Professor Enrique Galvez, who helped us extremely in developing these quantum experiments that we can use for engineering application, because we are engineers and we are mechanical engineers, we don't have the quantum background. So without Professor Galvez's help, we couldn't develop any of these systems. Now we are teaching also this to our mechatronics student at undergraduate level. We developed some kind of experiments. Student can do experiments and do some basic fundamental quantum experiments, so apply them to robotics and exploring the opportunities really. And I would like to thank you and I would like to stop here. Unfortunately, we don't have time for Q&A, and I would like to introduce our distinguished speaker, Professor Alan Willner. I'm sorry we took a little bit of the time, and it's my great pleasure and honor to introduce Professor Alan Willner. Professor Willner, would you like me to read your biography? I mean, I can read it, but we already.
No, that's okay.
I have already shared your biography with everyone, but I don't want to take your valuable time. But everybody knows you. You are very famous, of course. And I can also say that Professor Alan Willner received the PhD in 1988 in electrical engineering from Columbia University, as well as BA 1982 in physics, and an honorary degree Honoris Causa 2012 from Yeshiva University. Professor Willner was a postdoctoral member of the technical staff AT&T Bell Laboratories and a member of technical staff at Belcor. So he is currently the Stephen and Catherine Sample Chair Professor in Electrical in Mingsing Department of Electrical Engineering at Viterbi School of Engineering at University of Southern California. Professor Willner's talk is on free space communication, quantum communication links using orbital-angular-momentum encoding. I would like to, this is my great honor to welcome Professor Willner for his talk. Thank you very much.
Thank you so much. Let's see, I should start sharing. There we go. Farba, can you see my screen?
Yes, I can see. Thank you.
Great, thank you. So thank you, everyone. And I think that the sun doesn't set on this workshop. I think people are tuned in from around the world, which is wonderful. I'll be discussing free space quantum communications using orbital-angular-momentum encoding. And so I'll go through, because I think, Farbad, there are people from all different levels, right? Undergraduates and graduate students, and so I'm gonna explain everything and give you some results. I'd like to thank Farbad for the invitation, my excellent students and wonderful colleagues, and the generous support that I've received, research support from various organizations. My students, really an outstanding group of people. This is from a few years ago, but whenever we thought about, we had gotten into orbital angular momentum for communications. We got into it about 12 years ago. And then several years ago, we got into it for quantum. And we hadn't really done much quantum before that. So I'm a newbie to quantum. So I come from more the optical communications world, but we use techniques that we had learned in optical communications in the classical world. We applied it to the quantum world. So I'll be describing, this is an outline for my talk, orbital angular momentum that's carried on photons, using it in a quantum communications link. I'll describe some actual results of using OAM in a quantum communications link, and also I'll show using adaptive optics to try to undo some of the turbulence, because a photon can carry, there can be crosstalk into other modes. And when I say modes, I'll describe for you in a second just what these modes are. Okay, so this is one of the most important slides. It's a wonderful paper, and Miles Paget is out of the UK. His group has pioneered many aspects of this over the years. So this is a slide that comes from one of his papers, where on the top, many of you are familiar, of course, with polarization of light. So I'm going to be discussing light and photons. That a photon can be polarized on the top here. It can be linearly polarized, where it can be oscillating up and down as it propagates, or oscillating side to side. that would be linearly polarized, 45 degrees either way. And you can encode a photon as a qubit. So you can encode a 1 or a 0 bit on these two orthogonal polarization states. And those polarization states give you 1 bit of information. It could be a 0 or a 1 because you have two orthogonal states. And that's what's important, is the orthogonality, where the number of distinguishable states you have. On the upper right, this is circularly polarized photons, where the polarization can twist. The polarization can go clockwise or counterclockwise, and you can call that spin angular momentum. But still, with polarization, whether it's linearly or circularly polarized, it's two states. So 0 or 1, and that's really that's all you generally have. I mean, you could do more, but generally that's what's done. Now, in orbital angular momentum, it's a lot different. It is a much larger alphabet. So what is it? It's really about the phase front of the light. So here on the left side, as I point out here, this is a plane wave, and I show the intensity and the phase change. So the intensity is of a fundamental Gaussian beam is just a dot in the center. It's what we all know and love, right? There's a dot in the center, and it gets weaker as you get away from the center. The phase change, this black thing, is that what's the change in the phase front? So normally, I don't know if you can see my hands, if you have a beam, or in the case of a photon, which has you have basically your wave function. You have your wave function. The entire wave function would oscillate up and down together in the beam, all parts of the two-dimensional space, right, in the 2D space. So as it propagates, it's doing this. However, one can have the situation where different parts of your wave function, different parts of your beam, can oscillate up and down differently. It's still a coherent beam or a coherent photon, but the right and the left side, as an example, may go like this, in which case you would have a pi phase change from the left to the right, or a 2 pi phase change as you go around the circle. So what you see on the right here is L equal 1 would be an amount of orbital angular momentum that in this case would be the intensity is a donut. So it's a vortex beam. And around the center, if you cut the beam, the phase front of the wave is changing by 2 pi. But you'd have a fairly large alphabet because you can have a faster twisting of the beam. L equals 2, L equals 3. However, these vortex beams, if L equals 2, it's still a donut, right? It's just the donut gets a little bit bigger. So when you think of, let's say, somebody once asked me, well, what's the, can you go to L equal infinity? Well, yes, you can if you have an infinitely, well, you can't, but one of the limitations is if you had an infinitely large aperture, you could, that's one thing, but you're limited in your aperture. And so because as you go to higher L's, this thing does get bigger, as you can see. And as you go L equals 2, if you go around the center of the beam, there's a 4 pi phase change. L equals 3, there's a 6 pi phase change. And what's important, especially, it's fun for students, look at this formula. I think this is my only formula, or I may have another one. E to the IL phi, where L is the amount of twisting of the wave. And this is very much like a Fourier series. And a Fourier series is a bunch of orthogonal functions, cosine omega t plus cosine 2 omega t plus cosine 3 omega t. And as you know, in a Fourier series, you can add, these are all orthogonal to each other. So I could encode a photon on any one of these states. These would be OAM states, and they're orthogonal to each other. And the number of states can actually be not small, right? It's certainly it can be a heck of a lot more than 2. So, whoops. Now this is some work, and by the way, I will say that early work, especially out of this is Mayer in Nature of 2001, out of Anton Zeilinger's group, talking about encoding of information on a single photon. The idea that a single photon can carry orbital angular momentum goes back, and I will say that 1992, Les Allen was the first author of a wonderful paper that showed that vortex beams, vortex photons can carry orbital angular momentum. So on the top here, oh, and I'll come back to it, but Bob Boyd's group out of Ottawa and Rochester, and this is Mohammed Mir Hosseini, wonderful work, and I'll mention this this other piece of work from Light Science and Applications in a moment. But each of these Gaussian photons, just a Gaussian beam, a photon or a few photons, can go through a converter, which can, each photon can be placed on a different OAM state. So OAM L1 or L3, 2, it doesn't really matter. In each of these time slots, that photon or a few photons can twist if you have a single photon source, as an example. The phase structure is shown here of a photon. And what was really amazing, and this was the 2018 paper that I show here. This is the intensity profile. This is a donut. Your ring structure for OAM, this is for a few photons, and it was measured, and it really is quite astounding. You know, you can do many, you can take a Gaussian photon and create, move it up, so to speak, in a modal space. You can put it on a given mode, these fundamental Gaussian the plane waves, you can, the simple way is to just put it through a phase hologram. You can use a spatial light modulator. Many of you, you know, in terms of in laboratories, these you know, liquid crystal on silicon, all sorts of different technologies. And now there's integrated photonics that can do this. It's really quite wonderful. But if you have a phase plate that has a certain phase function, in this case, you can see this is like an L = 3 value, where it's 6 pi of a phase change, you can convert a photon onto a higher order mode. At the detector, you can, or wherever you want, if you want to separate them out, you can convert them back from by an inverse phase function at the receiver. I just show this for fun because this is some of our first work where this shows a beam. So this is not a single photon. This is a classical beam where this is an interferogram of OAM of +4, +8. These are the L values. -8 because the phase front can twist clockwise or twist counterclockwise. +16. So these are quite they're quite exquisite, actually. And these were done just using spatial light modulators. And again, you can encode a few photons on one of these states if you wish. I'll skip over this. Let's talk about quantum communications, right? So some actual links that were done. So this is this is one of the several early work, and I will say that there are many groups doing it today. Bob Boyd's group, Professor Andrew Forbes's group out of South Africa, really leading groups in this area of quantum OAM for quantum communications. But this is some early work out of Bob Boyd's group, Mohammed Mir Hosseini's paper, where essentially they used 7 different OAM states in which to encode. And of course, there's Alice and Bob. When Bob and I have collaborated, we've published together. I used to say, well, instead of Alice and Bob, it could have been Alan and Bob. Bob was there. I was not Alice. So let me show you some of the work we did, where and we did it at fairly high rates because we were trying to push it. Well, high rates for quantum is a funny word because in classical communications, we went up to terabits per second. So that was in classical sense, it was really quite astounding. But for quantum links, as you'll hear later in today, you're limited by the detectors, which are not that fast, because you're really looking. You have to worry about your signal to noise ratio. your signal is very low, your noise has to be very low, and your data rate becomes very low, partially due to the, to a large part due to the detectors. So what we did was basically 10 megabits per second, which is a reasonable number for regular quantum communications. And since we were doing multiple modes, putting a photon on different modes, it was a reasonable attempt to do. So again, the idea that you would take different photons and put them in different data bins, time slots, symbol slots on in different on different modes. I will go back for a second just to say, my apologies, I forgot to say, the number of modes that you can encode on. Remember, polarization, you have 2. With OAM, Bob Boyd did 7, his group did 7, but you can do even higher. The bits that you can encode per photon is log 2 to the n of n being the number of states that you have. So by having a larger alphabet, you have a larger number of possible encoding states per symbol time, a larger number of bits per photon. So your performance of your quantum link possibly can be higher, right? That's the hope. That's the hope here. So my apologies for not mentioning that before. What my students had done was they had a quantum channel next to a classical channel, and often that's the case. The people call that coexistence, right? Where there's coexistence between quantum and classical beams, and in this case, a Gaussian beam may be used as a probe, especially as you'll see in a few minutes, doing, let's say, adaptive optics to mitigate turbulence effects. So in this case, you have just a few photons on one wavelength and on one polarization, but then you have a big moosey Gaussian beam on a different wavelength, a different polarization, and a different OAM value, right? So you have 3 spaces that you have orthogonality here: polarization, wavelength, and mode, spatial mode. In that regard, you can separate, even if this Gaussian beam is 70, 80 decibels higher in power, you can still separate it out from your very weak, as you'll see, from your very weak quantum channel. What we did was we used, because it is very hard to change a spatial light modulator fast, we used a fast optical switch. As you can see here, a 1x2 switch. And we did it, it's a gigahertz switch, and we only did it at megahertz. But you can switch your beam, your sets of photons to go between two different fixed generators, basically phase holograms. One that would imprint an OEM value of 1, 2, 3, 4. You can do as many as you wish. And this just shows you what was transmitted and what was detected, sort of those clicks that appear. If you detect a photon at a single photon detector, you get this click. And so there are different branches that I just showed, one with L equals -1 or L equals +1. And this is the combined waveform here with these different photons sent. And at the receiver, you basically recover what you sent. So it's I'll show you the quantum symbol error rate in a moment. But as you can see, what you transmit and what you receive generally is going to be the same. I won't go through the details. This just shows you the crosstalk matrix or the cross coupling matrix, because you want to keep coupling to other modes as low as possible. Coupling the power to other modes will give you errors, and it will increase your error rate, and that's going to be a problem. This is just shown sort of what you transmitted here, let's say L sub I, what you received L sub J, and this is a matrix. I won't go through it, but it's not bad. It's actually not too bad. I'll show you in a moment some other results. This shows the quantum symbol error rate, QSER, as a function of what this is delta. Delta is the mode spacing. So I can put I can put 3 photons, let's say, on mode 1, mode 2, mode 3, or I could put the 3 photons on mode 1, 3, 5, or 1, 4, 7. I can space them out more. It turns out that the crosstalk, the cross-modal coupling, is greater the closer you are, right? It's just like frequencies. The closer in frequency you are, the more crosstalk you can have. So that's what happens is here. The quantum symbol error rate can be much higher, which is not good, if your modes are close to each other. But if you separate your modes further apart, so it's 1, 4, 7, as an example, then your quantum symbol error rate can go down. Now, you can do a forward and a backward link, and bidirectional links we had done. It was published in 2019 because essentially the photons are not, they're not really going to be interacting, certainly in free space, and even in fiber, which in fiber you get very little interaction with few photons. There are a technology in which to encode, another one that we used to encode photons would be these multi-plane light converters here. There's you can look up a wonderful paper on the bottom. They, in this case, they could be 7 input ports. These are just Gaussian single mode, but through this, when you couple these together through this phase, it's basically a phase, multiple phase plates that you can change, and you can encode each of these different inputs can become a different mode, right? You can put each of these photons at the different inputs. The input determines what mode you get, and you can go forward and backward. You can have a bidirectional link, which is what one of my students had done. And this just shows, again, the quantum symbol error rate, the single direction link here, and the bidirectional link. And the quantum symbol error rate goes up simply because of some of the cross coupling in the device itself. Now, I'm going to skip over this part here. I'm just going to spend the next very few short minutes to talk about this the issue of adaptive optics. So when you have turbulence, you can have crosstalk, right? Cross-modal coupling. Well, why is that? Well, when you have turbulence in the atmosphere, what's going to happen is that different parts of your beam go through different currents of air or different thermal pockets of air. When you change the temperature of air, you can change its refractive index. If you change the refractive index, you can slow that part of the wave slows down. You're changing the phase structure of your wave function of your photon, and parts of your photon wave function now appear in different modes. So there's modal coupling, and it's not a crisp single mode anymore, but there'll be many modes. Can you put the phase function back to where it was? And the answer is that's one of the things my students did. So first, this was done first in a classical beam. Here, this was a classical beam, a donut beam, which was messed up, and there was cross-coupling, crosstalk through atmosphere. As you can see, it was kind of messed up here. But if you have a wavefront corrector, which could be a spatial light modulator, where if you can measure and do some sort of a feedback loop where you can see how with adaptive optics, that's really what this is, adaptive optics, you can realign the phase front using adaptive optics. And this was done, I'll show you, this was done classically for 5 different modes at the same time. So we had 5 modes, and all of these modes were messed up on the top, but to first order were corrected. And now I'll show you what we did here. This was, as you can see on the bottom, this was some techniques for emulating turbulence and the wavefront correctors that's on the bottom. But this is what we did. We used, we emulated the turbulence with a certain phase distribution and a phase plate and a wavefront corrector. an adaptive optics system. I'll skip over this. This is the same thing. But this is the result. And this is one of my last slides. Here, this kind of shows you the, almost you can say this is the modal purity, right? How much of your wave function exists where it's supposed to be? Because that's really the key here. So again, this is at 10 megabits per second. And here with, this is, only a quantum channel. We, again, just due to components, this was kind of like the modal purity. We sent it in a +1 value. When we added a MUSI probe beam, a classical big beam along with it to monitor, to do anything else, there was some crosstalk and the modal purity went down to 0.7, okay, here. Now, what about when you have turbulence? So turbulence, this will be with no compensation here, these two, and then with compensation here. And what you can see is that clearly the system gets worse when you have turbulence, but when you have compensation, it can come back. So you can recover to a large extent the quality of the modal properties, the modal state. Whoops. And this is the this is actually next to my last slide. And for those of you who recently, if you're undergraduates who recently studied for the SATs, you could say this is my penultimate slide. But this just shows this is the quantum symbol error rate, and the lower the better. This is the bottom here where it's, without any turbulence or anything like that. When you include turbulence, it gets worse. It goes up to here. And when you include this adaptive optics to undo the turbulence, it does come back down fairly far, close to the no turbulence case. So with that, I'll just go to my summary and to say that a single photon, of course, you could put it on two orthogonal polarizations, but with OAM, there's the potential that one could use an even higher alphabet. One can use various OAM values. With turbulence, you can there can be a lot of modal crosstalk, which would reduce the performance of your system. But one can use very well-known techniques for, let's say, like adaptive optics, in which to undo the turbulence, undo to a fair amount the effects of turbulence. With that, thank you very much.
Thank you so much, Professor Willner. That was a really great presentation. There are some questions in Q&A, but if it is okay, we can answer them in the Q&A session at 10:30, if it is okay with everyone. Thank you so much, Professor Willner. And then with that, I would like to introduce our next distinguished presenter, Professor Paul Kwiat. This is my great honor, and to introduce Professor Paul Kwiat, who is the Bardeen Chair in Physics at the University of Illinois in Urbana-Champaign, and is the inaugural Director of Illinois Quantum Information Science and Technology Center, a Fellow of American Physical Society and Optical Society of America. He has given invited talks at numerous national and international conferences and has authored over 160 articles on various topics in quantum optics and quantum information, including several review articles. His research focuses on optical implementation of quantum information protocols, particularly using entangled and hyperentangled photons from parametric Down conversion. He received the Optical Society of America 2009 R.W. Wood Prize as the primary inventor of the world's first sources of polarization entangled photons from Down conversion, which have been used for quantum cryptography, dense coding, quantum teleportation, quantum metrology, and realizing optical quantum gates. He has also done pioneering work on high efficiency single photon detectors, frequency upconversion based detection, and high speed quantum random number generation. Professor Kwiat talk is on quantum enhanced and quantum inspired metrology, engineering more precise measurements. It is now well established that the use of entangled quantum states can, in some cases, lead to the square root of n enhancement in the precision of quantum limited measurements. Here we discuss two examples based on recycled quantum weak measurements and on frequency on degenerate two photon interference, which demonstrate metrological benefits of a different sort, including robustness and systematic noise in one case and noise and loss in the other. This is my honor and great pleasure to welcome Professor Kwiat.
Hi, my video is still muted. You need to unmute me. Unlock the video lock.
Yes, sorry about that.
Hi, everyone. Nice to see you. Thank you so much for the invitation to participate in this workshop. Let me just share my screen. Great. Okay, I'm presuming everyone can see that. Or anyone can see it.
Thank you.
Yes. Great. So I'm going to talk today about, as was just indicated, two topics in quantum metrology, or in one case, it'll be genuine non-classical measurements, genuine non-classical interference. And in the other one, I would call it a quantum-inspired metrological technique. And I have a habit of always changing my titles, so I decided that maybe this one could be increased. Oh, let's see, how do I get that to go? There we go, to also quantum financed, because at the moment, the area of quantum information has been receiving a lot of economic boost from various places. And so along those lines, I wanted to take the opportunity just to introduce you in 30 seconds to IQUIS, the Illinois Quantum Information Science and Technology Center, which was started here at UIUC about 2.5 years ago with a quite large campus investment trying to build on the strengths we already had in quantum information science and engineering, and also enabled to supplement that. We've had roughly 10 new hires in the last couple of years. And that now brings us to about 59 faculty members and affiliates over 9 departments. We've had a lot of large center award grants, large NSF Quantum Leap Center Institute, HCAN, and a large part of the DOE large center, QNext, and another DOE EFRC, Energy Frontier Research Center, QSQM. So there's a lot of things going on, and we're always looking for collaborations with people and such. So feel free to check us out. Just Google IQUIS and you'll find out more information. Okay, so I'm going to be talking about research that was done in my group, not by me, of course, just supervised by me. This is a pre-pandemic photo. It's a couple of years old. So some of the people on the photo are no longer here, and there are new people, but the most important people for this talk are here, in particular Spencer Johnson, Colin Lualdi, and Christina Meyer are relevant for the second half of the talk that I'll be giving, and Courtney Krafchik is relevant for the first one. She's the student who, that was her dissertation work. And of course, we're always looking for new people to join us. Dress code, not really enforced, except on photo day. Okay, so the two things I want to talk about are weak measurements and two-photon metrology for precision optical timing measurements. So let's start with weak measurements. I'm going to contrast this with what you may or may not know about a strong measurement. So this is just meant to be a representation of the so-called Stern-Gerlach experiment, where you have a spin, something that has a magnetic moment, like an atom, for example, that that's not in the S state, and we put it through a gradient of the magnetic field, and that magnetic moment will feel either an upward force or a downward force, depending on whether the spin is pointing up or down, whether it's pointing along the magnetic field or opposite the magnetic field. And due to the weirdness of quantum mechanics, those are actually the only two things that you ever measure. And so in a good experiment, when you send in something that's, say, unpolarized from the left here, it will show up. From the left here, it will show up at either of these two peaks corresponding to spin up or spin down. The point is, this is a so-called strong measurement because you can really tell whether it's up or down. And I'd like to maybe make a different type of experiment. Let's just say that you're trying to measure the tilt of a laser beam, say with a laser pointer. Well, what you could do is you could just point it on some faraway wall and you could just see, okay, well, how much did it shift if I tilted the laser pointer? What angle, how far did it move on the wall? And by knowing the separation on the wall relative to where I was doing the tilt, which I guess would be here, then I can figure out what that angle was. And that's going to be relevant to everything I'm talking about going further. So that's a type of strong measurement. That's to be contrasted with something where we have a weak measurement, where it's the same thing. I'm still interacting, in this case, with a magnetic field, but it's a smaller magnetic field. And so what happens is these two peaks don't really shift very far apart from each other. So in the case of trying to detect the tilt of a laser beam, I've shifted it, but much less than the width of the laser beam. And in general, that's going to be difficult to measure that that small displacement then, when it's much less than the uncertainty in the thing I'm trying to measure. So this idea of weak value amplification was proposed quite a while ago now by Aharonov, Albert, and Weidman, AAV. And what they realized is that if you can prepare your quantum state in a particular initial state, separate from what this distribution is, this might, for example, be the polarization of the thing that I'm looking at. And then I undergo this weak effect that I'm trying to measure. And if you can then do a post-selection onto a state, a different quantum state than this initial one, then what you end up with is a so-called weak value, which is the original sort of the average value that you might have typically wanted to measure in some experiment. But you divide it by the product between this initial state and this final state. And the thing is, if those are nearly orthogonal to each other, so for example, this could be horizontal polarization and this could be vertical polarization as one simple or nearly vertical. Then what we see is this number is very small, and so you can get a big amplification to what that weak value is. And so instead of just getting this small shift, delta, that's very hard to see, we end up multiplying delta by this value AW, by this amplification factor, and that can be much bigger. Now, I will say, because you've done a post-selection, you've only counted a small subset of the data. This peak, although it's shifted by a lot, it still sits under where this original distribution would have been. Okay, so you're never shifting it outside of where this distribution is. In fact, we can think of this as a sort of destructive interference effect that basically destructively interferes almost all of the pulses, everything that would have shown up on the screen over here, and leaves only this little blip off to the side. But it is shifted by a much larger amount. So let's say that the general goal is we want to measure some very small shifts. In this case, for example, the deflection of a beam. And what Aharonov, Albert, and Weidman noted in their paper was that by choosing this particular post-selection, so that we're selecting only a very small subset of the final data, we can get a tremendous amplification. Okay, so let's go back to our original experiment where I have some mirror. Let's say it's a mirror that's piezo actuated, that's going to make a small deflection. And I just want to see, well, what's the smallest deflection that I could measure with that? Okay, so this was an experiment that was done using weak measurements a number of years ago by John Howell's group, Ben Dixon and a couple other people working with John Howell at Rochester. And so their incident beam, they had an incident laser beam, and they sent it into this Sagnac interferometer. So the incident laser beam is in a superposition then of going clockwise around the interferometer and counterclockwise around the interferometer. And if you sort of calculate, if you either know these things or you do a calculation, you can find out that there'll be a complete destructive interference going out this way and complete constructive interference coming back toward the source. So this is like the pre-selection and this post-selection. So the fact that almost no light is going to come out to this port, this is this post-selection that we're talking about. And then they tilt one of the mirrors. And because they're doing this weak measurement, they're able to get a much larger deflection, a much larger effect on this position sensitive detector than if they didn't have this interferometer. Then if they had just removed this mirror and they just let the light bounce through, they'll get an effect that's smaller by about a factor of something like 100. And because that, they were able to detect very small tilts. So this is what their actual setup looked like. They sent the light in, they went through the beam splitter, either clockwise or counterclockwise around. They have some wave plates that enable you to put a small relative shift in the clockwise versus the counterclockwise path. That's how they can leak out a little bit of light to this output port. And then they just look onto a detector and see where did the beam show up, if it shifted, left or right as they tilt this mirror. And by doing this, they were able to then measure deflection angles down to about 500, 600 femtoradians. And that's a very, very small number. Let me just put that in context for you. If you were to take a laser pointer and tilt it to the moon, the center of that laser pointer the center of that spot would have shifted by a hair's breadth at the moon's, at the distance of the moon, as estimated by my colleague Ephraim Steinberg. So very, very, very small angles, very precise measurements. Okay, let us move on though. So brief sort of discussion about weak measurements. So it is absolutely true what I just said, that you get this enhanced signal at the cost of this strong post-selection. It is also true that if your measurement system is so-called quantum noise limited, which means you're limited just by the fluctuations in the number of photons that you might have, for example, if you're using a laser that has an average of 1 million photons, the next time, say per pulse, the next time you measure, it'll be 1 million plus or minus the square root of 1 million. So it's plus or minus 1,000. That's the so-called standard quantum limit, or shot noise limit. And if you have a system which is at that limit, so you don't have other sorts of noise, then it turns out these weak value techniques don't give you any more information than if you did some optimal strong projective measurement. And you might think, well, why bother with them then? And the answer is that if you have some sorts of systematic noise, then in fact you do get a benefit, because the signal can get amplified by these weak value amplification techniques without the noise being amplified. And the simplest example I know to think about that is, let's go back to our laser pointer on the wall. And let's say I'm only shifting it on the wall by 100 nanometers by doing this tilt, but let's say the wall itself is vibrating by a micron, which it almost certainly is, for a typical wall, or even much more than that. You'd be very, very, very hard to see that very small shift of 100 nanometers on top of this 1 micron vibration of the wall. Whereas if you could use weak measurements and amplify that 100 nanometer shift up to 100 microns, then it would be easy to see. So this is the slide that I already showed before about how this weak measurement can allow you to detect small tilts, but there is one problem. So we post-selected, only a little bit of the light comes out here. Most of the light is unused, it's wasted. And so, because if the probability of light leaking out this port is little p, then of the total number of photons we send in, capital N, only p times n are detected. So maybe only 1% of the photons are detected and the rest are completely wasted. So that brings us to the central idea here, is we want to do some recycling. So I'm going to send my photon into the system here, say initially with horizontally polarized light. I'm going to use a device called a Pockle cell that rotates the polarization kind of very quickly. It's going to rotate it from horizontal to vertical. And now any light that comes back will be reflected by this polarizing beam splitter and will just stay in the system. And then it interacts with this again. A little bit is leaked out by this weak measurement, and the rest of it comes back through. It's still vertically polarized, and it just keeps, I keep reusing it. I keep going through the system. And so in this way, basically all the light will end up exiting, except for losses in the system, will end up exiting to this weak value. And so we end up getting a signal to noise improvement that basically scales as the square root of the number of cycles that I can go through this system until we're dominated by losses. Okay, so I'm going to skip this because it's got more details than I want to go through at the moment in the interest of time. And to say that we've now implemented this, and these are proofs that I got yesterday morning from PRL. So this is a paper that's about to appear in PRL anytime, because I sent them back that their proofs were fine. So this is what our actual system looks like. So we have an attenuated laser that's operating where pulses have on order only, you need about 100 pulses until you get 1 photon. So they're very, very weak at the single photon level. And our light is coupled in through this coupling system here. It's initially horizontally polarized, and I leave it horizontally polarized. And then after it goes through, I'm going to turn on this Pockle cell. This is our interferometer that does the weak measurement, and the photons that come out, I direct onto a mirror that intersects half the beam, and half of the photons on the right half go to one single photon detector. The other photons go to the other single photon detector, and I just look at the difference between those two to get an estimate of where the beam is left to right. And then to do the recycling, every time it comes back out of the system, the photon basically makes its path, makes its way through this little delay loop, and then comes back into the system. So I'm able to go through multiple times. In this particular experiment, the beam is focused to a spot size on this mirror that's about 86 microns, which corresponds to an angular spread of almost a milliradian. So it's spreading out a fair amount. And the amount that we're actually tipping this mirror is only about 7.5 microradians. So we're really shifting it by a factor that's about 100 times less than the actual width. So normally that would be extremely difficult to see. Let me also say that in this experiment, we're leaking out about 3% of our light each time, but there are optical losses in this whole system going through all these optics of about 16% every cycle. So that means you're not going to be able to go, too many cycles. And in our experiment, I think we go up to a total of about 27 cycles. And by then, there's really no photons left to leak out because they've been lost by various absorption and scattering in the different elements. Okay, so this is data showing the signal that we get at the output versus how much we're tilting the mirror, the tilt size on the mirror, for doing a single pass weak measurement versus a multi-pass where I get to do this recycling. And in fact, you can see that we get roughly 4.5 times more photons out when I'm able to do this recycling. So that's good. The next plot here is showing that the noise is scaling like 1 over the square root of n for these experiments, where n is the number of photons that I'm counting in my measurement. And that means that we're at this quantum limit, so that we're not limited by noise in something else in the system, which is where we wanted to be to demonstrate this. This is kind of the maybe most important takeaway. This is looking at the signal to noise ratio of the system for comparing a conventional measurement where you just take the laser pointer on the wall and see how much it shifts, or the equivalent thereof in our system, to the single pass weak measurement shown in the blue dots here. And those, as I said before, those give basically the same result. It scales as the square root of the number of photons. And then the same thing using our multi-pass measurement where we get this benefit. And lastly, this is just comparing the multi-pass signal to noise ratio versus the signal pass signal to noise ratio as a function of the number of cycles that we're using. And we see that we get this a factor of improvement by about a factor of 2, which is in agreement with our theoretical prediction. That's somewhat limited, as I said, because we have quite a bit of loss in the system, about 16% per cycle. If we could reduce that to less than a few percent, less than how much we're intentionally dumping to the dark port for the weak measurement post-selection, then in fact that factor of 2 would become something more like a factor of 6 enhancement. Okay, so just in summary, weak value measurements can lead to improved signal to noise ratio, especially if we have systematic noise. They don't have a benefit over an optimized strong measurement if we're in a quantum noise limited system, because of the fact that when we do this strong post-selection, when we only collect a small fraction of the photons at the output, discarding most of the signal, that basically cancels the amplification benefit. But as we've shown here, if we can recycle those discarded photons then effectively every photon can be post-selected, and that enables us to enhance the signal to noise ratio beyond the standard quantum limit. And we've demonstrated that by a factor of 2 at this stage. Okay, I'm going to change gears entirely. So everything I talked about, I've been using the word photons, but also could have been described just with classical electromagnetism. So I will say that that was a quantum-inspired technique, measurement technique. Now I'm going to talk about one that is truly quantum mechanical. So as I'm sure most of you know, we can use interferometers, classical interferometers, as a very precise measurement tool that was used in the Michelson-Morley experiment to prove there was no ether. It's used in LIGO. It's used in a whole bunch of engineering applications, interference, where I'll take my incident electromagnetic wave, split it into, say, 2 paths, and then recombine them. And by looking at the fringes, I can get information about what's going on those paths, what phase shifts there are, how long they are, and so on. Of course, the same thing also happens at the quantum level. Even if I send single photons one at a time, I'll get that same sort of interference effect. That, in fact, in some sense, we relied on that in the previous experiment. But now I want to talk about a different quantum mechanical interference that really is genuinely quantum, has no classical analog. And that's where I take 2 photons, indistinguishable photons, and I send them to opposite sides of a normal beam splitter, a 50-50 beam splitter. And if I do that, there are a total of 4 different processes that can happen. Either both photons can be transmitted, as shown here. Both photons could be reflected, as shown here. Or one photon can be reflected and the other transmitted, and that can bring 2 photons to either output port, as shown here. So if I look at this, obviously these 2 end processes are completely distinguishable because they don't look like either of the other 2. The 2 central processes, if the photons arrive at different times at the central beam splitter, then those will be distinguishable and they won't interfere. I just add the probabilities for each of these processes. This would just be a 4th, this would be a 4th, this would be a 4th, this would be a 4th. But if the photons arrive simultaneously at the beam splitter, these processes are indistinguishable and you get a destructive interference. And so that process just doesn't ever occur. So when I send the 2 photons into the beam splitter, both photons always end up going out to the same output port. So if we do a scan of the relative delay of arriving for the photons to arrive at this beam splitter, we end up with this dip when the 2 photons arrive simultaneously, a dip in the coincidence rate. And that's called the Hong-O-Mandel dip, after Hong-O and Mandel, who first demonstrated this effect quite some time ago, back in 1987. And one final thing is that the width of this dip depends on the photon's bandwidth. So the broader the bandwidth, the narrower this dip. And the thing is, we might want a very narrow dip because we want to make a very precise measurement of some relative delay. I'm going to try and use this. That's what I want to use this for, as sort of a stopwatch to compare the relative speeds of the 2 photons. Not the speeds, but how long it takes them to get to this beam splitter. One other thing about this 2 photon interference, which is quite different from classical interference. In a classical interferometer, if I have loss in one arm of the interferometer and not in the other arm of the interferometer, the visibility of the fringes, the contrast of the fringes will drop quite a bit. I mean, it depends how much the loss is, but the more the loss is, the lower the visibility is, and the harder it is to get this information about phase in the interferometer. It turns out that in this experiment, in this phenomenon, interference phenomena, if there is loss in one arm and not in the other arm, that doesn't affect the relative amplitudes of these 2 processes because they both experience the same loss. And so you still get exactly the same destructive interference. So the dip visibility stays the same. This is robust against loss, relative loss, in a way that classical interference is not. And it is also robust against noise on the detectors because you have to wait until you get 2 clicks. And so that's going to be better than just seeing 1 photon, where if there's any detector noise, you won't be able to know whether or not it's just from the detector or whether it's from your photon coming in. Because this is a 2 photon experiment, it makes it much more robust against noise from the detectors and from other background light. Okay, so if I compare these different methods, in the classical case, we can have quite high resolution, but we're susceptible to loss, dispersion, which I didn't talk about, and optical background. In this quantum case, we have something which in fact is resilient to loss, dispersion, and background. But if you want a very high resolution, you need this very narrow bandwidth, and that can be difficult to use in a system. So the question is, can we somehow combine these and get something where we get all of the advantages of both of them? And the answer is yes. And to do that, we need to have entangled states of light. So I need to have two entangled photons. I've got two photons. One is going in mode in path A, one's going in path B. And the sum of one of them is, say, red and one is blue, or vice versa, but it's in a quantum superposition of those two possibilities. That's a so-called frequency entangled state. And if it turns out that if you use that and you combine those two photons on a beam splitter, like I just described, you get the same dip, except you multiply it by this this beat frequency, this oscillation that happens at the beat frequency, the difference frequency between those two colors that we're talking about. So if this is what the original Hongo-Mandel dip looks like, when the two photons are at the same frequency, as I pull the frequencies apart, what happens is I get this narrow, ever increasingly narrow fringe on top of that. And so the fact that these fringes are getting steeper and steeper means that I can have a more precise measurement of the time delay. Okay, so this has been demonstrated in an experiment just a couple of years ago, where they were able to have a detuning of the photons of about 7 terahertz or 40 nanometers. And in that experiment, they had a roughly 640 attosecond resolution, timing resolution, which corresponds to a shift of about 200 nanometers when they counted about 10,000 photons. The experiment we're trying to do has a shift that's much larger, a detuning that's much larger, so more than a factor of 100 larger. And we can do that because we have ways of making these highly non-degenerate, so in other words, different frequency entangled sources. And with that, we predict that we should have a resolution better than 10 attoseconds in roughly 10,000, for accumulating roughly 10,000 trials. So this is what the system would look like. We have a source that generates the photons. We split them. We have to convert polarization entanglement to frequency entanglement. We send them through different paths. We need to choose our optics carefully because they do have to work for both 810 nanometers and 1550 nanometers, which are the two wavelengths that we're dealing with in our experiment. We can control those paths very precisely, and then we can detect them using special single photon detectors, so-called superconducting nanowire detectors. So we previously demonstrated this sort of non-degenerate entanglement source where one photon is at 810 nanometers and the other is at 1550 nanometers. In this case, they're also polarization entangled, and that's what you need as a starting point for this experiment. And the source is pretty bright, and so we should be able to get that 10,000 photons in less than 10 milliseconds to get this of order 10 attosecond resolution. Okay, so in summary, using this sort of frequency entangled interferometer should enable us to have attosecond scale quantum metrology. It is resistant against dispersion, and I haven't talked about why that is, but it turns out that this 2-photon interference experiment is resistant against dispersion. And also because the photons individually, the states individually can be very narrow bandwidth. So the 810 nanometers can be narrow and the 1550 can be narrow. I just need to have a broad distance between them, but they're individually can be quite narrow. As I indicated, this is also robust against loss. So if we wanted to characterize very lossy materials, that could be quite helpful. And it's also resilient to noise because of the fact that we have to have pairs of photons. And so you can essentially project against that. So using our source, we should be able to get about a factor of 100 improvement in the resolution compared to previous work. And because of those enhancements, we think that this will be a useful resource going forward, with a number of different practical applications. And with that, I am finished. in 28 minutes.
So much, Professor Kwiat. Very interesting and great presentation. Now we have time for questions. And I think we have some questions in the Q&A, but also we can, if any of the attendees would like to talk directly, please raise your hand or type in the Q&A.
Yes, so I see one question which is what's the difference between classical and quantum? So
Yes.
that could be a very long answer. But basically, classical means that in this case, it's describable by electromagnetism. It's describable by Maxwell's equations. And the consequence of that is that if you have a beam coming to a beam splitter, according to Maxwell's equations, you can detect it on both sides of the beam splitter. According to quantum mechanics, if you send a single photon onto both sides of the beam, single photon onto a beam splitter, for that one photon, it will only show up at either of the two output ports, although you can't predict which of the two. It is in a superposition of going to both, but when you make a measurement, it only shows up at one of the two.
Thank you very much. If any of the attendees would like to directly talk, please raise your hand and I can, if you type in the chat, we may not be able to type and you may not see the chat, the answer in the chat.
So I can see the chat and I can also see and the Q&A. So another question in the Q&A is how to develop the certainty of only shooting 2 photons at a time in an experiment. Yeah, so that's a really good question. So the way that we do that, and this is pretty standard now over the last, well, let's just say since I was a graduate student back in the 90s, you take a high energy photon, let's say one that's at 530 nanometers, and you put it through a nonlinear crystal, and sometimes that high energy photon will split into 2 daughter photons, say one at 810 and one at 1550, and then you send those into the experiment, and your pulses are weak enough, your pump pulses are weak enough that any given pulse maybe only has a 1% chance of making 1 pair. So the chance of making 2 pairs would be only 10 to the minus 4. So that's how you prevent having these multiple pair events. But if you try to drive it really hard, those multiple pair events absolutely happen and they are a problem. So it's good to be worried about.
I think we want to talk. We have a question in yes, raising hand. Douglas Steen, would you like to ask your question?
No, he already answered it. Thank you so much. I appreciate it, Dr. Krishnan.
I do see another question in the oh, someone's hand is up actually.
That was Douglas I asked, and let's see if there is anyone else. Another question in the chat is maybe for all the panelists. Could you please give an introduction to basic quantum engineering? So what is really maybe the definition of quantum engineering? So
Okay.
to all the panelists.
Yeah, I'll let someone else take that one since I've been talking a lot.
Okay. Professor Willner, would you like to? Or
actually, it's actually, but Paul, you really are you're the right person. I would.
Okay, so I guess I would say quantum engineering. I mean, in some sense, it could mean 2 things. One, it means being able to create quantum states of a particular type. In the same way that you would do classical engineering to make classical states of a particular type. For example, the things that Professor Willner was talking about, that these different orbital-angular-momentum states, you certainly can create them classically. They're electromagnetic modes, and you could think about how to tailor them using classical optics. The difference is that now we want to also include this phenomenon of entanglement and superpositions of quantum states. And the superpositions kind of map onto classical, but the entanglement is the thing that really is quite different from classical. So I would say that in that sense, quantum engineering means engineering states, either states of light or states of matter that don't have classical analogs. And then the second part of quantum engineering, I would say, would be applying engineering basically, to be able to combine these things in useful experiments and useful applications. So not just things directly in a laboratory, but being able to, for example, put a down conversion source, so that this is this entangled photon source, to put it onto a robot, onto a drone, and be able to fly that around. That's much different than what we're typically, us as physicists are used to doing in our laboratories. We don't have to worry about, you know, things vibrating or falling out of the sky for that matter. And so you have to do a lot more engineering, but you have to do it in a way that maybe classical engineering wouldn't work as well, because for classical engineering, for example, you might just say, well, if I have too much noise, I'll just crank up the signal. But in the quantum case, I have to stick at the single photon level. So I can't just crank up the signal.
Thank you very much, Professor Kwiat. And also, could you please let everyone know a little bit more about your drone-to-drone quantum key distribution?
Oh, right. So we have an experiment that we've been working on for quite a while. It's not so easy. And the eventual idea is to be able to distribute entanglement between drones and to have a reconfigurable network where we could have multiple platforms, and they would also hook up to stationary platforms with telescopes, and you could then hook up a wireless quantum network to a wired quantum network. That's a thing that will absolutely be done sometime in the next several years. I don't know exactly when, but certainly. The main challenge of that, as we found, where we've been devoting pretty much all of our time, is it's not very easy to get optical locking between two drones that are in flight. And just to give you a sense of this, it's kind of like you have two gunfighters. I hate to use a gun example, but and I don't own guns, but anyway, it works. It helps to get the idea across. You have two gunfighters that are each trying to hit each other, but it's not enough that they shoot the other guy. Their bullet has to go into the gun of the other shooter, and vice versa. Yeah, and that's very difficult. It's not like you trying to shine a laser pointer on a distant person as he's moving around. You could do that easily. It's that he's also trying to shine a laser pointer at you, and those two lasers have to completely overlap each other on the whole path. And that just turns out to be quite difficult when the whole thing is vibrating. And so that's the thing that's been the big challenge. I'll say one more thing, which is that people have absolutely been able to solve that challenge with fixed telescopes on rooftops and on satellites and on big things. It's not easy to do on a light drone, because the drone can only carry 10 pounds or something like that. And so you can't have lots of heavy optics, which would, for one thing, make the thing more stable, because the moment of inertia would go up, and so it wouldn't be rotating so quickly. So that's one of the challenges of getting that to work. But it's a thing that absolutely will. Actually, I think we have a test happening either tonight or tomorrow, where we've already had ground to air and air to ground, but we're like this close to getting air to air locking.
Thank you very much. And I have another question. Is this, can I say that your drone-to-drone quantum key distribution, your patent, and also your paper is the first in this area?
So good question. So
I haven't found, because I follow your work, and we are one of the first groups that we are following your work, but we haven't seen anything before that. Just
no, right. So as far as I know, the patent was the first thing. I mean, I was on a patent when I was at Los Alamos National Lab about trying to do ground to satellite connections, but that's a little bit different than doing drone to drone. So anyway, in that sense, it was different. But I will say that just in the last year, there's been a paper published by a group in China where they were able to do entanglement distribution from a drone to two ground stations, not drone to drone. And I'm sure they're working on drone to drone now. Drone to drone is harder than drone to two ground stations, just because of the fact that both things are vibrating. So as far as I know, no one else has done that yet, but I guess it'll happen. I guess it'll happen soon. Also, Thomas Yenevine in Canada has done some very interesting things where they've gone from a plane to a telescope on the ground, and also from a telescope to a moving truck. And so that's also sort of legacy experiments of people who have successfully done this.
Thank you very much, Professor Kwiat. There is some questions in the Q&A, which I think there was one question before we finish the questions here. Some prepare ourselves. How can we prepare ourselves part of quantum research teams?
Okay, that's a good question. So I mean, obviously you need to know a little bit of quantum mechanics. So you should definitely take a basic quantum mechanics class. A lot of the engineering that we end up doing is absolutely not quantum mechanics. So all of the stuff about doing optical locking is done at the classical level with classical beacons. And then we let the quantum signal ride along at a different wavelength that we can pull off and measure independently. So also being a good engineer, whether that's a good aerospace engineer for drones and controls, or that's a good electrical engineer for making small FPGAs to control everything, those can certainly be different. So I guess that's how I would say that. Also, learning to think maybe a little bit broader than your own discipline. So quantum information at the moment is now really moving outside of science laboratories to the point where it's supposed to be taken up by engineers who will then get things that will work better than us scientists would be able to do. And so being able to have a broader perspective of understanding both the quantum physics and the electrical engineering and finance, because I was just at a talk yesterday about people trying to use quantum computers for finance, and they don't know anything at all about quantum computers and certainly about the hardware. So people who have a broader perspective are going to be very important going forward.
That's I think very important, because that's the main purpose of this workshop, really, because we know that electrical computer engineers are very involved and active in this area, but not other areas like mechanical, so much mechanical engineering and aerospace engineering. Thank you. And so I have another question. We have Mo Win. How to keep them after, but I'm not sure.
Okay, yeah, so I guess I see a couple of these. So we'll say more about how to keep them after you create or engineer them. So at the moment, when we make our photon pairs, our entangled photon pairs, they fly at the speed of light, or maybe if they're an optical fiber at 2/3 the speed of light. And then when they finally get to their detectors, they're measured, and that's the end of them. Certainly people are working on quantum memories. So you would have, for the moment, let's just say a box where you could send your photon in a quantum state, it would get stored and you could release it at some later time. And that box can be different things. It could just be a long loop, basically, although it's hard to stay in fiber for too long before you have losses. Another thing, it could be where you convert the state of the photon into the state of some atom in some ensemble of atoms, or in some crystal, ions inside of a crystal. So there are lots of different quantum memory methodologies that people are looking at. And in fact, you need those in order to make a long link through an optical channel. If there's loss in the channel, if it's quantum information, you can't put an amplifier. It's not possible to clone a quantum state, so you can't have an amplifier. So loss turns out to be quite bad. And the only way to get around that is with a so-called quantum repeater. And that requires you to have quantum memories. And so the next person asked about commenting about quantum internet or quantum networking hardware. Yeah, so there are a number of efforts around around the world at the moment, but also nationally, trying to work toward a quantum internet now. Basically, I would say no one really has one where you can distribute entanglement, from arbitrary nodes to arbitrary nodes over 1,000 kilometers. No one can really do that at the moment with any kind of a useful rate. And so there's a lot of effort going on for that, both for quantum communication applications, but also for trying to connect up quantum computers, for example, where you would have distributed quantum processing, or to have distributed sensors, quantum sensors. And in fact, that's one of the reasons we're interested in these things with drones and reconfigurable cases, which is that probably you want your sensors on things you can move around so they can sense different things, not just sitting at the end of some fiber network. You want to be able to move those around. What do I mean by finance? Finance, right. So if you Google quantum finance, you can find a whole host of papers on that. The idea is to use quantum computers, which are very good at algorithms, optimization algorithms, in order to answer questions very quickly. For example, how should you diversify your portfolio in the best way to optimize your gains? So you have some risk for each different thing that you might own and some possible reward. And the question is, how should you invest But the thing is, there's often interplays between these things. So if the price of oil goes up, that can affect how much bacon costs, because you have to shift. It affects how much it costs to ship the bacon from one part of the country to another part of the country. So there's all of these interplaying issues, and that can be very difficult to solve, basically intractable on classical computers, whereas quantum computers, if we had a large-scale quantum computer, which we don't yet, but we will, in a decade or something like that, quantum computers could be good with something like that. And yes, quantum computers do need servers to distribute information. And one of the issues at the moment is we don't yet have good interfaces between quantum computers, which are mostly based on physical hardware like superconductors or trapped ions or something like that. It's hard to get the information from them into photons that you could send down a telecom fiber. So making quantum transducers is another of the kind of holy grails for the field at the moment.
Okay, I think there's, thank you so much, Professor Kwiat. I think there is one more question that is for Professor Willner. In the Q&A, could you please talk about advances in laser technology that are needed to accurately and consistently detect various variations in light beams in order to exact 1 second and 0 second? Which companies are forefront of producing laser today? I can also promote you to the panelists if you.
Oh, that's okay. Can you hear me?
Yes, Professor Willner.
Okay. Thank you very much for the question. It's a wonderful question. I think in terms of advances in laser technology, one of the issues, of course, is a single photon. To be able to create a single photon, and that would be the case for whether it be these orbital angular momentum states or polarization states. Sort of, I think the whole field and of quantum communications can make use of single photon sources. And I don't know, as far as I know, that's really the thing that it would be great to be able to buy. Paul, I don't know if you know of any place that sells them. I'm not aware. Yeah, there's a lot of good research going on, but so I think that would be one thing. I think another issue would be the tunability. Can one be able to tune if the laser is putting out a qubit of some sort or a qubit? Can it be modified? And at rates that are a lot higher? So whether it be the polarization of this or the orbital angular momentum state, whatever it may be, whatever you're encoding your information on this single photon, if that can be tuned at the source for the encoding at a good line rate, at a good data rate, I think that would be that would also be extremely important. Something we actually didn't have, right? We did the brute force method where we just sort of split, sort of had a classical switch which comes with its own losses and its own problems, and then just put it through 10 different or n different encoders, right? But that's just a brute force method. It would be nice and much more elegant and efficient to do it right at the laser source. Anyway, that's I think my answer. Again, Paul, I defer back to Paul if there's anything else he'd like to add to this.
Yes, sorry, I was typing an answer in the chat to one of the questions. I agree with everything that you just said. Single photon sources are definitely lacking at the moment, although people are starting to get quite a bit better using, for example, quantum dots or like so-called NV, nitrogen vacancy centers, or other defects in solid state materials, where basically, ideally, you'd like to have a single atom or a single emitter, and then you excite it, and then when it decays, it emits a photon. That's fairly well established. That's easy to do. The thing that's hard is that usually that photon wants to go in all directions, and that's not really, when you order something from Amazon and they say they shipped it it's important that they ship it to you in particular. And so what's hard is to catch the photon that's coming from, say, a single atom that's decaying, and make sure that you can catch it, and that it preferentially goes only to the person who's supposed to receive it. And that's a huge challenge at the moment.
I'm getting spoiled. I not only want to know when it's coming, I even get to know where it is en route. I can follow the truck.
Yeah.
which actually there's some quantum analogies, I think. But, thank you, Farbad.
Thank you so much. Thank you, Professor Kwiat. Thank you, Professor Willner. Thank you, everyone. I think we answered all the questions for now. Maybe we can take 5 minutes break, and then we'll start at 11 o'clock with the next talk. I can share with you. Our next talk is at 11 o'clock, Professor William Oliver from MIT, Quantum Engineering of Superconducting Qubits. You take 5 minutes.
Thanks so much, everyone.
Oh, sorry.
I'm just saying thanks. I'll be around.
I had one
other
question.
questions.
Thank you so much, Professor Kwiat.
Yeah.
Oh, hi, I'm Doug Steen from CPP, undergrad for MSET. I just wanted to ask, I did a study this semester with trilateration with Wi-Fi signals, and I found it was using just a regular free space path loss model, and it produced a lot of regional uncertainty errors, like where the radiuses would intersect in the circles. Using trilateration, you wouldn't get a perfect point of intersection, so it produced an area of uncertainty. And so I guess in quantum, there's basically no uncertainty in the measurement, because if you know one position of the other entangled particle, you automatically by default would know the other one, right? Is that like?
I would say so. First of all, you almost never know anything completely. So because you have detector jitter, that's one thing. And for example, the relative timing of the two photons, remember I said that the width of that dip went as 1 over the bandwidth. So to the extent that they don't have infinite bandwidth, that means when you measure one, you don't necessarily know the exact position of the other one. You'll know it to within whatever 1 over that bandwidth is. So there will still be some uncertainty. I guess what I would say is that the type of uncertainty you're probably describing has to do with the uncertainty in the modes that you're using, to use Alan's language. And that same sort of uncertainty will still exist at the quantum level. The quantum is sort of the mode you can think of like cars that are driving by, whatever shape they are. And then the quantum are, do you put no photons into that car, or 1 photon, or an entangled photon, or squeeze state, or something like that. So all the problem with the modes will still persist at the quantum level.
Okay, so you still get the same like problems with SNR and interference and all that other stuff. Okay.
Yeah,
It's just smaller on a smaller scale, you would say?
Yeah, I mean, you mentioned signal to noise ratio, and that's a case where actually quantum could be lower, because in the quantum case, you might know roughly when to look. So if you have pairs of photons and you detect one, you know when the other one is coming, maybe to within, actually, you might know to within 100 femtoseconds, although you probably can't resolve that with your detector. But in any event, you might know to within 10 picoseconds, and you can use that to exclude any noise that doesn't come within that 10 picoseconds. So you definitely can get a benefit for signal to noise.
Yes, that sounds like a lot better than I think I was getting. I was getting in the 10 to the power of 3 with the regional area, or 10 to the power of 3 meters squared for regional area of uncertainty. So
I mean, one other thing I'll just say in general, since I talk about metrology, in general, the quantum cases will give you an advantage per photon, but it needs to be appreciated that that's not always what you care about. So for example, if you go to get an MRI done or something like that, or an ultrasound because you have a kid, you don't necessarily care about per photon because they have a lot of photons that are coming out of their ultrasound device. And in the quantum case, you have to do it sort of one photon at a time. And so you become much more limited in terms of how much signal you can get per second in the quantum case. Similarly, if you're trying to do quantum communication over let's say any communication over a lossy channel, like from deep space, if only 1 out of 1,000 photons gets through, you'd be better off using a classical pulse that has 100,000 photons, and then you're still going to get 100 photons in your pulse getting through. That's easy to detect. If you do it at the quantum level, you have to do it 1 photon at a time, and that means only 1% of your signal is actually going to make it. So that turns out not to be a good use.
Okay, makes sense. Thank you. Thank you
Sure.
very much.
Okay, welcome back. It's my great honor and pleasure to introduce Professor William Oliver. William Oliver is jointly appointed Associate Professor of Electrical Engineering and Computer Science at Lincoln Laboratory, Fellow and Lincoln Laboratory Fellow at Massachusetts Institute of Technology. He serves as the Director of the Center for Quantum Engineering and Associate Director of the Research Laboratory of Electronics. Will's research interests include the material growth, fabrication, design, measurement of superconducting qubits, as well as the development of cryogenic packaging and control electronics. Will is a fellow of American Physical Society, senior member of IEEE, and is appointed to the National Quantum Initiative Advisory Committee. He also serves on the U.S. Committee for Superconducting Electronics and is an IEEE Applied Superconductivity Conference board member. He received his PhD in electrical engineering from Stanford University in 2003. Professor Oliver's talk is on quantum engineering of superconducting qubits. Superconducting qubits are coherent artificial atoms assembled from electrical circuit elements and microwave optical components. Their lithographic scalability, compatibility with microwave control, and operability at nanoscale timescales all converge to make the superconducting qubit a highly attractive candidate for constituting logical elements of quantum information processing. Over the past decade, spectacular improvements in the manufacturing and control of these devices have moved the superconducting qubit modality from realm of scientific curiosity to threshold of technical reality. In this talk, Professor Oliver will present the progress, challenges, and opportunities ahead in the engineering larger scale processors. It's my great pleasure and honor to welcome Professor William Oliver.
Yeah, thank you very much for the introduction, Farhad. I just want to check that you can hear me and that the slides look okay.
Yes, we can hear you on the slides, okay.
Great, thank you very much. Again, it's really a pleasure to be here. Thank you for the invitation. And without further ado, before we get into quantum computing, I think it's worthwhile to take a look back at the history of classical electronic computing. If we go back to the early 1900s, 1906, the vacuum tube was invented and was used for radio transceivers for many years, as you know. But it was a full 40 years before we finally had a computer based on vacuum tubes, one called ENIAC, for example, from the University of Pennsylvania. Now, around that time, the transistor was invented at Bell Laboratories. And although within about 10 years, we had a fully transistor-based computer called TIXO, or TX0, built here at MIT, didn't look anything like the computers we're using right now for this Zoom session. To get closer to where we are today, we had to invent the integrated circuit in the late 1950s. But even then, you had to fast forward to the 70s before you got processors like the Intel 4004 and the 8008 with a few thousand transistors. Go forward another 20, 25 years to get to the Pentium Pro with 5.5 million transistors. And then fast forward another 20, 25 years to get to where we are today with billions of transistors on a chip, multi-core processing, and graphical processing units. So from the standpoint of today and looking back, it's been well over 100 years of development. Now, in comparison, quantum computing is basically at the first mile. In the early 80s, Richard Feynman, a famous physicist, suggested that if you want to simulate a quantum system, you should use a quantum system to do that. And theorists thought about it for quite a while. In the mid-90s, we started to see algorithms like Shor's algorithm and Grover's algorithm, and the first proposals for error correction of quantum systems. In the early 2000s, small quantum computers could factor the number 15 into 3 times 5 using Shor's algorithm. And then 20 years on is where we are today, where we have processors with, I don't know, 50-ish qubits available for people to use in the cloud, and even a demonstration or a few demonstrations of quantum advantage. So the takeaway here is that it's true, quantum computing is transitioning from scientific curiosity, laboratory curiosities, to a technical reality. But there's a lot of hype, and advancing from discovery to useful machines takes time and it takes engineering. And that's where we are today, is trying to make this a technical reality. Maybe another takeaway is you've got to be in the game to play. It may not be surprising that many of the leaders of classical electronic computing have been in that game for decades. So where we are today with superconducting processors, I just show here a few pictures. Here's Google's Sycamore chip. Here's a chip from IBM that's available on the cloud. Here's Rigetti's chip on the cloud. This is the backside of, I guess, the packaging of Intel chip. This is D-Wave's quantum computer, which is a different type than the others. It's a quantum annealer. And then, of course, this one in the middle is not a quantum computer. This is the Wright Flyer from the early 1900s, the first plane that was manned and under its own power, propulsion, was able to fly about 600 feet. And as amazing as all these processors are and the fast advances we've made, I still think that we are at the very, very beginnings, just like the very, very beginnings of flight. And what it means is that there's a lot of promise, but to realize that promise, we need to engineer quantum systems that are robust, reproducible, and extensible. And so in this talk, I'd like to just at a high level talk about what quantum computing is and what we're doing to achieve these goals. So just 2 slides on what is a quantum computer and what makes it different. So we know classical computers, they're based on bits like a transistor. The state is either 0 or 1. That's it. They're discrete. And if you set it in a particular state like 1, you're going to measure it in 1. Quantum computers are different. They're based on quantum bits or qubits, a coherent 2-level system. We think of them as what we call the block sphere or the planet Earth. you can think of the North Pole as state 0, the South Pole is state 1. And if your qubit exists at the North or South Pole, well, then it's just a classical bit, that's it. But of course, you can be anywhere else on the surface of the planet Earth. And when you are, the qubit is in a superposition state of 0 and 1 with weighting coefficients alpha and beta called probability amplitudes. And if you're on the equator, or say anywhere other than the North or South Pole, you're in a superposition state. And in particular on the equator, if you make a measurement, you'll have a 50% chance of snapping back to the North Pole, state 0, or 50% chance of snapping back to the South Pole, state 1. And so this is a different type of behavior than we're used to in classical bits. And so it means that we encode this information in a new way. Now, the consequence of that can be seen here. Classically, if you have bits, and let's say you have n of those bits, you can, of course, represent 2 to the n states. So that's an exponentially large state space. But the issue is you can only represent one of them at a time. So for example, let's say n equals 3. So 0, 0, 0, that might be an input to my classical computer, and it calculates some function of that. But if I want to calculate different input states to see what the output states are, I basically have a choice. I can reproduce the hardware, duplicate it, that's classical parallelism. Or I can take one computer but input different inputs as a function of time, and serially in time. And so whether you're reproducing hardware or looking at this serially in time, it's an exponentially large number of inputs, and so it takes exponential time or exponential space. Now, quantum computers can take those n qubits and that 2 to the n components and put it into one superposition state with weighting coefficients, and here where they're A, alpha, beta, gamma, etc. And conceptually, you can think of taking that input, putting it into your quantum computer, and it'll run a function, and then you get an output. We'll talk about that output in a moment because it's quite important. But to get from input to output relies on something called quantum parallelism and quantum interference to arise at a single answer. So in a nutshell, quantum computers encode information in a fundamentally different way. Now, we perform operations on them much in the same way as we do on a classical computer. So classically, we have these gates that you're familiar with, Boolean logic gates like the NOT gate, the AND gate, the OR gate, etc. And I won't talk through the whole table, but here's the truth table. And we know that with just a handful of these gates, we can form what we know is a universal set, meaning that we can perform any Boolean logic with just a handful of these logic gates. And we also know that it's not unique. The NOT gate and the AND gate together, or the NOT gate and the OR gate together can do this. Now, quantum mechanically, it's the same story. We have a large number of, well, small number, but a handful of single qubit gates, and the rotation on the block sphere of the planet Earth is shown over here. Then we have a couple 2 qubit gates where the rotation on qubit 1 depends on the state of qubit 2. And with just a handful of these single and 2 qubit gates, you can form a universal set of gates that can perform any quantum logic. Now, in fact, it can also perform any Boolean logic, but often, in fact, a quantum computer will perform Boolean logic no better than a classical computer. Often, it'll actually be worse. But with a small set of single and 2 qubit gates, you can perform arbitrary quantum logic. So to take a look at what this single qubit operation is, let's consider a classical NOT gate and its analog, which we'll take here as the X gate. So the classical NOT gate takes 0 to 1 or vice versa, and the quantum NOT gate does a similar operation. So we can look at it here and see the rotations on the block sphere. What you're looking at is the blue arrow on the left is the qubit state, and the red arrow that comes in and out represents the envelope of a driving pulse that we use to drive it. That'll depend on the technology. But what you can see is we're rotating from the North Pole 0 to the South Pole 1. And in this sense, this is just a classical gate because we started at the North Pole, we ended at the South Pole. It's called an X gate, I'll say, because we're rotating around what we define here as the X-axis. But of course, you need not start at the North or South Pole. You could start anywhere on the surface of the planet Earth. The gate performs the same operation. It rotates around the X-axis by 180 degrees, But of course, we're starting with a superposition state and ending with a superposition state. And this gate takes those coefficients alpha and beta and swaps their position. Okay, so this is an example of a single qubit operation. Now, 2-qubit operations we can think of in the context of a classical exclusive OR gate, which you probably know there's 2 inputs. These are Boolean inputs now, bits. One's the control bit, one's the target bit, and here's the truth table. And basically, if the control bit is 0, the target bit is just passed to the output. But when the control bit is 1, you perform a NOT gate to get the output. So 0 becomes 1 and 1 becomes 0. It's the same story on the quantum side. We call this a controlled NOT gate. You have qubits X and Y. This is the symbolism for it. X is the control qubit, Y is the target. The truth table looks the same, but we're now using quantum mechanical notation. And we can just basically say that, look, the rotation of the target qubit Y depends on the state of the control qubit X. And so we can take an interesting example where our input on the qubit X is a superposition 0 plus 1, and our input on the Y target, the control qubit, sorry, let me say this again. The control qubit X is in a superposition of 0 and 1, and the target qubit Y is in state 0. And so we can take these one at a time. So when the control qubit is 0, we just pass the target qubit forward. So that gives us 0, 0 state here. But when the control qubit is 1, we know we have to flip the target. So 0 becomes 1. And now this is a very interesting state because we can no longer factor it into a component that looks only like a qubit X and only looks like a qubit Y. In fact, this is an example of an entangled state where it cannot be factored, and that's true in any basis, not just in the one that I've chosen here along the Z-axis. And so with these types of single and 2-qubit gates, we can form a universal gate model quantum computer and computation with just this small set of single and 2-qubit gates. And so what an algorithm looks like is the following. You have a large input state, massive superposition state. You could even make it an equal superposition state, so all the coefficients here nominally are the same. And you feed that into a quantum computer, and you perform an algorithm, which is basically a prescription of these single and 2-qubit gates. So single qubit gates, you perform 1 qubit operation, 1 gate on 1 qubit. But what you can see here is that you'll impact the coefficients on all of the aspects that form this superposition state. And this is called quantum parallelism. That's followed by quantum mechanical interference. And the net result is you've changed the value of these coefficients or these probability amplitudes. Of course, there's also 2-qubit gates, whereas we just saw the rotation on, say, the target qubit depends on the state of the control qubit. But the point is it's 1 gate applied to 1 pair of qubits, but you're affecting the coefficients of the entire, of all of the components of this superposition state. Again, quantum parallelism followed by interference. And at the end of the day, what you want to have your quantum computer state be is something that looks like this, where one of the coefficients is very close to 1 and all of the other ones are close to 0. And that's because when we make a measurement, we need to get a classical result. And we know that we're going to project this state out onto only one of these components. And the probability that we project it out to any one of them goes as magnitude of the component's value squared. And so if one of these weighting coefficients is near 1, then with high probability, in fact, we will get the answer that we seek. And so that's the challenge for the algorithm designer, is to make a combination of single and 2-qubit gates, the right prescription, such that you get the answer to your problem and it's weighted with near unity coefficient. So there are a number of algorithms, of course, that exist today. And I just show a few of them here. I won't read through the whole chart, but they center around simulation, quantum simulation, which was Feynman's original idea, applications such as quantum chemistry, material science, and the like. There's also number theoretic algorithms like Peter Shor's factoring algorithm with application to cryptanalysis. There's linear systems of equations. We can sample solutions to large linear systems. There's optimization algorithms. and also search in the construct of unsorted or unstructured databases. Now I show the classical in quantum time and the speed up here. Again, I won't read through it. They're mostly exponential, some are polynomial, some we're not sure because the proofs are challenging. And also the research today, what the limitations are and what we're working on. So why don't we have quantum computers today? What's the problem? And the answer is basically these two time scales, the coherence time and the gate time. So the coherence time is, you can think of this as the qubit's lifetime. You have a quantum state at some time t equals 0. We can make that state. We know exactly what it is. But from that point forward, the qubits and the quantum computer interact with their environment. And over time, this state blurs and eventually becomes lost. And it's not that the qubits disappeared. They're still physically there. But what's happened is that after this period of time, the state we would have predicted these qubits and this quantum computer to be in is quite different than what it's actually in. And that's why we indicate it as being blurry. It's lost to us and no longer useful. And the time scale over which this happens is the coherence time of the qubits. Now we can compare with that the gate time, how rapidly we can perform these single and 2 qubit operations. And of course, the figure of merit then is how many operations can I do before my qubits decohere, right? That's the figure of merit. And one thing to emphasize is that it's not enough to just say that my coherence times are long, right? Different technologies will have different coherence times, but they'll also have different gate times. And so it's not enough to have a very long coherence time. It's how many gates can I do within that coherence time that matters. And so as a result, we're at a point today where there are basically two paths to realizing quantum algorithms. One is what we call the noisy intermediate scale quantum era. This term was coined by Preskill at Caltech, John Preskill. And basically what this is we have the coherence time we've got. We can do as many gates as we can within that coherence time. Let's see what we can do. And that's what's here on the right. On the left is the march towards trying to develop or implementing quantum versions of error correction, where by adding more qubits and redundancy, we can improve the overall performance, the resilience of these. And so we talk about logical qubits being comprised of, say, 1,000 physical qubits. The logical qubit is protected. The physical qubits look like the same qubits we use in the NISQ era. And those qubits have to be good enough in order to actually show an improvement when you add many of them together. And so that's called the threshold for these error correcting codes. And you want to be well beyond the threshold so that the resource overhead, the amount of redundancy you need, doesn't blow up unrealistically. And so with that, let me now talk about superconducting qubits. They're basically harmonic oscillators, LC resonators. If you take an inductor and a capacitor, make a parallel resonance circuit, cool it down to low enough temperatures. How low? Well, the energy scale KT has to be much less than Planck's constant times the resonance frequency of this circuit. If you do that, then this is a harmonic oscillator. It has a parabolic potential, and it has discrete states, 0, 1, 2, etc. Now, this is a quantum mechanical circuit, but it's not a qubit yet because we can't uniquely identify the 0-1 transition. Its energy separation is identical to the 1-2, to the 2-3, etc. So to make it, to be able to identify a 0-1 transition, we need a nonlinear element. And the one that we choose is called a Josephson junction. It's a tunnel junction made from superconducting leads and an insulating barrier. So aluminum, aluminum oxide, aluminum would work. And if you combine the Josephson relations for voltage and current together in the usual way to define an inductance, you find that this inductance is highly nonlinear in the current that flows through it. So by replacing the linear inductor with a Josephson junction, you basically have an LC circuit, but it's anharmonic. In fact, in this simple case, the potential is a cosine, and the 0-1 transition frequency as a result is different than the 1-2 frequency. And so we can just draw a box around 0 and 1 and say that's our qubit. So there's a large family of artificial atoms that are built from this concept by adding more inductors and capacitors. And I show some of them here. I won't talk through each one. The one that we just looked at is called a fixed frequency transmon. But by adding more of these elements, you can define and design different functionality. And so the design parameters that we have basically are things like the critical current of the junction, its capacitance, additional capacitance that we add, say a number of additional junctions that we add, et cetera. And with those, we can define the qubit properties like the 0-1 transition frequency or its degree of anharmonicity. How different is 0-1 from 1-2? Or the sensitivity to different types of noise in the environment. These are things that we can design for. Now, we typically choose the transition frequency of our qubits to be around 5 gigahertz. That's convenient for a number of reasons, but it does have one consequence, and that is that we must operate at low temperatures because the thermal energy corresponding to 5 gigahertz is about 250 millikelvin, meaning that even at this low temperature of 250 millikelvin, just the thermal environment will drive transitions if your 0-1 transition frequency is 5 gigahertz. So what that means is that we just need to operate much colder than that. And we can do that in a dilution refrigerator. I just showed one here from different sides. Size scale, this is about 0.5 meter across, 0.5 meter down. And this whole region here will get to 20 millikelvin. To put that in context, it's about 100 times colder than outer space. Now, you see a lot of familiar microwave knickknacks here, like filters and switches and coaxes and the like, and these packages hold the qubits. These are commercially available items. 30 or 40 years ago, this was a research project, but today you can purchase these commercially and they generally work. Of course, we fabricate our devices, and so we have to engineer the fabrication in such a way that we achieve this high coherence. And we fabricate on silicon wafers. I should emphasize that this is a silicon technology. We fabricate on silicon wafers. We use materials like aluminum and tinitride that are silicon compatible. We use the same fabrication tools as a silicon line. And so, there's really no distinction between this and a silicon technology other than these materials, when cooled down, are going to superconduct and give us the properties that we talked about. This is an 8-inch wafer, 150 millimeters. If you zoom in on a chip on that wafer, you'll find something like this. There's 5 of these plus signs in a row. This plus sign is a capacitor, a lateral capacitor to ground, capacitance to ground. Up here are readout resonators. Down here on this side are control lines that we bring in to control the qubit. If we zoom in further, you can see this capacitor a little easier now. And the inductor is quite small. You have to zoom in yet again to see 2 Josephson junctions in a loop. We put them in a loop because if we put a magnetic field through this loop, we can actually control the 0-1 transition frequency. That's one of the knobs we can turn. And then here's a Josephson junction, the smallest length scale of around 200 nanometers or so. So this is what it looks like. We control them with microwave engineering. So this is controlled using IQ mixing with a local oscillator and an arbitrary waveform generator. You're probably familiar with IQ mixers. If you put a pulse into the I port at an intermediate frequency, it'll multiply with a local oscillator tone, and what comes out is the sum and difference frequency of this enveloped pulse. If you go in the I port, there'll be no phase shift, so we call that in phase. And if you go in the Q port, that's called the quadrature port. Well, there's a 90-degree phase shift if you do that. And we'll associate that with the X and Y axes. So this is what control looks like. Here's our planet Earth or block sphere again. The blue vector here is the qubit state, and the red vector shows the envelope. Now, let me qualify that the blue and the red over here are not related to the blue and the red on the left. On the right, blue and red means in phase and quadrature. So here's an in phase pulse rotating around the x-axis. Here is rotating 180 degrees, minus 180 degrees, minus x-axis. Now we'll switch to the Q port, go 180 degrees again. And now this is half of the area. So it's pi over 2 brings us to the equator, and then another pi over 2 brings us back up to the North Pole. So this is how we can achieve universal control using just AWGs, local oscillators, and mixers. Now, the question is, of course, how well are we doing these pulses? And this is the notion of gate fidelity. And you can think of, if I start at the North Pole and go to the South Pole, how close did I get to the South Pole, right? Then the closer you get, the closer to unit fidelity you have. The state of the art today for these different rotations that we might do is above 3 nines. This is data from my own group, but many groups have achieved this. So more than 99.9%. And for 2 qubit gate fidelity, the state of the art is almost 3 nines. Here's 99.87%, 99.76% for what's known as an I-swap gate and the controlled Z gate that we talked about earlier. So with this, of course, there's quantum advantage, and this has been demonstrated quite strongly by the Google team. This is their Sycamore chip, which had 53 qubits on it. And what they showed is that if they perform a random series of single qubit gates, 2 qubit gates, then again, single qubit, 2 qubit, and they repeat that a large number of cycles or times, at shorter numbers of cycles, in fact, they can just simulate on a classical computer what they get. And they're just benchmarking the output, compared what they got versus what they simulated. But if you continue to increase the number of cycles, at some point, you're going to have too many gates and too many qubits to actually predict what output you have. And so that's when they get into the quantum advantage regime. And that's this paper from late 2019. So using 53 qubits, the Google AI team, quantum AI team, demonstrated a calculation, this random number generation, if you want to think of it that way, in about 200 seconds that is expected to have taken a few days or more on the Summit supercomputer at Oak Ridge. Now we say we expected because nobody actually tried it on, used all of Summit's power. But of course, Summit has, 10 to the 17 transistors, uses 100 megawatts of power to operate, and it would have had to operate for a couple days. So clearly there's a big distinction between the quantum and the classical case here. So if we, and Farbad, please interrupt me if I get to the end of time so I don't go over. How much time do we have left?
We have until 11:30, but it's okay because after Professor Lvovsky talk, we have 30 minutes Q&A, so we can extend to that time.
I see. Okay, so I'll take 5 more minutes if that's okay. So superconducting qubits, state of the art today, the coherence time's called T2, which you can think of as how long you live on the equator. That's about 95 microseconds. The fidelities I already mentioned. And our largest chip at MIT has 16 qubits. And if you look at this, it's interesting. You can see those 16 qubits in a 4x4 array, but you start to see some long wire bonds. And that's because, of course, we can't bring all the signals and the I/O that we need from the edge of the chip, and we now have to jump over and break the plane. And of course, we prefer not to do that with wire bonds. We'd like to 3D integrate, and so through the IARPA Quantum Enhanced Optimization Program, we developed a 3D integration protocol that I'd like to show you here that we're using. So the qubit chip is on top. We call it a 3-stack because it takes 3 chips. The qubit chip's on top. We have an interposer, which I'll describe in a moment. And then on the bottom is where we have a multi-wiring layer ROIC, if you want to think of that, readout and interconnect layer. We do it this way because there are a few features. One is that the qubits, to have long coherence times, their electromagnetic fields need to remain confined to regions that have high Q. And so these substrates are high resistivity silicon, which do have high Q. It also gives us another plane to work with, so we can put active elements on top of the interposer. And of course, through silicon vias are critical that we can bring the signals up and down from the ROIC itself. So this is what it looks like. And of course, the qubit chip would look like this 16 qubit chip, it just flipped over. The interposer chip, these are through silicon vias. They have high aspect ratio. They're 200 microns deep, but only 10 to 20 microns on top. They're lined with titanium nitride, which superconducts below 3 Kelvin. Of course, we're at 20 millikelvin, so this is fine. They superconduct. This is a picture, so a few more SEM pictures. So this is the side cut. This is looking from the top in. This is a racetrack or an oval shape. If you look down from the top on a qubit, this is the capacitor and the qubit control line, you can see these little black ovals. Those are the TSVs. And of course, this is an RF transition combining 10 TSVs, 2 of them for signal and 8 for the ground. You can compare this with other TSVs that have been proposed and are being used, and of course they're too large, 500 microns or 100 microns even. If you need 10, 20, 30 TSVs per qubit, it dominates the size. Now there's another large length item here, which is the resonator. It's a millimeter long, and that's used for readout. And so 3D integration can help us there as well. By using the TSV and connecting it to a compact resonator on the bottom side of this interposer chip, the TSV can basically couple to the qubit and read it out, but it vastly reduces the amount of real estate needed to do this readout. What we show here is the coherence time T1, 40 microseconds, in this configuration where we're using the TSVs to control and read out the qubit. And if we look at just the planar 2D version of this particular design also got around 40 microseconds. So, the coherence times are not impacted in this 3D structure at this level. The bottom layer is a readout and interconnect chip. And what I'll just say is that this is niobium, also a superconductor, multiple wiring layers, planarized, even has some active elements. This is how we can route multiple signals around until they get to the TSV we need to take them up to the qubit layer. And so there's a lot of activity worldwide. We know this, but necking back out, what we see is that a lot of companies are joining and recognizing that quantum will impact their bottom line in the future. And so it's in this environment that we formed the Center for Quantum Engineering at MIT. And I emphasize again that there's a lot of promise, but there's a lot of hype currently in what quantum computers can do and over what time scale they will do it. And so we want to be careful of the hype so we don't rush into a quantum winter, but there is tremendous promise, and this is exemplary of that. So with that, let me just finish up and acknowledge the teams at Lincoln Laboratory and the MIT campus, and thank you for your attention. I apologize for going over a little bit.
Thank you so much, Professor Oliver, for the excellent presentation. We don't have time for Q&A, but after Professor Lvovsky talk, we will have more time, 30 minutes for Q&A. I'm sorry, Professor Lvovsky, for a little delay. So I would like to introduce the next talk. It's my great pleasure and honor to introduce Professor Alexander Lvovsky. Make sure my sound is on. Alexander Lvovsky is an experimental physicist. He was born and raised in Moscow and did his undergraduate in physics at Moscow Institute of Physics and Technology. In 1993, he became a graduate student in physics at Columbia University in New York City. His thesis research conducted under the supervision of Sven Hartmann was in the field of coherent optical transients in atomic gases. After completing his PhD in 1998, he spent a year at the University of California, Berkeley as a postdoctoral fellow in the Department of Physics, and then 5 years at University in Konstanz in Germany. First, as an Alexander von Humboldt postdoctoral fellow, then as a research group leader in quantum optical information technology. In 2004, he became professor in the Department of Physics and Astronomy at the University of Calgary, and from autumn 2018, a professor at University of Oxford. Alexander has also been a part of the team that created Russian Quantum Center, and since 2013, he has been working there as a part-time research group leader. Alexander is a past Canada Research Chair and lifetime member of the American Physical Society, a fellow of Optical Society, and a winner of many awards, most notably the International Quantum Communications Award, a commendation letter from the Prime Minister of Canada, and Emmy Noether Research Award from German Science Foundation. His research has been featured by CBC, NBC, Wired, New Scientist, MIT Technology Review, TASS, Daily Mail, and other media. Professor Lvovsky talk is on optics and machine learning that are natural symbionts. He will present 3 examples of how these fields can benefit each other based on their recent experimental work, optical neural networks and their all optical training, robotic alignment of optical experiments, application of machine learning in linear optical far field super solution image. It's my great pleasure to welcome Professor Lvovsky.
Thank you. Thank you. Do you hear me? Do you see my screen?
Yes, I can hear.
Excellent, excellent. Yeah, so thank you. It's also an honor and a pleasure to be here and to be invited to this conference. Yeah, so a bit about the group. So we moved to Oxford quite recently in 2018. And yes, so there are two groups. So I like to think about them as one sort of in the superposition of 2 places, Oxford and Moscow. So both groups are doing a lot of research. And those of you who know me, you probably know me as a hardcore quantum optics scientist, but now we diversified quite a lot. So we are still doing a bit of quantum optics, but at the same time, we are doing machine learning, quantum machine learning, classical machine learning. We are doing this deep optics, optical neural networks, and even a bit of robotics. So variety of things, some of them more successful than others. And I'm going to today talk to you about, actually I shortened only 2 topics. One is the robotic alignment of an optical interferometer, and the other one is super resolution microscopy. 2 completely different topics, but they're united by this. You see, this conference is sort of on symbiosis between classical optics, quantum optics, and machine learning, and that's exactly what these sort of 2 otherwise unrelated presentations are, how they are united together. So yeah, robotic alignment of an optical interferometer. Those of you who are experimentalists know that a quantum circuit consists mostly of interferometers, right? I mean, some of you have seen this picture from Manuel Bloch's lab, right? I mean, not all optical tables look like this, but yeah, but all of them, many of them have a lot of interferometers. Yes, interferometer is a component of every quantum optical experiment, and in addition, it's of course an important measurement tool, a sort of primary measurement tool in optics, one can argue. But in order to work well, an interferometer needs to be aligned. Yeah, and well, this is an example of what alignment of the interferometer means for a simple case of Mach-Zehnder interferometer. That means that the 2 beams must precisely coincide in position and direction, right? So a well-aligned interferometer will look like this. A poorly aligned, misaligned interferometer will look like this. In one case, you have visibility 1. In the other case, you have low visibility, right? Almost no fringes. Now, this picture shows the formation of interference pattern and sort of our setup. So what we do is we build our Mach-Zehnder interferometer and send the interference fringe to a camera, right? And what we observe on the camera is a picture that looks like this, right? There are 2 spots from individual beams, right? And then in the area where they overlap, they show interference fringes, right? So here are 2 videos. I should also say that we changed the path length difference of one of the beams with respect to the other by means of this piezoelectric transducer. So this first video shows a poorly aligned interferometer. As you can see, that's kind of similar to here, right? You have 2 spots and interference fringe where they overlap. And this video shows a well-aligned interferometer. So here, when we move the piezo, the beams precisely overlap. So you see just blinking, you don't see any fringes. So yes, so that's our experimental setup. What you see here is, well, what you've just seen in the previous diagram. The only thing is that these two elements here, the mirror and the second beam splitter, are on motorized mirror mounts. Yeah, and so our interferobot, our reinforcement learning agent, which we call interferobot, receives the data from the camera and then sends commands to those motorized translation stages. One somewhat technical detail is that our piezo, normally, those of you who are experimental physicists, you know that you want to oscillate the piezo. Usually what's sent to the piezo is a sawtooth, and we also send a sawtooth, but the sawtooth is asymmetric. So it sort of moves like this, moves slowly one way and then briefly and quickly jerks back. Slowly one way and briefly jerks. That's in order to provide the agent some kind of asymmetry, some kind of information, because you see, just from the interference pattern, you cannot tell whether the beams are misaligned like this or like this. The interference pattern will be the same. And so this sawtooth provides this information. Yeah, so now in the language of reinforcement learning, right, we have an agent which interacts with the environment, and the environment has a state, right, which, well, the information about the state is provided to the agent in the form of observation. Then the agent performs an action on the environment, and the environment then transitions to the next state, and it awards the agent with the reward. So in our case, the state is the position of one beam with respect to the other, right? We control only one of the two beams. Yeah, we control only this beam too. And so the state is the position of one beam with respect to the other. However, this information is not accessible to the agent. What is accessible to the agent is the observation, is this video picture, is this video film that is received from the camera. And then the agent performs actions. The action is to turn the mirror. So it's allowed to turn by one of the three discrete angles in both directions. And yes, altogether there are 25 actions. 2 mounts, 2 directions, 2 dimensions, yeah, and 3 magnitudes, and plus there is a do nothing action, altogether 25 actions. Now the reward that we use to train our agent is, well, naively, what one would offer as a reward is just visibility, right? However, visibility itself does not really, that turns out to be not a good reward. Why? First of all, because it's always positive. That is, if the agent just, spends time doing nothing, it will still keep receiving a positive reward and will not be motivated to align. So we add this -1 on every step to make the reward negative, to penalize the agent who spends too much time aligning the interferometer. And then again, experimentalists know that when we align the interferometer, the alignment has to be really good. That is, the visibility of 95% and the visibility of 98% make a big difference, right? So you really want, like this little last few percent, you really want to achieve. To that end, we add this additional term here, which is a strong, which is a strong reward for approximating 1. So you see the visibility of 95% gives you a reward of about 3, and the visibility of 98% gives you a reward of about 4. So sensible difference due to these little few percent. Right, then, okay, then of course, every time we reset the interferometer, and then there are technical details about reinforcement learning that I won't bother you with. We use an algorithm called DQN. We train. One thing perhaps that's important to tell you is that we train in simulation. Right now, that's sort of a curse of robotics, right? I mean, if you think about it, machine learning made great progress in the past few years. Basically, now one can say that machines can perform better than humans in all environments about which they have complete information, right? So machines recognize faces better than human, machines play chess better than humans, right? Machine calculate integrals better than humans. One thing that machines do not yet do well is they do not operate well in our surrounding world. Now, why is it the case? Why it's like, you know, it would seem for us as, you know, even for children, for babies, it's easy to, like, you know, to do simple actions, say, you know, pour a glass of water. For the machine, it's very difficult. Why is it the case? The reason is that it's very difficult to acquire a training set, right? When we train, when we train when we train on the environment that's fully known to the machine, we can do millions of actions and millions of samples of the environment. On the other hand, in real life, we can acquire maybe 1 or 2 samples a second. So the sample acquisition is much slower, and that's a big problem. That's why robotics has been developing very slowly in the past few years. People are working hard on finding solutions to this problem, and hopefully it will be found. Hopefully one day it will be found. But at the moment, what we have to do is we have to train on simulated data, right? So we just build a model of our interferometer, simulate the interference pattern, and train our agent on that interference pattern. Now, when we do that, it turns out to be not enough, because you see, well, a simulated laser beam looks like this. The experimental laser beam looks like this. If we train our agent on these beams, then it will not work on these beams. So what you have to do is you have to artificially add noise, add simulated noise to your data, right? So what you have to do is to your training set, right? So you have to vary the beam radius, you have to vary the brightness, you have to add noise to each pixel, and so on. And then it becomes somewhat reasonable, and then the agent trained in this noisy, randomized environment will perform reasonably well also on a real interferometer. So this slide here shows training in simulation, so not yet in reality. So here you can see basically what we plot is the performance as a function along the horizontal axis. So it's the number of updates, how many times we update our neural network. And you can see that the average angle between the beams per episode goes down, which is good. The average distance also goes down, which is also good. Now, the bottom 2 pictures shows the advantage of this visibility, of this reward that we have introduced. You see that in the end, the mean visibility does not visibly increase, right? So it would seem that the agent that is trained on just the visibility would not see the difference. But because we feed to the agent this amplified reward, the reward that amplifies the sort of the endpoint, you see that it keeps gradually increasing even near the endpoint. Right. So that was in simulation. Now the practical experiment. Here are 2 videos. Again, one is well, we had Russian state television. This experiment was done in Moscow, so we had Russian state television visiting on that day, and they asked us to show something fun. So we showed them this interferobot, and you kind of get an idea of what it looks like. And this picture is actually more scientific. It shows you the actual alignment of the interference pattern. So here's the camera image, and what happens here is what you see here is the actions that the agent is performing, and you can see that how it's aligned, what kind of actions it's doing, right, with the 2 mirrors, and how it's gradually aligning the interferometer. Yeah, now it's aligned. Now, we of course wanted to compare the performance of this interferobot with a human, and well, I'll just show you this plot here. So what you see here is the blue one is the agent, is the interferobot, and the red one is the human. And you see that well, in the end, the agent wins, right? The agent does much better, right? And here we measure we plot the visibility as a function of time. But you can also see remarkably what happens, right? That initially initially, at some point, so first the interferobot actually knows where to go. The interferobot does better. Why is it? It's because of this asymmetric sawtooth that's sent to the piezo. You see, the human has to try both their directions of the knob, and then they will know which way to move. The interferobot sees the interference pattern and sees the video and can immediately tell where to move. But then, you know, human adjusts themselves, then they figure out, and then they quickly do the rough alignment, right? So in this rough alignment, the human wins, right? But then when it comes to fine alignment, it takes quite a bit of time, right, for the human to figure it out. But the agent, you see, just steadily goes up to the top. So, yeah. So basically, the interferobot wins, performs better than the human expert. Now, the last slide of this part of the talk. How smart is our agent, right? Suppose you want to climb a hill, right? So it's aligning the interferometer is like climbing a hill. Now, you're still starting somewhere here, and you're not allowed to go straight to the hill, right? You're allowed to only move like in somewhat sideways direction, like this and like this, right? And then you're allowed to do small sizes or big sizes, with small steps or big steps. How would you move? Well, if you're not very smart, you would move like this. You would take the greedy actions. So you would take steps such that every step would take you closer to the top, right? But then you need a lot of steps. If you're intelligent, however, you will do something like this, right? You would take larger steps, yeah, that will take you to the top faster, but then at some point you really have to go down the hill. You have to completely misalign your interferometer. And the question is, how is our agent doing? Here's strong evidence that it's actually intelligent and not greedy. What you see here is, for example, these points 24, 25, and 26. You see at point 24, it has almost aligned the interferometer, but not very well. So what it does, it goes to point 25, misaligns it significantly to compensate for it at point 26. Yeah, so here you can see the phase space diagram. Also, you go from 24 to 25 to 26, right? Instead of like doing these baby steps towards the hilltop. So that was the first part. Now the second half of the talk is completely different story. It's about overcoming diffraction limit in optical imaging. Now, all of you who studied optics know that the resolution of optical devices is limited by the diffraction. That is, and even if our source is a single point, the image will be a blurry point due to this diffraction, right? And the question is, can we overcome the diffraction limit in our imaging? This question has been around, forever, since at least 200 years. There was this quest to improve the resolution of microscopes, and well, people came with some solutions, right? So basically, one can identify two main avenues of super resolution microscopy. One is near field with near field probes, right? You probe in near field, and then of course there is no diffraction, so this diffraction limit does not apply. Or you use some kind of nonlinear properties. You interact with the sample in a nonlinear fashion, and again, diffraction limit does not apply. So that's of course great, and there were many Nobel Prizes. The last one I think was in 2014 in chemistry for this type of microscopy. However, what would be really great is to you see, these microscopes, they still have to, these imaging devices, they still have to somehow interact with your object, right? They have to be invasive, right? They have to do something with the object and look at its response. It would be much more interesting to develop some kind of passive microscope that would passively analyze the light that is just coming from the object without touching the object in any way, right? Now, of course, that would, if we could do something like this, it would, completely change the face of optical imaging, right? Because it would allow us to image objects such as stars, right? To achieve super resolution in astronomy, which is now completely beyond limits. And it sounds crazy, right? Because of course you cannot break the laws of optics. How can you go beyond the diffraction limit that's been known for hundreds of years? And the answer is, turns out, it is possible. But what you have to do, you see, this diffraction limit applies only to a certain type of measurement, namely measuring the intensity of the optical field in the image plane. What you can do instead is do some different measurement. You can instead measure not the intensity, but the correlation of amplitudes of the electric field at different points within the same image plane, right? So a different kind of measurement which has not been analyzed, and to which it turns out that the Rayleigh limit does not apply or applies not fully. So this was a theoretical breakthrough that was achieved about 5 years ago. And well, the question then arises, how would you do this? How would you do this correlation measurement rather than intensity measurement? And the answer is, it's related to what to one of the previous talks, where the image has. So what we do is we decompose our image into transverse modes, right? So instead of measuring the intensity, we ask ourselves how much light coming from the source is present in each transverse mode, and we use the Hermite-Gaussian basis. Now, the principle can be understood from this diagram. So suppose first we have a source just on the axis of our optical system, and we look at Hermite-Gaussian mode 0, 1. Now, this Hermite-Gaussian mode 0, 1 is asymmetric, right? So we'll have all of the signal will go into the fundamental Hermite-Gaussian mode, and no signal will go into the TM01, right? So we'll get no signal whatsoever. However, when we displace the object, it will now also emit a little bit of light into the asymmetric mode, so we'll get some signal in this asymmetric Hermite-Gaussian mode 0, 1, right? So by measuring the intensity in this TM01, we can measure the displacement of our single object or the separation of 2 point objects. And this measurement turns out to be much more precise than what you can achieve via direct measurement. Now, why it is much more precise can be kind of understood from this picture. Suppose you have 2 slits, right? So in this case, it's 1 slit, in this case, it's 2 slits, right? If you do direct imaging, it's kind of, these 2 pictures are kind of similar to each other, right? So you cannot really use this information to measure the separation between the pixels. However, if you do this Hermite-Gaussian detection, in this case, you will see no signal in TM01. In this case, you will see some signal in TM01, or if you use single photons, you will get a click you get a weak signal, you get a click with some probability. It turns out that working in this setting, that is distinguishing between a situation of no signal and a little signal, is much easier than distinguishing between a lot of signal and a different lot of signal, right? It's kind of related to what Kwiat has been talking about, this null detection, right? You have small displacement, and this leads to some signal versus zero signal, and it turns out to work much better. So now some technical detail. As again was discussed, what you need to do in order to implement this in practice, you need to sort your incoming light, your incoming field, into Hermite-Gaussian modes, right? You need to demultiplex into Hermite-Gaussian modes. In practice, it is difficult. Now solutions are starting to appear, right? They are gradually, this technology is gradually emerging, but it's not there yet. So what we do instead in our experiments is something else. Instead of detecting in certain Hermite-Gaussian modes, we use heterodyne detection. We use heterodyne detection. Right now, what is heterodyne detection? Heterodyne detection, what is shown here, is detection of interference between your signal and the local oscillator. And heterodyne detector responds to the field only in the mode that matches the mode of the local oscillator, right? So if you prepare your local oscillator in Hermite-Gaussian mode TM01, you will only see the part of the incoming field that matches this mode TM01. It is much easier to prepare light in a certain mode than to sort of demultiplex light into that mode. And that's what we use here. Turns out to be much more practical. So I'll show you two experiments. One experiment was done back in 2016, back in Calgary. So here what we do is, basically we have this double slit, and well, to clarify, it's a toy experiment. We don't really have a real microscope yet. We have a macroscopic object. So in this case, it's just, you know, pairs of slits from a teaching lab. However, we artificially reduce the resolution of our microscope by using an optical system with low numerical aperture. So yes, so here you can see we generate the image of our double slit, and here's our local oscillator that we can prepare in a variety of Hermite-Gaussian modes. Well, this picture shows direct imaging. The top row is when the iris is open, right? So when we work above the Rayleigh limit, and we can clearly resolve the slits. Now, when we close the iris, then we cannot resolve them anymore, right? And that's the regime we work in. And well, here we plot the position of the slit versus the signal that we observe in TM01 versus the position of the slit. And you can see that we can resolve the displacement of the slit to a very high, you know, to a very high precision of about 1/1000th of a Rayleigh limit for coherent light and 100th of the Rayleigh limit for incoherent light. And well, here we just displace an object. Here we measure the separation of the two objects, and here again it's about 1/50th of the Rayleigh limit, the resolution we obtain. Now, however, this is really not our goal. What our real goal is not just measure the separation of two objects, but really to image objects with sub-Rayleigh resolution, right? And the question is, can we use this Hermite-Gaussian technique to achieve this? The answer is yes, we can. And well, this equation shows the basic idea. It basically tells you that the heterodyne photocurrent that you obtain is proportional to the moment of the object to the object amplitude distribution, with the degree of the moment corresponding to the degree of the Hermite-Gaussian mode in which you're doing your observation. So if you know all the moments, then you theoretically you can reconstruct the object with arbitrarily high precision. In practice, the quality of the reconstruction, of course, depends on how many moments, how many modes you use, right? You cannot use infinite number of modes. The number of, this number is finite. For example, if you use 20 modes, then you can achieve about 1/3 of the Rayleigh limit, right? 1/3 of the diffraction limit. And that's what we do in our experiment. So this experiment that was now done at Oxford this year, it's quite similar to the previous one, except that now we don't use the cavity. We don't use a cavity to generate Hermite-Gaussian modes. Instead, we use a spatial light modulator, and we also use another spatial light modulator to generate our objects, right? So now we have a full control of both the object and the image, and we can achieve, we have a much bigger playground. Yeah, and the object that we choose to image is, of course, the logo of the University of Oxford, right? So what we do is we divide the logo into these little subframes, which we display in sequence, and you can see a fragment of the object, and you can, for comparison, you can see the point spread function because everything is coherent. And it's this case here, right? So you can see that basically you cannot resolve, right, these little letters with within the diffraction limit. Right now, before I show you the results, here's one important point: how neural networks are related to all this. The answer is, well, going back to this equation here. You see, in theory, we have these moments from the moments where you can reconstruct the object. In practice, it doesn't really work, right? Because this equation is written for the idealized case of no noise, right? No aberrations, the point spread function being perfectly Gaussian and so on. All of that is not really present in practice, right? So in practice, we have all this junk and all our math therefore becomes useless. How do we resolve this? We use a neural network, right? So what we do is we display a whole bunch of training objects, right, to our as our objects, and then we measure the photocurrents associated with the Hermite-Gaussian modes, and then we train our network to reconstruct the object from these photocurrents. Importantly, as the label for our training, we don't use the original object, but we use a somewhat smeared object to make sure that we're not trying to extract from the network the information that that is not there, that physically cannot be extracted, right? If we did use the original object, then we would oversample, and the training would not have been good. So yes, so after training the network, we can show it a proper real object, and it will then reconstruct it. And here you can see the reconstruction. This is our original object. So in this case, it's the coat of arm of the University of Oxford on the left. On the right, in the middle, you can see the direct imaging case, right? So the image that you acquire with the camera. You can see that you cannot resolve much. Here on the right, you can see the image acquired with our method, the Hermite-Gaussian microscopy. You can see that the resolution is much higher. It's higher by about a factor of 2, right? And I'm approaching the end of my talk, so let me emphasize again. So I think this is, this is something remarkable, right? Because we have beaten the diffraction limit, not resorting to either near field observation or nonlinear optics. It's entirely passive observation using only linear optics and only in the far field. So we don't really touch our object in any way. Now, of course, it will take some time before this becomes a proper, imaging technology, right? We need to answer a lot of open questions, such as we did the experiment with a coherent source. Now we actually, we just did the experiment with an incoherent source. Of course, in practice, microscopy is incoherent. Then, as I told you, the setup was really a toy setup. It was not the object was not really microscopic. So we need to try it with truly microscopic objects. And finally, when we deal with practical microscopy, then the signal is narrow, the signal is quite broadband, right? Broadband signals cannot be resolved using heterodyne detection. We have to use proper demultiplexing to perform Hermite-Gaussian measurements, and that's what we have to do next. So yeah, with this, I'd like to thank you for listening, and I'll be happy to answer any questions.
Thank you, Professor Lvovsky, for excellent presentation. If there's any question, Professor Kwiat, you have?
Yeah, hi, Alex, that's beautiful.
Hello. Yeah.
Hi, so with regard to your last comment in terms of a broadband source, so the idea is that you would break it into channels basically, and you could do with a narrowband interference with a number of different sources, heterodyne sources?
Well, I don't want to heterodyne at all, right? Because heterodyning only works with narrowband sources, right? The bandwidth of a heterodyne detector can be a gigahertz at most, whereas proper microscopy sources, like fluorescent microscopy sources, can be hundreds of nanometers. So what you have to do is you have to
why is the heterodyne restricted to just a gigahertz? What sets that scale?
Well, you look, because if the signal and the local oscillator are of different frequencies, then the output electronic signal will, well, the output electronic signal will be of the frequency that equals the frequency difference between the signal and the local oscillator.
Oh, I see. Yeah, okay, so you do actually mean heterodyne. Sorry, I've been talking to a lot of astronomers about long baseline interferometry, and when they say heterodyne, they mean what we would have said was homodyne, but you really mean different frequencies.
I really mean, well, I mean, homodyne is a particular case of heterodyning with zero bandwidth.
Right.
So yes, so if we have perfect matching between the frequency of the laser and the frequency of the signal and the local oscillator, for example, when we are just looking at the scattering object, then we could use homo-heterodyning. But otherwise, the application is quite limited.
For broad bandwidth, then, is the idea that you could use one of these like quantum pulse gates, where those you can project onto things that are broader bandwidth, I guess.
Well, we could use this demultiplexing that was mentioned in one of the previous talks. That you can actually demultiplex. You can input. You can send in an optical mode, and the output would be multiple single mode fibers. Containing the signal corresponding to each of the basis modes. Well, either Laguerre-Gaussian. I think our method would also work with Laguerre-Gaussian, but it's probably not difficult to make it Hermite-Gaussian as well.
Thanks.
Okay, any other question? I see one comment in the chat. I'm not sure if this is helpful. The educational slits are often just printed on slides. There are better ones cut by femtosecond lasers in metal. You see in the chat.
Well, the purpose of that experiment was proof of principle demonstration. So that the educational slits are not printed, right? They actually, the actual slits, they are, there are transparent areas in otherwise opaque slides, right? So there is nothing wrong with them except that they are macroscopic, right? And we want to work with a microscopic object. Instead, what we did is we artificially reduced our numerical aperture.
Thank you. If you have any question, you can raise hand and then or type in the Q&A. If not, I'd like to thank Professor Lvovsky for the excellent presentation.
Thank you.
I appreciate your time. If there's any question, I think we are here to answer any question. But meanwhile, I would like to, this is our time for Q&A and for our, if you like to take a break, but we have in the panelists, I think joined us, if I can find. Oh yes, we have Professor Martin Cryan from University of Bristol. He would like to talk a little bit about their program at Bristol.
Okay, yeah, that's great. Can I share my screen?
You should be able to share if you like to.
Okay. Yeah, let me just get that to work. Okay. Hopefully you can all see those slides. Yeah, so thank you very much, Farbod, for giving me the opportunity to just tell you a little bit about some of the educational aspects of the quantum technology work that we're doing in Bristol. A few years ago, the opportunity arose to set up a new MSc program. We connected, a lot of the quantum activity in Bristol is within the physics department. And we thought there's a nice opportunity to spread that out more into electrical engineering. You know, I think quantum technologies have reached that point where a lot of the issues are actually more engineering related than physics sometimes. And so I took the job of setting up an MSc program that's sort of embedded within electrical engineering, but with basically aimed at electrical engineers who want to get into quantum technology. So to give them that foundation in quantum, but also teach them things like, you know, RF technologies, FPGA technology, programming. And yeah, so this is sort of an overview, and I'm not sure what the audience is I'm speaking to here, but I'm happy to tell everybody about what we're doing. We think it's quite a good idea. So, whoops. Yeah, so I'm sure everybody realizes that the sort of potential of quantum technologies. All sorts of amazing applications are possible, and lots of spin-off technologies. I think that's the other thing that we have to bear in mind. There's not only the things we're actually working on, but there's a lot of associated, unexpected ideas will come out of this as well. And this program is aimed at sort of teaching students, so you know, well-qualified undergraduate, what we call undergraduate students in the UK. So coming out of their first degree, Bachelor of Engineering or Master of Engineering, or also physics students too. We're open to either electrical engineer or physicists. That's the kind of requirement. And the way we set the program up is we've got 3 different streams within the program. The one I'm most interested in is quantum photonic chip design. So we do a lot of that in Bristol, and we've now partnered with a UK foundry at the University of Southampton called Cornerstone, where we're allowing, and for the first time this year, and we're really kind of proud of it, we've been able to run an actual a fab run for the MSc students, where they designed their chips in February this year, and they were turned around in 3 months, and they've now measured their own chips, all sorts of correlated photon sources, tunable phase shifters. It's in an SOI platform. And we get very low cost access to that foundry as a special deal with the University of Southampton. So yeah, there's great opportunities in photonic chip design, but we also have a very big communication networks research group, and they're now starting to do a lot of quantum networking activities. So we have a specific stream connected with that part of our research team. And then we also do a lot of sort of theoretical work and algorithm work in Bristol. And so we have a stream that we call Quantum Information Technologies, where, again, it's this one's kind of aimed at electrical engineers who want to get more of the quantum foundations. If you want to, you know, create new algorithms and new sort of like the software level of these systems. And the way our MSc programs are structured, they're 12-month course, they're 12-month long, basically one year long, runs from September till September. And we have 10 core units that all students study. We have one unit that we call Engineering Research Skills that prepares students for their research project, which then runs from around June time till the end of August. So they do like 100% project phase across the summer. And these are the core units that we've chosen. So we have some sort of traditional, let me see if I can get a laser pointer on here. Yeah, okay. So we got some traditional units, sort of like radio frequency engineering and digital signal processing units that are sort of, you know, our typical electrical engineering units that we're finding are more and more important in quantum technologies. We also, you know, if students haven't come across the fundamentals of optoelectronics, we teach them that as well. You know, what is an optical fiber, what is an LED, what is a laser type things. And then we go on to more system level units. So that's mainly aimed at classical communications, you know, double DM systems, but a lot of that is now translating over to quantum technologies. And we have an advanced unit where we delve more into the sort of research aspects of what we do. So in my case, that's sort of nanophotonics, plasmonics, and things like photonic crystals. But we also have a section of that course on nonlinear optics as well, which, you know, links right into all sorts of you know, single photon source technologies. And then for the electrical engineers, we have the first unit where we introduce them to quantum fundamentals. So that's their first exposure to you know, what is a qubit, you know, how you sort of use, you know, unitary operations and Poincare sphere type approaches, which is all very new. You know, the problem with electrical engineering in the UK, you know, we don't teach students what a Hamiltonian is or any of those things. So there's quite a steep learning curve for UK electrical engineers before they can fully step into quantum technology. So we think this unit helps prepare them for that. So that's our core units that everybody studies. And then these are the three different streams that we offer. So in terms of chip design, what we're working on a lot at the moment in Bristol is actually combining photonic integrated circuit technology with quite conventional electronic integrated circuit technology, and the challenge is to bring them together on the same through the same foundry, for example. So we're teaching students about, you know, conventional integrated circuit electronics, how do you design a VLSI chip, and then we step into the quantum aspects of this thing. So this unit here, nanofabrication for quantum engineering, is the unit where the students did their chip fab run. Originally, we sort of planned that unit where they were going to our clean room. We've got a quite a nice clean room, Voyager e-beam system, but the COVID situation actually made us rethink that unit, and I think it's worked out quite well in the sense that we've got our students to actually do a full fab chip run, which we probably wouldn't have done if we hadn't been forced into the sort of remote teaching scenario. And then we have a quantum system engineering where they start to think that they look at a number of different quantum technologies and sort of compare them in a sort of like a system level approach. Quantum networks, these are all these units here are really focused on learning how classical networks operate. And what we're exploring a lot in Bristol at the moment is what are the challenges in operating quantum communication systems overlaid over the top of a classical communication system. And so to do that properly, you really have to understand how the classical systems work. And all those units introduce that really well. And this is the more sort of theoretical quantum information stream that links with our maths department and our physics department quite strongly. And so this is for students who are more interested in the kind of software and algorithm development side of these technologies. And a really big part of these programs is what we call the individual research project, where students get to, you know, work pretty much one-to-one with one of the faculty academics in Bristol. And students get to choose from around 50 project ideas, and that's not only supplied from academics in what we call KET labs, which is our main sort of research group, but we have a whole host of industrial partners, a lot of which are spin-outs from Bristol. And we've been really fortunate this year that actually more than 50% of our students are actually doing projects embedded within industrial partners. And that goes all the way up to multinationals, like some of you might have heard of Airbus is quite a big multinational in the UK and Europe. And they're very interested in exploring what the possibilities are of quantum technologies. And I've got some examples here. So here's some of the companies that we're working with. Ket's Quantum spun out of Bristol a few years ago, and they're very interested in things like quantum random number generators, and they're now at the point where actually engineering are their issues. The quantum side works fine, but it's about, you know, how do you design the chip, you know, in a low-cost way, package it, get it to work. Again, overlaying it with classical systems. And so it's really sort of a whole host of issues that electrical engineering students can deal with. Again, they're interested in quantum networks and all sorts of characterization and validation that, you know, is bread and butter for electrical engineering students. But physicists, you know, wouldn't normally be interested in that stuff, if I put it that way. But, you know, that's what engineers like doing, is making sure something works properly and every time and understands the specifications of these things. Airbus are interested in all sorts of aspects of these technologies. They can't tell us too much in detail of what they're interested, but it's great that they put 2 project ideas in, and one of those got chosen by a student. And we have another spin out called Control that is actually purely electrical engineering, and it's about developing the driver systems and all the control systems that go around quantum technology. And that's Josh Silverstone as one of our new academics in Bristol. And then on the research side, these are sort of some of the academic projects that we offered this year. Let me pick out that's one of my projects. I'm interested in resonant cavities for things like full wave mixing. And again, we're going to attempt to put that through some of these foundries that we've got access to in the UK. But there's a whole host of different aspects of quantum technology that we offer for students. And just a couple of words on our sort of research structure. So, you know, a lot of these activities span electrical engineering and the School of Physics. KET Labs is majority based in the School of Physics, but also links into electrical engineering. We have another research organization called the Smart Internet Lab, and then our research groups sit within this Smart Internet Lab. I'm in this research group, Photonics and Quantum, which links into this KET Labs. The summary is there's about sort of 200 academics and researchers that are looking at all of these different aspects of these technologies. And in terms of careers, the main route we think for MSc students from this program is to go on to do a PhD. And so we've specifically designed this MSc program. We have what's called the Centre for Doctoral Training, which is the way the UK have sort of moved to training PhD students now. It's a little bit more like the US model, where it's a 4-year program. First year is sort of training, short projects and lectures. And then you have a 3-year PhD program after that. And we've designed this MSc program to link into that. So for example, we have around about 100 applicants for our CDT PhD program every year, but only 10 get accepted. So it's incredibly difficult to get on that program. And what we think the MSc can do is if you sort of miss out or you're not quite properly aligned to do PhD straight away, come onto our MSc program, you can learn the fundamentals, and then you can attempt to do a PhD, maybe at Bristol, maybe elsewhere. And we're really pleased this year that 2 of our MSc students have actually been offered places on our PhD programs, you know, proving the concept that the program was designed for. Yeah, and we think, you know, I think the time is sort of coming now where not only, you know, quantum spin-outs and startups are looking for electrical engineers, but a lot of the big multinationals, they've reached the point where a lot of the physics is established, and it's actually about the nitty-gritty of, you know, designing the chips, making sure they work every time. Yeah, and that's the sort of what electrical engineers are sort of interested in. Yeah, we have a quantum entrepreneur program in Bristol called QTech, and that itself has produced startups, which again, you know, we think pretty soon we'll be looking for MSc qualified students. So yeah, that's it from. Oh yeah, and this just I'll leave that slide there about entry requirements. You know, if anyone's actually genuinely interested, you need what we call an upper 2nd class degree in the UK. But yeah, if anybody's interested, they can contact me, and we can have a chat about that.
Thank you so much, Professor.
Thank you very much. I'm happy to answer any questions if anybody's got any.
I would like to ask you to send us the presentation so I can
sure.
share with you in future with attendees. Some of them are interested and they're asking to read more about the slides that you shared.
Yeah.
I have a quick question. We are out of time, unfortunately.
Okay.
But I have a question, if you don't mind. I can see a lot of excellent programs in engineering, like yourself, which is an amazing program in quantum engineering, but I can see a lot of good work in electrical and computer engineering programs, but I haven't seen really in mechanical and aerospace. So for the first time, we offered in my mechatronics course some fundamentals of quantum, like how to do quantum entanglement, how to do maybe quantum cryptography experiment. And we think that because mechatronics is a kind of a multi-domain area, and this is a work with my colleague, Professor Clarence de Silva, who is one of the authorities in the mechatronics, and leaders in this area, Dr. Marco Quadrelli from JPL, who also has been working with us, and other colleagues. We think that this is, we really need to bring also these kind of areas to mechanical and aerospace engineering.
Yeah, you're right. We're starting to do a lot of work in Bristol on acousto-optics. And acoustics, electrical engineers don't learn acoustics in their undergraduate degree programs, and we're gonna have to form really big links with the mechanical engineers and yeah, I think that's a really good idea.
I think we should really integrate such technologies, for example, in robotics for communications. And I mentioned earlier that Professor Kwiat was one of the leaders or one of the pioneers of drone-to-drone quantum key distribution application. So we are following this work, and we feel that it is necessary for mechanical engineers and aerospace engineers also to get involved, because great work is done by mostly electrical and computer engineers like yourself.
Yeah. No, you're right. I think that's a really good idea, actually. I think I'm going to discuss that with my mechanical engineering, colleagues, and see what they think. And it's all about, what background you have. And it's such a big step into quantum technologies that electrical engineers are quite close. They all learn electromagnetics, especially if you're doing quantum photonics, which we tend to do a lot in Bristol. That step is not too difficult. But for mechanical engineers, the step might be even bigger. But
they haven't got any background, absolutely no background in quantum mechanical engineers. But we were able, with my colleagues, with the help of my colleagues, to put together something that is basic, like quantum entanglement experiment with basic equivalent. So, for example, what is a polarizing beam splitter? What does it do? What is BBO crystal? What does it do? And demonstrate that. Actually, we were able to demonstrate that for the students in the lab.
That's great.
Okay, so the undergraduate mechatronics student, they were able to understand it. And I don't see why they shouldn't understand if the complex theory, for example, behind it. We don't need to teach all the quantum mechanics theory to understand how quantum entanglement experimentally work, and maybe how the quantum cryptography communication can work for two robots to communicate with each other.
Yeah, you're right. There's lots of opportunities.
Yeah, thank you very much. Thank you for your time.
Okay, yeah, thank you.
Thank you so much.
Bye.
So we have to now, our next speaker is Professor Clarice Aiello. I'm very sorry that we are a little bit behind the schedule. And our next speaker is Professor Enrique Galvez. So I hope that he doesn't mind that we go a little bit over time, 5 minutes to his time, because we are a little bit behind. So I would like to introduce our next distinguished speaker, Professor Clarice Aiello. Dr. Clarice Aiello is a quantum engineer interested in how quantum physics informs biology at the nanoscale. She is an expert on nanosensors, harnessing room temperature quantum effects in noisy environment. Aiello received PhD from MIT in electrical engineering and held postdoctoral appointments in bioengineering at Stanford and in chemistry at Berkeley. She joined UCLA in 2019, where she leads the quantum biology tech lab. Professor Aiello's talk is on from nanotech to living sensors, unraveling the spin physics of biosensing at the nanoscale, substantial into vitro, and physiological experiment results suggest that similar coherent spin physics might underlie phenomena as varies as the biosensing of magnetic fields in animal navigation, and the magnetosensitivity of metabolic reactions related to oxidative stress in cells. If this is correct, organisms might behave for a short time as living quantum sensors and might be studied and controlled using quantum sensing. It's quantum sensing techniques developed for technological sensors. Dr. Aiello will outline their approach towards performing coherent quantum measurement and control in proteins, cells and organisms in order to understand how they interact with their environment and how physiological is regulated by physiology is regulated by such interactions. Can coherent spin physics be established or refuted to account for physiologically relevant biosensing phenomena and be manipulated to technological and therapeutic advantage? It's my great pleasure to welcome Professor Aiello.
Hi everyone. Hi Farbod. Farbod, I cannot turn my video on. It says the host has disabled it. Wait, and now I cannot hear you. Hello? This is working.
I'm sorry about that. You should be able now to turn on. I'm sorry about that.
Oh, am I there? Can you see me?
Yes, I can see you.
Awesome. I cannot see myself, but you have to. You can see me, right? Oh my God.
I can see you.
You have no idea how many things went wrong just before this presentation. So I cannot see myself. I hope you can see me more or less. And at some point I'm going to use props. So let me know if you cannot see my spins when I start talking about spins. You can see, awesome. But shout out if you cannot. So thank you so very much for the opportunity to talk here. And as many of the other people who presented here today, I also like to call myself a quantum engineer. And this means that I build apparatuses to study and control things that are so small and so well protected from their environment that they're better described by the laws of quantum mechanics, as opposed to the laws of classical mechanics that ruled everything big around us. So people get a little confused when I tell them that actually I study things like birds and butterflies. And before I explain where I'm going, I really need to tell you where I come from. We're going to start talking about quantum mechanics and quantum sensing in particular. And by within 20 minutes, we will have talked about things of biological relevance, such as organismal migration, how our cells react to oxidative stress and radiation. And I hope to have given you a glimpse on how I believe we can learn with nature to build better technologies. And that's because I'm a quantum engineer who's interested, as Farbod said, in how quantum physics informs biology at the nanoscale. So as a preamble to my talk, let me tell you that I think that humankind is obsessed with measuring things better because it might make us feel like we understand nature better. So we might think about measuring better frequencies, for example, with this atomic clock at NIST that helps us determine very, very precisely what a second is based on atomic transitions. We might think about measuring better magnetic fields so that the image of our baby is better resolved. And yes, that's the magnetic resonance image of a baby inside the mother's belly. And we can also think about measuring better accelerations so that our gaming experience is enhanced. Those tiny little accelerometers are now ubiquitous in all our handheld devices. But the question that I ask is, what happens if the quantity that you want to measure is very, very small? Or worse, what happens if the object causing the quantity to be measured is very, very small? I'm going to argue that in this case, you need a tiny little sensor that can measure tiny little things. If the sensor is tiny, let's make it very tiny. Let's make it quantum. There's a whole body of mathematical evidence that can prove that if you use a quantum object as a sensor, your measurement is improved. In other words, the sensor's quantumness enhances the measurement. In my past, I worked with such a technological quantum sensor that was a very fine magnetometer. And this sensor was implemented by a single spin in diamond. And I would like to talk to you a little bit about this technological quantum sensor that I worked with. So here's what I promised. And without further ado, I just would like to make you remember what a spin is. So a spin is a merely quantum property that has no classical equivalent that tiny things such as electrons and atomic nuclei they have. And spins, basically, this quantum property of spin measures how well this quantum particle interacts with magnetic fields. So engineers and physicists and chemists like to depict spin as an arrow, and spin up or spin down just signify two different energy levels of this merely quantum property called spin. Okay. The single spin in diamond that I put to use as a very sensitive magnetometer actually arose in a tiny crystalline defect in the diamond lattice. The diamond lattice is, of course, composed of a lot of carbon atoms, but sometimes there are imperfections in the solid state that can cause interesting things, like the phenomenon that I'm going to describe. This spin arises from a crystal defect that is actually a color center. Color center in diamonds are the crystalline defects that happen that actually are responsible for the color of those nice diamonds that you see at the bottom of the slide. And color centers are named so because those crystalline defects can absorb light, get excited, and then fluoresce, emit light back. And that's actually why you see the color of those very nice diamonds. The particular color center crystal defect that I worked with is one that is actually very famous. It's called the nitrogen vacancy center. It arises naturally, but it can also be engineered, and it happens when a vacancy, that is a missing carbon atom, sits nearby next to a nitrogen atom, which is one of the most commonly occurring substitutional impurities in the diamond lattice. When the nitrogen sits close to the vacancies, it's sort of like a mess of electrons interacting, right? Near the vacancy, there are electrons that are unpaired. The nitrogen has like other electrons. There might be extra charges, but something very interesting happens when you calculate the quantum mechanical energy levels of this mess, this atomically sized mess. And in fact, it turns out that when you calculate the quantum mechanical energy levels of this mass, it looks very much like the quantum energy levels of one single spin. So for all purposes here in this talk, we can look at this crystalline defect and think of it as a electronic spin that can have different energies. The way that we find those defects in the lab to play with them is by placing a diamond slab. It can be a crappy diamond slab, okay, nothing special. At room temperature, we place the diamond slab on top of a moving stage, okay? And as we move this sample around, we shine laser onto this sample. Actually, it doesn't need to be lasers, but in fact, it's more efficient and more convenient. But all we want is for light of an appropriate energy to hit one of those defects. Like if when we're scanning the slab, the light hits one of those defects, the defect is a color center, so it's going to absorb this light and then fluoresce back. And this fluorescence we can collect. And this is what it looks like in increasing zooms. So at the very bottom to the right, what you're looking at is a blob. This blob is, it's about 500 microns, 500 nanometers in diameter. It's a diffraction limited blob, but it's very interesting because what you're looking at is this fluorescence signature of one single spin, one effective single spin. Again, this blob is relatively big because that's the limitation of our optical components, but the defect is tiny, 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 but we still can see in our computer the manifestation of the fluorescence of this single electronic spin. And in fact, things get even better because this defect has the very interesting property that depending on how strongly this blob is fluorescing at your computer screen, we can actually distinguish if the spin was up or down. In the quantum sensing jargon, people say that this spin has a quantum state dependent fluorescence intensity. And that's also very convenient when we start playing around with those spins, because just by looking at its mean fluorescence, we can know in which state it was. But I promised that I would put it to work as a very sensitive magnetometer, and here it goes how it works. They're named 0 and 1. I named the two different spin energy levels of this spin in diamond. And actually their difference in energy is about 3 gigahertz. It's in the microwave. Okay? And it turns out that in the presence of an external field, the state that I mark 0 there is insensitive to magnetic fields. It doesn't really care. But in the presence of a magnetic field, the state marked +1 is going to interact with this magnetic field and actually is going to be promoted a tiny little bit in energy by this tiny quantity that I marked there as delta. And of course, for those of you who remember, this delta is proportional to the intensity of the magnetic field via something called Zeeman interaction. And now I'm going to make a point that is not usually made in the circles of quantum sensing, but I think it's a point that is extremely important, which is the fact that the problem of measuring magnetic fields is actually mapped onto the problem of being able to measure a tiny mismatch, a tiny detuning from resonance, delta. So if you know what the microwave difference of energy between 0 and 1 is, in the absence of a magnetic field, if you can measure how much you go away from this known resonance, you can actually observe, you can actually infer what magnetic field this spin was subject to. Okay, and actually measuring detunings from resonance is how much of quantum sensing and actually quantum computing works. But the catch of this very nice way of measuring magnetic fields is that it only works while the spin is well described by the laws of quantum mechanics. Everything that starts quantum dies classical, so that at some point, this spin, which in particular for those of you who have taken quantum mechanics, this spin, which could at some point be well described by a coherent superposition of being in state 0 and in state 1, it will be sucked into the classical world, and it will only be either in state 0 or in state 1. And this time, the time of loss of coherence is usually called coherence time. And it turns out that the coherence time of such spin at room temperature and in bulk, like in the solid state lattice, and for crappy diamonds, is about 2 microseconds. And this number can actually be increased if you engineer the material. And 2 microseconds at room temperature inside like a messy lattice is actually very, very long. And that's one of the reasons why this spin defect has attracted so much attention in the past. This also means that you can only obtain useful sensor information within this coherence time window. Right? So the name of the game, again, in both quantum computing and quantum sensing, is trying to give kicks to this spin to try to make it live longer as a well-defined quantum system, so that you can acquire a signal for longer. You can think of it about in the same way that you would think about acquiring a signal for a longer time. The longer you acquire a signal in time, when you Fourier transform it, the better the detail that you're going to have in your spectrum. For here, it's the same. If we can find a way of kicking this spin so that it maintains its quantum properties, you have a lot to gain. You can think of it like as a swing, right? If you're smart enough to give kicks to the swing at certain points, the amplitude of oscillation is not going to go down. And engineers and physicists have known how to give these very fine spin kicks. And actually, for 3/4 of a century now, with electromagnetic fields. Starting from a field called nuclear magnetic resonance, people have known that by applying engineered electromagnetic fields in particular ways, you can control the spin and extend its quantumness. Okay, so before I get a little bit more technical, I just want you not to forget about the big picture. Okay, the big picture is to have a tiny little sensor that you can bring in close proximity to a tiny little sample, so that magnetic fields produced by, say, one or a couple of spins or something else in the sample, tiny little magnetic fields can be picked up by this tiny little sensor, and then we can read out the magnetic field information via this tiny sensitive quantum sensor. Okay. Now, this is probably going to be the most technical that I'm going to get. Don't forget this big picture, but I would like to share with you just one example of such a spin control experiment. Okay, so I'm going to show how we can use a sequence of electromagnetic pulses called rotary echo in order to find magnetic fields. So this sequence of electromagnetic pulses has nuclear magnetic resonance origins, and it's depicted in nuclear magnetic resonance jargon in this plot to the right. What this plot means is that you are applying a CW microwave field onto your spin, onto your diamond, okay, at the known resonance, okay, at a frequency at the known resonance between spin up and spin down, and at particular intervals, okay, you're going to flip the phase of the pulse. So you're applying a continuous microwave and you flip the phase, just the phase. This sequence of tailored electromagnetic radiation is known in nuclear magnetic resonance to correct for imperfections in the microwave, okay, if you have a faulty microwave source or whatnot. But it's also known not to correct for detunings from resonance. And if you remember from my last slide, detunings from resonance is actually what's going to give us information about the magnetic field. So if we do that, if we apply this sequence of microwaves with phase flips onto our spin, what you obtain in the lab is a signal as a function of your interrogation time. And the signal is just fluorescence normalized. So you can think of this, for those of you who have seen this, as a Rabi experiment with modulation. So for example, when the spin is emitting at its maximum, it's, say, in state up. When the spin is emitting at its lowest intensity, it's in state down, and everything in between the spin is in a superposition. So we actually can apply a average Hamiltonian theory formalism to understand how the signal depends on the detuning delta, this tiny little delta there in the formula that we want to measure. So we know exactly how to take this delta information from this signal by just fitting this signal. And in fact, I'm not going to explain, but if you Fourier transform the signal, you get something that looks like a spectrum. Again, I'm not giving you enough information on how to read this plot. I just would like to mention that with this plot there, with this signal, I am measuring a magnetic field, a detuning corresponding to a magnetic field, which is about 1/10 of the magnetic field of the Earth, which is tiny, very tiny. But again, I just want you to remember this big picture, that you have a tiny sensor that can sense tiny samples. And I also actually want you to remember another thing, which is the fact that I have just shown you a technological quantum sensor that works at room temperature and in noisy environments. The sample can be noisy, biological, and the sensor itself is embedded in a solid state lattice. Turns out that, again, I've shown you one technological quantum sensor, and actually those that you see there were the types of quantum sensor that I was used to working with, until I discovered, almost by chance, and I got convinced that many times nature outperformed humankind-made sensors in crazy ways. So I would like to spend the rest of my 5 minutes to talk to you about a natural magnetic field sensor that seems to be quantum driven, that seems to be working very much like this spin in diamond. Okay? But in order first to talk about this magnetic field sensor, this natural magnetic field sensor, I would like to talk about the biology at the nanoscale, namely the chemistry. Okay, and it's been known from basic chemistry that magnetic fields can alter the final products of a class of chemical reactions that are spin sensitive. Okay, so this means that, and now you should be looking at my spin again, that there are some chemical reactions where one spin is important, so that if the spin is up, the reaction continues through one branch, and if the spin is down, the reaction continues through another branch. Importantly, the macroscopic final products of those two branches can be very different. So if a spin can be altered, the probability that we find it up or down at the top of a chemical reaction, a long time after that, and macroscopically, it's been proven in chemistry, I mean, that this is possible, that a tiny little spin mechanism can have big final consequences for physiological processes. And this has been demonstrated at room temperature, in solution, in the gas phase, in the solids phase, and down to magnetic fields of the strength of the magnetic field of the Earth. If you're curious, the magnetic field of the Earth is about 50 microtesla, which is way smaller than the magnetic field that you feel when you put your cell phone close to your face. And it turns out that in the beginning of the 80s, biophysicists wanted to understand how some organisms seem to be following the magnetic field of the Earth, at least as a partial cue, when they were migrating, such as birds and butterflies. And then the chemists, the biophysicists and chemists, they made a hypothesis, right? Were the same spin-dependent chemical reaction at play in organisms under physiological conditions, organisms could sense magnetic fields to the extent that they could sense different physiological concentrations of products coming from these spin-sensitive chemical reactions. And this hasn't been proven, but what you see there is what people think could be happening, for example, in the eyes of birds, where a particular protein called cryptochrome is thought to be regulating, seem to be sustaining a spin-dependent chemical reaction, so that people speculate that birds, when they look in different directions, their retinal sensitivity might be altered via spin-dependent mechanisms so that they can see magnetic field lines. Okay, so whereas this is still a hypothesis, a cryptochrome, which is a protein that is well conserved across the tree of life, cryptochrome has been implicated in many studies having to do with magnetosensing. All those organisms there express cryptochrome, and the organisms boxed in red are organisms for which there have been magnetic field studies implicating to some extent cryptochrome. And it turns out that evidence for cryptochrome or spin-based magnetic field sensing by organisms is really widespread, but unfortunately at disconnected length scales. So in the very short length scales to the left of the slide, people with cryptochrome in solution actually see that cryptochrome behaves pretty much like the single spin in diamond. For example, what researchers did was capture the fluorescence of cryptochrome as a function of the time during which they shone laser onto it. Okay, so they were exciting cryptochrome. Cryptochrome is a fluorescent protein, so it absorbs light and fluoresces pretty much like the spin in diamond, the color center. So what the researchers saw was that as they excited with the laser, the fluorescence went down. It means that you're killing the protein. It's called bleaching. But as the researchers pulsed on and off a magnetic field, and this is not an artifact, it has been reproduced many, many times, the fluorescence intensity emitted by this protein was sort of modulated with the field, which is, again, in pretty much a one-to-one correspondence to the spin in diamond. Just by looking at how strongly the spin in diamond was emitting light, we could know if the spin was up or down. Just by looking at how strongly this protein is emitting light, we can know if the reaction went through one branch, the spin up branch, or the spin down branch. And actually, cryptochrome at room temperature is thought to have coherence times of about 1 microsecond, on par with the spin in diamond. The problem is that the next length scales of evidence occurs with like whole birds, whole flies, in ways that are consistent with the spin hypothesis. Birds changing their direction with different magnetic fields, flies not responding to magnetic fields when they have their cryptochrome gene knocked out. Okay, but it's very hard to join those two length scales. So this is what we are doing in our lab. We're trying to bridge those two length scales by doing chemically and quantum sensing inspired experiments inside proteins, inside cells. We're not quite there yet. We're building the instrumentation right now, but basically we are building glorified microscopes with coils. The coils are there to play with the spin, and we want to do this under a microscope. I'm going to just say this: what we want in our group is to know whether quantum physics can either be established or refuted to account for biological phenomena, and importantly, can we manipulate it to technological and therapeutic advantage? If nature is using quantum things to work, it knows damn well how to deal with noise. So can we learn ways to be more resilient to noise with nature? Or can we start driving physiological processes to correct things, to drive physiology in the same way that one would drive the spin in diamond to work for a certain purpose? So that's what we're after in our group. I would just like to thank all those wonderful people who joined the group during a pandemic, a new group in a subject that is to some extent controversial. Thank you for your attention, and I hope to be able to interact with all of you again soon. Thank you.
Thank you so much, Professor Aiello, for the excellent and interesting presentation. We have a little time for Q&A, and not so much really, because we have to start our next presentation. Is there any question that we can answer? Let me see. I think I don't. We can maybe talk about questions later on by email, maybe. But yes. The thing I would like to ask is that do you think one of the you were talking about a quantum scale and then macro scale, so you can sense from quantum to macro? So is this some kind of a multi-scale system you're talking about here?
Yes, in real biology, it's not known how, if this is true, if this mechanism is valid, it's not known how it gets transduced, right? This is not known. It's probably a mess, but yes, the idea is there is evidence that this finicky quantum mechanism of spin up and down that can be altered by magnetic fields, it is causing macroscopic changes at much longer timescales somehow. And the idea would be to try to understand, like, imagine that we had a flip book. Like, if you do a certain thing with your spin, a certain physiological process happens. Or if you do something else, you do something like something else macroscopic happens. You could start thinking about commandeering physiological reactions using the quantum knobs, the endogenous quantum knobs that exist in spins inside proteins, basically.
It's like amplifying the quantum effect to the microscope. Very interesting. Thank
exactly.
you. And then we had earlier one question from Professor Clarence de Silva about quantum actuators. I think you are working more on the sensors, but I think your group at MIT worked on quantum actuators. If you have any comment about that.
Well, that's the question. What do you mean by actuator, right? Because it's something that sensing is also acting on, or what do you mean by?
It's like something that is moving, like electric motor. So can quantum effect cause a motion at macro scale?
Yeah, thank you, Professor Khoshnood and Professor Clarice. That was exactly my question. I can understand an actuator being assisted by quantum tools, quantum technologies, right? But what I was saying is that I cannot imagine an actuator by itself that is quantum in a macro scale. I can understand a micro, I mean, quantum scale, but not in the the conventional classical scale.
But can it be chemical? So
yeah.
Or does it need to be, so chemical actuation is for sure what's probably happening, right? Spin physics is changing chemical reactions that then can have macroscopic effects.
Yeah, but you cannot have like a motor, as Professor Khoshnood said, a conventional, let's say, DC motor with magnetic fields and so on, and can you generate the same effect using quantum technologies?
That's an interesting question. I do not know. I would love to discuss more about that. Let me think. I do not know what my answer would be there.
Yeah, I know that it's a far-fetched kind of a question, but I'm thinking it's not complete, I think, in a sense that quantum cannot address everything in the physical world. That's what I'm thinking.
I agree. And I think that there are still things that might be doing something important at the quantum level that translates to something else. And there's still a lot of things that I don't know, I don't think are discovered yet. I'm interested in those quantum things that might not have been discovered yet.
Yeah, thank you. It was a great presentation. Thank you very much.
I look forward to talking more. And I think Paul has a question.
Well, more just a comment. I mean, I guess certainly the things you're talking about are using quantum superposition states, and you aren't going to get those with a classical motor. So that's certainly true with regard to the previous question. But you could certainly take a bunch of quantum spins and start them all in the ground state, and then you can treat them just like like a classical object, and they could flip them all at once, right? So I think in principle you could do motors with a bunch of quantum spins. It's just that you have the benefit in the classical case because you have just so many of them, so you get much larger enhancements, right? Just like you can do classical computing on a quantum computer if you don't want to do superposition states. It just you don't bother because you already have all the technology built up in the classical case.
So the question is, and I think that's the point so what do you gain by making a quantum system work as a classical motor or something, or getting work out of this quantum system in a classical way?
Oh, that's a perfectly valid question. I was merely just commenting that I think you can do all classical stuff on quantum machines. It's just that you probably shouldn't much of the time.
Yes, yeah, I agree.
We are in violent agreement, as they say.
That's good. That's good. That's rare. That's rare, and that's good.
I'm looking at one of your publications, Professor Aiello, that is called, the title of the publication is time optimal control by a quantum actuator.
Well, again, I think I'm okay. So that publication was about like, if you have a finite set of controls, I think in our case it was, if you have a qubit in the Bloch sphere, right? And you cannot do all 3 rotations around X, around Y, and around Z. I think in our case, we only had around X and around Y. What's the least time consuming way of going from one arbitrary point to another arbitrary point? I think that the actuator in this sense was just like the possibility of the experimenter to apply X and Y rotations at will.
Interesting. Thank you very much. And there's one question in the chat. There is also gravity playing into that. Is there gravity?
Unclear. I know that magnetic field effects sometimes are confounded with gravity effects and also with moon effects on the tides. It's sort of crazy. But since someone talked about gravity, let me tell you, I'll spend 30 seconds talking about something that I think is important. There have been experiments when the absence of tiny magnetic fields, that is, if you grow things inside a hypomagnetic chamber that shields, like, so the magnetic field of the Earth is about 50 microtesla. I have a friend who is a precision measurement physicist who builds hypomagnetic shields, and where inside there's only like nanotesla field. If you grow, in his case, he grew tadpoles. If you grow tadpoles inside just this nanotesla level of magnetic field, the tadpoles are 30% of them are macroscopically like deformed. Given the strength of magnetic fields involved and the fact that people do not know about big magnetite crystals inside those embryos, the best guess is that such alterations in embryo physiology, they have to do with spins. Okay. Hence the question, if you want, for example, to colonize Mars, right? What's the magnetic field in Mars? Can we reproduce in Mars? Can we grow lettuce in Mars? So I think this whole spin physics in biology thingy is super important for many, many things. And what we hope is to bring like all the techniques from technological quantum sensing and start applying those techniques directly onto those spins in proteins as if they were, because we think they are, bona fide quantum sensors. And we think there's a lot of wealth to be learned from that.
Thank you very much.
Hey, Farbod, this is Marco. Can I make a comment? Perhaps an example of a quantum actuator is a light-induced optical tweezer, because radiation pressure is a macroscopic manifestation of electromagnetism, right? And it's used very frequently to guide and move and align molecules and macromolecules. So perhaps that is an example of a actuator with an attribute of quantum, perhaps not an electric motor like a DC or AC motor, but I've worked with that before and it goes pretty close.
Yeah, and what about laser cooling?
Same thing, yes.
Okay.
Indirect effect of laser trapping, so.
Right.
Thank you.
And by the way, both laser cooling and trapping and optical tweezers, they've been used for in a regime where with very low level disturbances, like in space applications, for example. Not to speak of atomic clocks and other ion trap devices that leverage that mechanism. Just a comment.
Thank you very much. There's also another comment that you can use spin effects to exert a force in a specific direction. If you can exert a force, you can spin a motor. This is from one of the participants in the chat. And David Chester, Dr. David Chester mentioned something about gravity. If you like to add something to that before we move to the next section.
I was just a very brief comment. I was just mentioning that a lot of experimental chemistry, there is maybe about 5% error in a lot of cases of measurements that are being done. And it does appear that when you look at quantum gravity effects, maybe part of the reason why we don't understand precisely some of these discrepancies in experiment could be there's possibility that quantum gravity affecting chemistry through spin could come into play for some of just explaining some of the discrepancies. But obviously, carrying out these calculations is very difficult. So for sure, that's all I really have to say.
How strong would be the effect? It's something that people could measure?
I'll have to try to find the work again. Let me search for the work I have in mind, and then I can share something.
But that's exciting. That's very, very cool.
Thank you.
Oh, and just as another thing, for example, there is someone here at UCLA who's using quantum sensors to find signatures of dark matter and things like this. So there are many uses for quantum sensors in general.
Thank you so much, Professor Aiello. That was an excellent presentation, very interesting. I'm sorry, Professor Enrique Galvez, that we are a little bit behind the schedule. It's my really great pleasure and honor to introduce Professor Enrique Galvez. I have to say that I really have to thank Professor Galvez, I'm very grateful to him because I've learned a lot from, I'm a mechanical engineer, and everything that we learn and everything we have done in our lab in terms of quantum entanglement experiment, I've learned from Professor Galvez, and I'm very thankful to him. I would like to introduce Professor Galvez. He obtained a PhD in physics from University of Notre Dame, Indiana in 1986. He has been a member of the faculty at Colgate University since 1988. Currently, the Charles Dana Professor of Physics and Astronomy. His research interests include atomic and optical physics and physics education. Recent research projects include the study of light in complex scalar vector modes and photon entanglement. Educational projects include modernizing the introductory physics curriculum and the development new laboratories to teach about light and quantum mechanics. He's a fellow of OSA and has received 2 APS awards. Professor Galvez's talk is on photon quantum mechanics and education. The abstract is technological advances in the production and detection of single photons has opened new opportunities for teaching the fundamentals of quantum mechanics via hands-on laboratories. The rise of quantum information has only understood the need for students to confront the counterintuitive aspects of quantum physics and their contrast with classical physics. The future workforce needs to understand these concepts deeply along with the quantum formalism and statistics. Photon laboratories provide a platform for understanding both the fundamental concepts and their application to physical systems. It's my great pleasure and honor to welcome Professor Galvez.
Okay, can you hear me now?
Yes, we can.
Yes, okay. So thank you, Prabhat, for the kind invitation and for letting me share my work with everybody. This is a little bit off the mainstream of this workshop. I'm not going to be really talking about new developments in research, but really about how we use the fundamentals of all the many processes that have been already discussed today to teach about quantum mechanics. So this work has been done at Colgate University, and we started really some time ago about, well, our first grant was in 1999. And I have to say that we got encouraged to get into this project by Paul Kwiat, and then we had some collaborations with Mark Beck. But then over the years, we had a lot of students work on this project, and then
Professor Galvez, I think we cannot hear you. Professor Galvez, we cannot hear you. Are you muted? I think it's frozen. I think Prof. Galvez got disconnected. You're muted.
sorry about that. So let me share the screen again. Okay. And let me see. Can you hear me?
Yes.
Can you hear me?
Yes, we can hear you.
Okay, I apologize. I don't know what the problem is. Okay, so I just want to acknowledge many students that have been involved with this project. Now, I don't know what part you didn't hear. This was done at Colgate University, which is a small college in central New York. I just want to acknowledge that Paul Kwiat actually got us started in this work. And then this work has been funded by National Science Foundation, both the Division of Undergraduate Education and also physics grants. National Science Foundation has this broader impacts, and then we use broader impacts to develop these educational activities. So we have, I'm going to give you a little bit of an introduction and tell you a little bit about 3 types of experiments. And so just so you can get a flavor for what we're after. We need to prepare a workforce with quantum technologies, and Photon Labs is one way. We have all these emerging technologies that rely on superposition and entanglement, and we've heard about many of them today. And so my approach has been to develop these laboratories with single photons. And I claim that it is a convenient teaching platform. They address quantum fundamentals, quantum mechanical fundamentals live, that is, students actually do an experiment. And the experiments highlight counterintuitive concepts, and we can focus on some applications. I'll show you one on quantum key distribution. And then we use a source of photon pairs, and 2 photons can be convenient qubits, and we can use polarization, linear momentum, and so on to say encode the qubits of these photons. And the equipment costs are inexpensive. You'll see how expensive they are, but they're not outrageously expensive. And the experiments are tabletop, and this type of experiments work very well with the advanced lab. So I really developed them for physics, but there's no reason why they could be introduced into engineering. And there have been various sources of funding, of course, NSF, but then this Society Advanced Laboratory Physics Association, they provides workshops. In fact, I run yearly workshops, and this year I am running a workshop in a few weeks on how to do these experiments. That is to teach faculty or perhaps lab instructors how they, what do they need to know to set the experiments in their institution. And then also there's the Jonathan Reichert Foundation that also provides funds for small grants, just what you need, $10,000 or so to set up the lab. And of course, there are other initiatives to let's say rethink how we teach quantum mechanics. There's new textbooks, there's new approaches in the physics education literature, and also a lot of ideas for introducing quantum physics in high school and get them started early. And so about our platform, so we use twin photons created simultaneously by spontaneous parametric down conversion, and then various talks, certainly Paul and others have talked about these sorts of photon pairs. Okay, and then they have correlated properties of energy, momentum, polarization, spatial mode. Alan Willner talked about that. And then there are two types of experiments. There are single photon experiments where they're called heralded photon experiments, where one photon heralds the presence of the other one that does something in the apparatus. And and then there's various, one is that the photon exists. I'll say something about that, and then I'll talk about interference here and delay choice. And then there's experiments where both photons play a role together, and sometimes they're called biphotons. And you can think of the two quanta of light behave as one. And so I'll tell you a little bit about entanglement, but I won't tell you much more about other two photon interference experiments. And then I'll tell you a little bit about an application with quantum key distribution. Okay, so at the heart of this source is the production of pairs of photons. So I'm going to apologize to the experts because this is very basic stuff, but I want to perhaps give an introduction for those who don't know about this. And anyway, so this source produces two photons from one. It's inefficient, but also we don't want too many photons because we want to detect one photon at a time. And the energy is conserved and momentum is conserved. And depending on how you do an experiment, you can have some form of energy entanglement and some form of momentum entanglement. You could even reproduce the famous EPR experiments. Some people have done that. And so then, because of conservation of momentum, the photons come forming a cone, and photons that are opposite to the center of the cone are the partners. And of course, if the photons have the same energy, they come out at equal angles. Okay, but now this is something important, and it is that this process, spontaneous parametric down conversion, is robust. Once the crystal is aligned, photons come up, and you can do an experiment. And you don't have to start all over if the alignment is not touched. And but there's a challenge in the initial alignment, and then that's what the workshops that I run and others too entail, which is to show people how to do the alignments. Let me give you a flavor for what is the basic apparatus. So we start with a laser, and then there are various levels of sophistication. This is a laser that has temperature control, but you can go with just current control, or you can go even with very modest current control with a laser pointer, and the prices go, you can see there. We've done experiments with $20 laser pointers, but more reliable are slightly more expensive lasers. And then very convenient for these experiments is that to have a short wavelength laser, and then very widely available is this one at 405 nanometers. Okay, so our laser comes here and hits a crystal, and nowadays this technology is well known, and so then you want to adopt this, you can actually buy off the shelf the crystals that are needed for these type of experiments. And then here you can see in red, one photon goes to be detected, to be collimated and then detected, and then another one goes through some interferometer, and then the light coming out of the interferometer eventually goes to be detected. And then this is a picture of a breadboard. You don't need an optical table. If you do the if you use pedestal mounts and certain type of optical equipment, vibrations are not an issue. And then one bottleneck is that the detectors are somewhat expensive. They're single photon detectors. And but then once you detect the photons, then you can record the pulses that come from the detectors, and especially record the coincidences, because we want to detect both photons, which is a way to get a single photon effect. Let's put it that way. And then that's a more recent incarnation. They use FPGAs, and then you control that with a computer. And then, for example, an interferometer can look like that. And so let me mention then one bit of fundamental physics about quantum interference. And then this was very succinctly and clearly laid out by Richard Feynman. And that is that the following, that if an event can occur in two or more indistinguishable ways, then the probability of the outcome is the square of the sum of the amplitudes for each case. And what is important here is this word indistinguishable. And then that becomes relevant really in all of quantum information, that whenever we think about when do we have quantum superposition or quantum interference, and that is when these two possibilities are indistinguishable. When that happens, you add the amplitudes. Sometimes the amplitudes have a phase relation between them. And so then the square of the sum of the amplitudes produces interference. And you can get that the probability is 1 or 0 or somewhere in between. Now, if the possibilities are distinguishable, then there's no interference. And then the probability is constant. And I have to admit that here there's a bit of a mystery in that distinguishable or indistinguishable is inherently. It's not that we're not looking or that our apparatus is somewhat defective. No, it's that it is impossible by physical means to distinguish the two possibilities. And so these are the kind of things that are important for students to understand, to have a basic foundation of quantum physics, and then from then on, quantum information. So for example, if we look at interference of light, so we have an interferometer, we've seen those before in this conference. So then if the arms are nearly the same length and no distinguishable features, then the probability of the photon going from A to B is a superposition of the photon going through both paths. So that's, you do the calculations, that's the probability, where delta depends on the path length difference. It's a phase. And but if the paths are distinguishable, then the probability in going from I to B is 1/2. Now, we can also think of this from a different point of view, perhaps in the language of qubits. And we could say that light going along the x directions with momentum along the x-axis is represented by this ket x, and going along the y direction is y. So then that's our qubit, light going in these two directions. And then light going through the interferometer then needs to go through a beam splitter. And then the beam splitter now in the language of quantum mechanics is an operator, and then the mirror does its action via this operator, and then we have a phase, and then going through interferometer, quantum mechanics wise, you is a product of these operations done on the state of the photon, and then when you want to calculate the probability, you get, of course, the same answer. And then this is the kind of things that we do in now this is a quantum mechanics class for physics majors. And now we go to the lab then to do the experiment, and we know the answer there. Well, that's the probability of going all the way to B. And then we change the path length by slightly moving the mirror, one of the mirrors, with a piezoelectric. And so then here you have as a function of the voltage applied to the piezoelectric. And then, then we measure coincidences between A and B. And then we see that as we change the path length, of course, we get constructive and destructive interference. And then we can ask the students, well, if delta is pi, so we have a minimum in interference, well, where does the energy go? What happened to the photons? And of course, the answer is, if they don't go to B, they go to C. And then the probability in going to C has a minus sign. So then you measure the coincidences between A and C, and then you get, of course, the opposite fringes. And then I always like to put this quote from Dirac that that becomes really striking, and it almost rocks your understanding of what nature is, which is we think of photons being a thing, and now the photon goes through interferometer and interferes with itself going through the two paths. And now something else. So think about that at this voltage. You have some photons going to B, some photons going to C. They're not the same photons. But so if we were to try to get the triple coincidence, we get 0 because they're not the same photons. So the light goes through interferometer as a wave, but is detected in B or C as a whole thing. And then we could get more strict about this and calculate something that's called the degree of second order coherence. And it has to do with a triple coincidence. And now this is, and it's called the G2. And then these are the results from a student lab report. And then you can see if we use a coherent source like a laser mimics a classical wave. So we get coincidences between B and C. And so this G factor is 1. But if we use photons, then the photon comes either to B or to C. So the G2 is 0. So what the students get here is nearly 0. And now what if we make the paths distinguishable? So here we can make them distinguishable in polarization. So we pick horizontal and vertical polarization in this experiment called the quantum eraser. And so what we end up doing is the following. The photons created by the source produce vertically polarized photons. And so we know what the answer is. Probability is given by that equation. We take the data and we see the fringes that similar to the ones that I just showed. But now if we rotate the half-wave plate at the top so that it rotates the polarization by 90 degrees, then the paths become distinguishable by the polarization. and we don't get any interference. And but then comes the quantum eraser, which is we put a polarizer after the interferometer, oriented at 45 degrees. So it projects the two polarizations, vertical and horizontal, along the diagonal. And so then after that, there's no distinguishing information about which path the light took, and we recover the interference. And now this experiment also is interesting because it works in a counterintuitive way in that we do the erasing after the light goes through the interferometer. And then we published this a while ago. And but then we asked the students, so the information was erased, right? Well, we put the eraser on the path that goes to B. Well, what happened to the path that goes to C? There's no interference on the path that goes to C. So here's something striking that is also central to quantum information, and is that interference is about the information that is available. So going towards B, there's no path information, so there's interference. But going to C, there is path information, so there's no interference. Now, those of you who are optics experts will say, of course, light polarizations that are orthogonal, they can't cancel each other. But we're talking about single photons. Okay, so let me tell you about this other experiment. So we detect the photons. Okay, the photons are produced broadband, that is in a wide range of energies, and then we put filters and irises in front of the fibers that collect the photons. So we don't know their energy to within some let's say factor, a curve specified by the filter and the iris. So this, not knowing what the energy of the photons are, is we get a superposition. And so then the photons that are detected are in a wave packet. So let's think about this. So we have a distribution of wavelengths. So we can think then the Fourier transform of that is that it's like, these are not pulses, but it's like that photons have a finite extent, or finite coherent extent, given by that, where delta t is the coherence length, and L sub c is the delta t is the coherence time, and L sub c is the coherence length. So if we have a wide bandwidth, we have a short coherence length, and if we have a narrow bandwidth, we have a long coherent length. So let's do this experiment, thinking in those terms. Okay, now I'm just telling you just one way of thinking about it, but you may think of different ways to explain this experiment. But think about this. We have our wave packet going through the two arms of the interferometer. So if the difference in length is less than the coherence length, then they do not get delayed enough, so we don't know from which path the wave packet took. But if the difference in path length is greater than the coherence length, then the two arms are distinguishable, because in principle, we could time the arrival of the photons and obtain which path they took. Okay, so how about this? We send the light through an interferometer. Now, this experiment idea was originally reported by Kwiat et al. In '92. And so we have filters before the detectors of both photons, and then the filters are 40 nanometers in width, which correspond to a coherence length of 16 micrometers. So suppose we align the interferometer to get a path length of 8 micrometers. So we get some interference. And here I'm mimicking, this is not a simulation, this is just a picture just to try to visualize coherence length and the difference in length of the two arms. Okay, but we can characterize of course, the degree of interference by the visibility, which is how big the fringes are. So in this case, the visibility is 0.94. And but now we increase the length of one of the arms by a good chunk to a path length difference of 28 micrometers. So then there's less overlap, think of it, of the wave packets coming out of the interferometer, and so the visibility goes down. Now it's 0.45. We keep going, and it's 0.16. We keep going way beyond the coherence length, and all of a sudden the visibility is nearly zero. So now what can we do? We can change the coherence length by putting a narrow filter. And so then we do that, but then we do this, that again, this is what Paul had reported way back, and that is you put the filter on the other photon going through the interferometer, and then you recover the interference. Okay, and now let me take this to a further extreme. Okay, and that is a modality of experiments called delayed choice. So this is what we do. We send the photon through interferometer. It comes out. It gets measured by the detector, and immediately after interferometer. But then the other photon we send through a 20-meter fiber, and then through the filter that determines the coherence length of the wave packet. And but this is, by the time the light, this photon goes through this filter, this other photon no longer exists. Okay, and so then this is this is interference with the long wide bandwidth, short coherence, short difference in path length, and then here is same bandwidth, but now really long difference in path length, so no interference. And now here we put the narrow bandwidth in 1 nanometer, but on the other arm, and after the other photon going through interferometer has been detected, which produces, of course, an incredible mind twister. And then let me see, and then here's a picture of the apparatus, and so this really rocks your understanding. What just happened? Well, the choice of filter decides whether the photon acts as a particle or a wave. Again, this is one way of thinking about the experiment, but this choice is done by the idler photon after a signal photon has been detected, and it is not action into the past, right? And that is somewhat, I have been somewhat misleading you and to think that the photons are independent, but they're entangled in energy. And so when we do a measurement, we do a measurement on both photons, and you can also think that then the information wave or particle is in the coincidences, and so by recording the coincidences, we can determine whether there's interference or not. Okay, and so this type of experiments that are kind of shock you are good for students to just think more deeply about these concepts. Now, John Wheeler, who proposed the late choice type experiments, says no phenomenon is a phenomenon until it is an observed phenomenon. Really, what happens is quantum mechanics gives you probabilities. Okay, now it is us who are making this pictures in our heads about what is happening, but quantum mechanics is not telling us that. It's telling us what is the probability of detection according to our experiment. And then that's something to keep much in mind. Okay, So let me tell you a little bit about entanglement. And then this is a source of, again, our towering figure, Paul Kwiat designed this source. You put two crystals, and then each crystal produces pairs of photons that are of one kind of polarization. One crystal produces horizontally polarized photons, and the other crystal produces vertically polarized photons. And then we get two rings if we send a pump photon that is at 45 degrees, which has a component horizontal and another one vertical. So we get pairs of photons that in one ring, they're vertically polarized, and the other ring, they're horizontally polarized. But now, if we tilt the crystals right, we can make those two cones overlap. And then it becomes inherently unknowable from what crystal those pairs were created. And because of that, then we create an entangled state, which would be a superposition of both photons horizontal with both photons vertical. And then that's our entanglement. Our entangled state, which was first, the idea was given, and the name was given first by Schrödinger in a 1935 paper. Then quantum entanglement has very interesting consequences. Realism, non-locality, contextuality, and those are all interesting concepts to think about. And they force you to think about because you're doing an experiment on those. And so the important thing to point out is then that making this state is being both horizontal and both vertical at the same time, and not half the time horizontal and half the time vertical. And of course, Einstein didn't like the fact that you could determine what happens to the other photon by measuring on the first photon and called it spooky action at distance. But then we could mimic the two situations, entangled versus the other one mixed, which is horizontal half the time, vertical the other half the time. And by doing a type of experiment where you send the photons to polarizers, and if they're in an entangled state, you get this function, which we can measure. But if they're in a mixed state, you get a constant value, and you can measure that. Okay, and I'm not going to give too much details of that because of time, but then look at the setup that we have here. Okay, so let me see, keep going. So we decided a while ago to see if we can come up with something more related to applications, and that would be quantum key distribution. And at the heart of quantum key distribution is that the act of measurement inherently modifies the state of the system. And another thing is that the quantum states cannot be cloned. And so, for example, if your initial state is an eigenstate of the measuring device, so think about this, some piece of calcite that deflects, that does not deflect vertical, but deflects horizontal. So if you're in one of the eigenstates of the device, then you get an outcome with probability 1. But if you have as initial state a state that is not one of the eigenstates of the measuring device, then you'll get vertical half the time, and or with probability 1/2, or horizontal with probability 1/2. And the same thing with the other diagonal. And this is a nice quote that I like about from Dirac, that when a photon is in a superposition, when a photon in a superposition is measured, the photon has to make a sudden jump from being partly in each of these two states to being entirely in one or the other of them. And then that's really at the heart of quantum key distribution in this protocol of Bennett-Brassard, 1984. So the idea is something like this, that Alice sends photons to Bob in either of two bases, vertical, horizontal, or diagonal, anti-diagonal. And then Bob measures in those two bases. If Bob uses the same basis as Alice, he gets the same result. But if Eve, an eavesdropper, is in between and measures and resends the photon in the wrong basis, then Bob and Alice may not get the same answers, and then they'll get errors. That's the basic essence of this protocol for quantum distribution. So this is what we did. We created entangled photons, and that they remain parallel to each other in both the horizontal vertical basis and diagonal anti-diagonal basis. And so then the source, one photon goes to Alice and another photon goes to Bob. And then Alice measures in one of the two bases, Bob measures in one of the two bases. And now we need to insert Eve. So we can do this very well. Alice measures in two bases. You can use a polarizing beam splitter. Same thing with Bob. But then how do we do detect and resend? Because Eve is intercepting and then resending the same photon so that Bob doesn't know that she intercepted the photon. So what we do is we mimic Eve with a dephasing optical element, which is basically a thick birefringent element that dephases the horizontal and the vertical in such a way that then they become incoherent. And so that's the idea. And when we thought we were so smart figuring this out, we found that there's a paper that already did it, of course. Who did it? Paul Kwiat. Okay, so and then this is a little bit of a picture of the apparatus, the laser, the crystals to produce the entangled state, and then here the detections from Alice and Bob, and by so we have a Thomson prism that splits the light by polarization. We have half-wave plates so that Bob and Alice can decide whether to detect in the horizontal vertical basis or the diagonal and the diagonal. And then here's Eve, which is basically a thick quartz plate. And then here's the apparatus, and there's some details there. Probably I should keep moving, but as you can see, it's not a terribly complicated apparatus. Okay, and then here are some results. If Eve is in the same basis of Bob as Bob and Alice and Bob always agree. And this is just a sample of, just to give you a flavor. And if they're all three are in the diagonal basis, we get some errors because our entangled state is not perfect. And so in theory, they should agree 100% of the time. In our experiment, they agree 92% of the time. But now, if Eve is not in the same basis as Alice and Bob, then you start to get errors. That is, Alice and Bob, when they do their measurements, they're not the same. And so the theory says that they should disagree 25% of the time, and we get about 28% of the time. So, another thing that we did that another way to think also more deeply about the entangled state is to actually measure the state. And you can measure the state via what is called the density matrix. That's that. It's just a matrix that tells us what is the state of the light. And then one way to represent the density matrix pictorially is to plot as columns the values of the elements of the matrix. And then this is the density matrix for the entangled state. And this is measured, okay? But now if you put Eve in there, which dephases the horizontal and vertical components, then it mimics the situation where half the time both photons are horizontal, half the time both photons are vertical, which is a mixed state. And then that's a measurement of the density matrix, and this is the predicted value. And so we also did other measurements. Once you have the density matrix, you can calculate other things, other quantities that tell you how good your state is, how entangled it is. You have the tangle, and which without Eve is 90.96. With Eve is essentially 0, and you have the von Neumann entropy, linear entropy, and so on. And so all that came out very nice. So let me say something about our most recent adventure, and it has been in doing remote labs. Of course, because of COVID, we couldn't do a lab. Okay, so we have a course on quantum mechanics that has a lab, and students, when we do it in person, we have 3 setups. So over the years, we built the equipment for 3 setups, and so students build everything from scratch, and they take 1 to 2 weeks to set up the experiment, and the 3rd week they actually do the experiment. And but of course, when we had to shut down due to COVID, we couldn't do the experiment in person, so we resorted to automize the apparatus. So here's a picture of the setup now for remote control. So we use Arduino and some little tricks to via the desktop turn on the laser. Actually, in this case, we turn on the laser, but in some other case we have blocked it or unblocked it, and also the detectors. Okay, and then we need to do these polarization experiments. You need to detect the photons by projecting them at different polarization angles. We don't use polarizers. We use fixed polarizers and rotate half-wave plates in front of the polarizers, but basically it's the same thing as rotating polarizer. And we can control those also via the computer. And then the other thing is, in the experiments, we can produce a mixed state. Guess how? With a quartz plate. So we can insert a quartz plate in the path of one of the photons, and then that dephases the entangled state and becomes a mixed state. And then, so you can control that through the serial port. And then we have, we use MATLAB to take the data. That's an example of the data. And then we also have a webcam so that students can see the apparatus, and then the students log in. Okay, so this is what students do, and this is what they did this semester. Let's see how my time is doing. Okay, I'll finish in time. The students, well, first they get a long write-up that they have to read, and then they have to decide what they're going to measure. Okay, then actually, let me backtrack. We set up the apparatus with one group of students. We've had as many as 15 students, but to align this thing that you see in front of you, we need 3 students, no more. And then they follow instructions, then they align it. And then the virtue of that is that they get to do experiments on something that they created. It started with a blank breadboard. Okay, now the students, after everything is aligned, the instructor might make a couple of tweaks to beautify things. And they meet by Zoom. And then one of the students logs into the desktop in the lab by remote desktop, and then they do the lab, and then they've done beautifully. And anyway, and then down here, I'm giving you examples of the results that they get. That one of the things that they have to do is that do a measurement of Bell's inequality, and the S parameter of Bell's inequality that they get is 2.67. And if it is greater than 2, it corresponds to a violation of Bell inequality. And then when you put in the quartz plate and you produce a mixed state, the value of S now drops to 1.35. The calculated value is 1.42, so it's not too far from what it should be. And we reported some of this remote experiments in recent proceedings of SPA. So I'm winding down. Let's see. Okay, so what else? I have not mentioned spatial modes. Alan Willner mentioned them. Something striking to think about is that photons occupy the entire mode, and that's Alan mentioned that. And it's fascinating to think about. And when we have a double slit experiment, and you see an interference pattern in the screen, let's see in the camera, the dots that you see are the pixels, not the photons. The photons occupy the entire screen, and then you have photon detectors, which would be just the pixels, and that's quantum for you. Then we have I haven't told you about biphoton interference, and a workhorse of quantum optics, quantum information is the Hung OU Migdall interferometer. But that's, of course, research groups can set it up in no time. But I'm thinking in terms of, can students align a Hung OU Migdall interferometer in 1 or 2 afternoons? And the answer so far is no. So I'm just recently with the grant, I got a pre-aligned beam splitter, a Hung OU Migdall, which was described by Paul Kwiat, has a beam splitter, and you just have to have the beams exactly overlap. So what I got was with optical fibers and so on. Okay, but I have some hope that maybe with that we can make a feasible Hung OU Migdall lab experience. Now, the other thing is that we could do in principle, what did I do? We could do in principle qubit operations, and for example, the half-wave plate can be a Z gate, an X gate, a Hadamard gate. So the only other piece that we need is a CNOT gate, which I'm working on it. It's not easy because we need, as far as I can tell, perhaps Paul can comment. I think we need 2 pairs of photons. But maybe there's a way around it. So anyway, so that's a little picture of the lab. You can see 3 breadboards and the group of students. We have a website that has lots of information, manuals of how to align things, parts, prices for all the equipment. And anyway, thank you very much for your attention.
Thank you so much, Professor Galvez. That was an excellent presentation. And as I said, I've learned a lot from you, and your workshop is very helpful for anybody who is interested to learn more. And there's a lot of good material on your website that I've used myself and others can use to learn how to set up their experiments. Thank you so much. And I have a video of your running your remote experiment, which I would like to show everyone later during the day. If I check the time, we have a remote hands-on, which I would like to show you the video at 4:30. So that video that you are doing a remote experiment. Thank you so much. There is one question that is, how difficult is it to align the Kwiat crystal versus the BBO type 1?
Well, okay. Well, Paul invented both methods. One is a type 2, which for me is hard to align. And a type 1, if you have just one big type 1 crystal, it doesn't produce entangled photons, but it is not difficult to align. Now, let me say this. That's why I run a workshop, because you can't see the photons. They're infrared and they're too weak. And so I use an alignment laser. So I line all the optics with an alignment laser. And I had a whole bunch of just in case slides, but I use an alignment laser to mimic the paths of the photons. And so there is a difficulty in the initial alignment, but then once the crystal is in place, then things are good. Now, for entangled photons, there's additional considerations, but then there's lots of information available, so it should not be too hard. I saw Paul raising his hand at some point.
Well, I did, just because I had sent a quick message to the person in the chat, so I tried to answer some of the questions. I guess I'll just say that yeah, the type 2 source is a real pain. I mean, it's not so bad if you don't want entanglement, but it's a pain if you want entanglement, because you only get it in a set of measures 0. It's only over that particular intersection between the two cones, and that's not easy to find. And you can have coincidences and yet not be at that spot, and you don't know which way to go, and and the colors could be different. It's just hard. If you do it with the type 1 crystals, you know, you put them together, and when they're in the mount, the nice thing is that when you tip about one axis, you'll change the opening angle of one of the cones and not really the other one. And so you just you can set the polarization so you know you're only collecting from one crystal. You tip that crystal until you go into your irises. And I agree, it's nice if you have alignment lasers, that makes life easier. And then you just do the other crystal by tipping it about the other axis. And that gets you, that gets you pretty close. And then you can do a little bit of walking in. I think the main thing that's a little tricky is you won't necessarily get, for example, HH plus VV. You'll get HH plus E to the I. Well, okay, then you have to do some temporal compensation. So you have to put in another crystal, but you just need to know you need to do that, and then you plop it in, and then it kind of works with the right thickness. And then, but you could still get a different phase. And so you just have to, do some measurement of that to figure out what that phase is. And it's easy to fix. With a lot of different ways with a liquid crystal by tipping a wave plate. I mean, there's a lot of ways of doing it. It's just that when you first set it up, you could get unlucky and you could get like HH plus IVV. And then when you measure in the diagonal basis, you're not going to see any fringes. It's going to look like you didn't do a good job, and yet you could have a perfectly entangled state. So what we typically do is we do a quantum state tomography where you have to measure in the HV basis, in the diagonal basis, and the left-right circular basis, and then that tells you everything. It tells you how pure the state is, and on our webpage we have a full tomography code, so you can just go and enter data in, and it'll tell you what the density matrix is and what the error bars are on the fidelity and things like that. So yeah, the first time you do it, it's not so easy if you're not used to using single photons, because it's hard to align things you can't see. I'll just say one other quick trick that I'm sure you also use, Kiko, is it's very helpful on your detector side. If you're going into fiber, it's very helpful to have like a patch cable so that you can send your laser backwards through the fiber. So it basically comes out of the detector through the coupling lens, and then you just see, is it going in the right place onto the crystal where the pump laser is going the other way. And once you get those things aligned, you kind of have to, you have to be getting counts at that stage, unless something is very wrong, and that helps a lot. Going backwards is always a pretty helpful. It's kind of counterintuitive, but anyway, for people who've done this for a while, it's definitely an extremely quick way to get things aligned sometimes by being able to go backwards. Okay, I'll shut up.
No, yeah, you showed all the tricks. Actually, for getting the right sign of the entangled state, what works really fine is if you put detective pairs in diagonal and anti-diagonal. So your coincidence should be 0, and then there's a little quartz plate before the quartz plate that does some compensation before that 2 BBOs. By tilting that one, eventually you get the minimum.
Yep.
Which of course you know that.
Yeah, no, of course. This is this conversation. Everything I'm saying, you also know. This conversation isn't for you, Kiko. It's for other people who might be trying to do it. It really isn't. It isn't that hard. I mean, we do this in undergraduate labs. I know a high school in that has done it. They do it. It's one of these like science magnet schools or something, but they do it as part of their project to do entanglement. Now they were also trying to do like teleportation, and that's much harder. That's a much harder experiment to do.
I have a question about the same thing. When you have a polarizing beam splitter, when you're shining the light backwards to a line, if you rotate the polarizing beam splitter from the vertical side when there's reflecting the light, how do we make sure that that polarizing beam splitter is also in the right angle? Exactly.
Kiko, you can also answer this, but I'm not sure which. In general, we never try to rotate polarizing beam splitters. That's almost always a bad idea because the reflected port, then the beam goes in some totally different direction, and then you don't get to hit anything, right? So I would typically always try to do things with a halfway plate afterward to effectively rotate it.
Sure. Thank you so much, Professor. Thank you. Thank you so much, Professor Galvez, for the excellent presentation. We are a little bit behind the schedule. Thank you for the excellent presentation. We need to move to the next presentation by Dr. Alan Migdall. I'm sorry, Dr. Migdall, that we are a little bit late. It's my great pleasure and honor to introduce Dr. Alan Migdall. Dr. Migdall's current interests broadly cover quantum optics with research related to single photon source processors and quantum memory for quantum cryptography and quantum computation. Specific efforts involve correlated 2-photon light, nonlinear optics, parametric down conversion, Raman scattering, microstructure fibers, multi-particle entanglement, randomness generation, and classical and quantum metrology. And Migdall leads the quantum optics group of the Quantum Measurement Division at NIST. He is the fellow of the Joint Quantum Institute at the University of Maryland and fellow of American Physical Society. He has organized a number of conferences and workshops on single photon detector and source technologies, as well as the application of metrology of that technology. He founded the Single Photon Workshop, which debuted at NIST in Gettysburg in 2003 and has continued biannually at metrology and national labs in the US and around the world. He was editor of the book entitled Single Photon Generation and Detection. Migdall has been part of a number of science outreach efforts, including the OSA Eastman Presidential Speaker Program, giving lectures at numerous universities and colleges, as well as local high schools, middle schools, and elementary schools. He has provided research opportunities for graduate, undergraduate, and high school students. In addition, he was the science advisor for a National Academy of Sciences Middle School Optics curriculum program. Migdall began his career at NIST with an NRC postdoctoral fellowship in laser cooling and trapping of neutral atoms, was made a fellow of American Physical Society in 2007, awarded the NIST Bronze Medal in 2009 for his efforts in single photon technology. In 2013 and 2015, awarded patents related to single photon technology, and in 2016 was part of the team that was awarded a Commons Department Gold Medal for long sought goal of achieving a very strong test, rejecting local realistic models as possible alternatives to quantum mechanics. Dr. Migdall's talk has two parts. The first part is on the quantum age measurement for all time, for all people. And the second part is multiplexing a path to an ideal single photon source. It's my great pleasure and honor to welcome Dr. Migdall.
Well, thank you for the very nice introduction, and we'll see how this goes. There may be some background noise. We're in the middle of a emergence of a 17-year cicada brood, and it can be quite loud even inside. We'll see. So, like you just heard, my talk is actually two separate talks. I made the mistake of saying, would you like this talk or that talk? And the answer came back, oh, you should do both. So the first talk is talking about the quantum age and measurements for all times and all people. And before I begin, I'd just like to highlight where we are. We are at NIST, the National Institute of Standards and Technology, which is the metrology lab for the US. But we also have a footprint at the University of Maryland at this Joint Quantum Institute. And just in follow-up to the previous talk, up in the upper right-hand corner is actually what it looks like for looking down a cone of parametric down conversion produced light. And these rainbow colors are all photons produced two at a time. So let's begin here. And as a metrologist, it's always good to define your terms. And I want to define what metrology is because not everybody knows. It's the study of measurement. And I will try to share my joy of measurement in this talk. What I'm going to talk about is why we measure stuff, how we measure it, the problems with measurement, but it's also a story of human civilization as a whole and how measurement was actually crucial for the development of civilization. And then I will move on to a grand idea to actually unite all the peoples of the world in a common language. And I will argue that that common language is not even limited to Earth, it goes beyond, and how quantum enabled that dream. And the point of such a slide like I'm just showing is one of those to get across the idea of why people should be interested in what you're talking about. In this case, it's because it's critical to everything we hold dear to us, as I hope you will see. And I don't know whether you paid attention to it, but 2 years ago, actually 2 years ago, plus 5 days, 6 days, was World Metrology Day. And what happened on that day 2 years ago was actually the greatest revolution in measurement since the French Revolution. And I will explain that. And it was actually, oh, wait, it went away. The dawn of a new age. Are you still able to see my slides?
Yes, we can see.
Okay. Okay.
Is
so,
there a video?
No, I think we're good here. So I want to step back at the basis of our measurement system. We use the metric system, but it's based in what's known as the System International, the SI, and that consists of 7 base units. And in the corner here is one that presumably people have all heard about, the kilogram. This is an artifact standard that sits in a vault outside of Paris. And that revolution that happened 2 years ago essentially eliminated this artifact and based now all of the standards in terms of defined fundamental constants. That's what's intended to be indicated here. And to explain this, let me start with a story of metrology. This is a story that starts more than 150 years ago when there was a need for a standard of light for the gas industry. And what they decided on was a candle made of a particular substance that comes from a whale. But as they developed this standard, they knew that this was really not the best of sources in terms of stability or long-term stability, or not to mention the problem of would they always be able to get the same material and would it be the same over time? So what they decided they needed really was an electric candle. And that electric candle is based around something that you've probably seen. If you look at the light coming out of a kiln, you see this characteristic red glow. And if you notice carefully, you'll see that the image you see is a bit indistinct. And in fact, if you were to close up this hole and actually only peek in through a small port, it would become even more diffuse and indistinct. And what Kirchhoff noted was that such a cavity appeared to be only dependent on the temperature and independent of what you made this device of. That's something that a metrologist gets very excited about. So you're able to make something that makes a uniform output and a stable output and doesn't depend on what you make, what you make it of. And that's in fact what we call a black body. So it's a device with a cavity, a small hole. It's all heated to a uniform temperature, and it spits out spectral radiance, which is optical power per area, per solid angle, per bandwidth. And this is something that started to be measured carefully 125 years ago or so. And what you see are curves shown here. This is, if we look at the lowest curve here at 700 degrees, this is the optical power as a function of spectral wavelength. So this is going from 1 micron to 6 microns. So this is all in the infrared. And what you notice is that as the temperature of the black body gets higher, the peak moves to shorter wavelengths. And here at 1600 degrees, it peaks below 2 microns. And if you go to 5,000 or so, which is effectively the temperature of the surface of the sun, that will peak in the visible. And these people in the metrology lab in Germany made careful measurements, and it looks pretty good. But if you actually look more carefully, you'll start to see there's some deviations from the theory that was supposed to define this at the time. And in fact, they did make very careful measurements, and these discrepancies were real. And I'd like sort of people to think about how incredible it is thinking that 120 years ago, they're making these measurements in the infrared, where detectors are still not very good, and they're making absolute measurements with a few % accuracy to know that this was a problem. So what they did was they brought in this theorist from the university up the road in Berlin, Max Planck, and he looked into this and found that the only way he could explain it was if the energy of light emitted was quantized. He didn't like that solution. His phrase was, it was an act of desperation to include such a thing, but that's what was needed to meet this data, to fit this data. And if you actually look at comments made about this, so this is in the Nobel Prize speech, this I would argue is one of the most prescient comments ever made, where they pointed to Planck's radiation theory, saying that it's the most significant lodestar for modern physical research. And it seems it will be a long time before the treasures will be exhausted, which have been unearthed as a result of Planck's genius. And here we are 120 years later, and we are still finding new aspects of this quantum age that Planck pushed us into, even reluctantly as it was. And then this is a note for students that these are some of the comments that Planck solicited when he was trying to figure out what to do with his life, whether he would go to school, whether he would study physics or not. And one of the renowned professors said, everything's already discovered. There's all that remains is just to fill a few holes. I don't recommend you going into physics. But Planck, a true metrologist at heart, said he's not interested in discovering new things. He'll just work to understand the known fundamentals of the field. And yes, he did. And as myself, I'm a metrologist, I thought I would throw in a couple of quotes that I call as an ode to metrology, where Michelson, who's already been mentioned today, of the Michelson-Morley experiment, said that the future truths of physical science are to be looked for in the sixth place of decimals. And Maxwell, who said that the only occupation that's going to be left in a few years is to carry out these measurements to another place of decimals. But even Maxwell knew that that was a critically important thing and is likely to be rewarded by discovery of new fields of research. And I'm going to step back and take an even bigger swipe at the importance of measurement. I won't go into detail, but it appears that the oldest markings mankind has made were recording counts of things. So that it was metrology. It goes back not just thousands of years, but tens of thousands of years. And I believe the view is that it's those markings that ultimately developed into writing, which is essentially allowed the full flower of human civilization, and as well as even affecting our logic and thinking. So without measurement, nothing that you see around you is would be there. So this is an important field. And one of the examples of this important field is that you need to make measurements that you know are stable and will be understood to future generations, that things don't change with time. And one particular application is the storage of radioactive waste. You need to somehow mark the site so that people will understand to stay away from it, and not just in normal human scale time, but for tens of thousands of years, where you can't expect language to even be interpretable at that point. So how do you deal with that? Not to fear. The government has looked into this and come up with a study. And one of the ideas is to use artistic renditions of warning signs, but it's not clear if humans, tens of thousands of years, will understand these. So another way of basing your message is to base it on physical systems that are immutable. Here is the periodic table with indications of something that indicates the radioactive elements. And over here is a map of the night sky showing the precession of the Earth's axis over tens of thousands of years. And here the indication is that the radioactivity is falling off over that kind of time period. So that's a sample of making an absolute marking based on fundamental constants. So let's go back to measurement standards and talk about how this system international is now fixed by defining fundamental constants of nature. So where did we start? Well, an earlier approach was to use the human body as a convenient standard of length, and that's a problem. It's convenient, everybody's got an arm or a foot, but you've got issues if your merchant that you're buying stuff from is shorter than average, you might be getting less stuff that you are being paid for. So what did you do? Well, one solution was to use a particular body. That was the use the arm of the pharaoh as the base standard. And in fact, what they did was a relatively modern approach. They used that granite standard, which was based on the pharaoh's arm, and then they had secondary qubits in wood, and they did pretty well with their accuracy. And you can tell that they did take their metrology seriously, where they recalibrated. They required a calibration of those secondary standards every month, and it was serious because if you didn't get the calibration in time, the penalty was death. So very serious metrology. Then thousands of years later came the French Revolution, and the idea was to come up with a metric system that was based on a particular philosophy, that there would be some fundamental artifact that's accessible to everybody. And the idea was, let's use the meridian, the distance from the Earth's pole to the equator, and not to make it quite available to everybody, they picked one going through Paris. And here is actually in the Paris Observatory marking that portion of that meridian. This is shown here with Bill Phillips, whose slides I've basically stolen for this this talk. And he is there with Dava Sobel. If you don't know who she is, she wrote a book called Longitude, and it's a terrific story of metrology as well as life and death situations. It's a terrific story. I highly recommend every student of physical sciences should read it. So they had this revolutionary idea that they would use the Earth as the absolute standard for measure. But in fact, it turned out that that was challenging to implement because it's hard to access the pole, and making such a measurement turned out to be very expensive. So what happened was they made a measurement as best they could, and then created a meter bar, which measured from end to end was the primary standard, which essentially violated the rule that everybody should be accessible to everybody, but that's the best they could come. And that was in 1799, and 76 years later, they realized an end standard was not the way to go. Instead, it would be better to have a line standard. So they have a couple of scratches in this bar. The distance between those is the meter. And this was adopted in this convention of the meter in 1875, and it was a world standard. And this was the international prototype of the meter. But over time, people found that they could make measurements much better than using the distance between two scratches, they started to use light to measure. And again, think of Michelson-Morley experiment. So effectively, the wavelength of light became the measurement standard, but it was not the official standard because that was this SI unit. But what happened was in 1960, to acknowledge this improvement of measurement with light, they adopted a new definition of the meter based on number of wavelengths of light coming from a krypton lamp. That was done in 1960. And the important thing to note is that was the year the laser was invented. And it was soon found that the krypton standard was not the most accurate way. People started making measurements with lasers. And the de facto standard became this iodine stabilized helium neon lamp. But again, it's a problem because it was not, because those lamps are not based on the SI meter. So it was clear that the meter needed to be redefined again, and the obvious choice was to define the meter in terms of this stabilized helium neon laser. But rather than make the obvious choice, what they did was they made a brilliant choice. That is to define the speed of light. That is to fix the speed of light, not as something you measure, but something that is actually defined. And that way, you can define the meter as the distance traveled by light during a certain fraction of a second. So that means that if you know the frequency of light, and you know, and we fixed the speed of light, you can now know what its wavelength is. So now you've eliminated this artifact length standard. And this definition means that as measurement improves, you don't have to have another redefinition. And in fact, it's a good thing because around about 15 years ago, the Nobel Prize was awarded for frequency combs, which was yet another significant improvement in measuring light. And it didn't require redefinition of the meter. So while that definition of the meter is both brilliant and beautiful, in May of 2 years ago, the metrology community brought that same beauty to the kilogram and to the other units. So how'd they do that? Well, let me digress again to a history of mass, an abbreviated history of mass. Again, you've got ancient artifact standards, and clearly the fact that we have these items shows the importance of accurate measurements going back into history and prehistory. So the way to get beyond these artifacts, again, was this idea of the French Revolution, was to base the mass on a specific volume of water defined by 1/10 of a meter cube. And that was defined as the kilogram. And but it quickly turned out that using a liter of water was not the most accurate way to measure it. And what ultimately happened was they created a kilogram as this platinum cylinder, and that became the de facto standard. And we were back to essentially where the Pharaoh was. And then 76 years later, that kilogram was replaced by a platinum iridium kilogram, which is this artifact that's known as the International Prototype Kilogram, the IPK. And this is this last artifact that was just eliminated. Now, having such an artifact has got operational problems. Here it is, a picture of it shown kept in a vault, and it's something that you don't want to open frequently. So that means you can't have access to this basic standard. It was only opened less than half a dozen times in a century. So that's a real problem. If you think about it, we were here in the 21st century, and the unit of mass was this artifact made in the 19th century based on an object in the 18th century, and it's a problem. And what's the problem? Well, here's some data made comparing the international prototype kilogram, that's indicated by this fancy K here, over a period of nearly a century. You can see there were 3 measurements made, or 3 times measurements were made, comparing that primary artifact to a number of secondary standards. And what you see, they got close grouping initially, but then things started to drift. And it's clear that things are deviating from that. And either you're left to think that that in general, all of these secondary standards are getting heavier with time, or more plausibly, perhaps this international prototype was losing weight, but it can't lose weight because it's actually, its mass is the definition of the kilogram. So obviously it's a problem and something needed to be done about it. So you need to fix it the same way that the meter was fixed by defining the speed of light. So how do we do that? By fixing some constant. Well, we start with the most famous equation in history, comparing the energy of an object at rest to the mass of an object and the speed of light, and also using the equation that the energy of a photon is equal to Planck's constant times that frequency. And by setting the two equal, you can actually solve for mass. And this would be the change of mass that a particle would experience if it emitted a photon of frequency f. Well, it's really hard to weigh the mass of a photon, but in fact, a fellow by the name of Brian Kibble came up with a scheme that would effectively do that by using Planck's constant to define the kilogram using this electromechanical device. It's also known as a watt balance. And how does it work? So we will see. So this here is a clip that explains it better than I can, if I can get it to run. Let's see.
An ordinary beam balance works by adjusting the amount of mass on one side of the beam so that its weight exactly balances the weight of a test mass on the other side. Gravitational force against gravitational force. A watt balance, for all its sophistication, does basically the same thing. In this case, however, the force that balances the weight of the mass is not gravitational, but electromagnetic. This force is produced by a coil of wire that is suspended in a strong magnetic field, created by stationary permanent magnets. The watt balancity mode uses an electric motor to move the coil through the magnetic field at a constant velocity. This movement induces a voltage in the coil that is exactly proportional to the field strength. Measuring the voltage indicates the field strength. In the second mode, called weighing mode, an electrical current is run through the coil to turn it into an electromagnet. As the coil's field interacts with that of the permanent magnets, an upward force is exerted proportional to the current, which can be measured.
Okay, let's go. So what we're doing here is we are taking mechanical power and equating it to electrical power. We've got the mass from the weighing mode and the velocity from the velocity mode and the local gravitational constant. And we're comparing that to the current and voltage measured in the weighing and velocity modes. So question is, how do you get this to relate to Planck's constant? Well, it turns out that by measuring that the electrical units of current and voltage are connected through the quantum Hall and the Josephson effect. Voltage is proportional to h over 2e, where e is the charge of the electron, and current is just proportional to the charge on the electron and passing per unit time. And thus you're able to relate mass in terms of Planck's constant. And this is what a Kibble balance looks like. This is a balance that it's opened up. Normally it's done in vacuum, and it's capable of making masses measurements accurate to a part in 10 to the 8th, which is actually smaller than those changes that we saw of the daughters relative to the primary standard. That is the mass of any dirt that might accumulate or be wiped off of those artifact standards. And in along a direction that would certainly have made the authors of the idea that was born out of the French Revolution very happy. You can actually have your own Watt balance. There was this paper published a few years ago showing how to implement this Watt balance scheme made from Lego for relatively low cost. So it truly is a balance for the masses in both senses of the terms. And in addition, the kilogram doesn't have to be defined through this Watt balance. It can actually be defined other ways by taking very precisely machined and pure material where you are getting the kilogram through the Rydberg constant or Planck's constant over mass. And in fact, these measurements were made truly global fashion all over the world, and all of these labs contributed to defining these constants. So it really is an example of what can happen when the whole world works together. And the final part is the doing things like eliminating the ampere, which, as I mentioned, is, had previously been in terms of force between infinite wires, which are hard to implement. So now by defining electric charge, the ampere is defined in terms of fundamental constants. And the same with the mole, it's now defined just as a number. And same thing with the Kelvin. The Kelvin is defined just in terms of Boltzmann constant, which is fixed. And this convention of the meter in 1875 had this, began this international agreement on units. And 2 years ago, we had what is arguably the biggest revolution in measurement units since the French Revolution. And I would argue that because of the real impact of this artifact-free standard of measurements, it was the biggest deal ever. And this, with the new system being based on these fixed constants. And if you see me somewhere, say hello and ask me about this card, and I will give you, because I typically carry these around, everybody should have one of these fundamental constants cards, and notice that there is no uncertainty associated with these. These are the fixed values. And we really have realized this dream, which started a couple hundred years ago. And just to show you what metrologists do for a victory lap, this is see, it's going to play.
It took more than 140 years. Groundbreaking science. And the agreement from the world's scientific community. At times, it seemed impossible. Accurate. Precise measurements. Anytime. Anywhere. But we did it. Ce l'abbiamo fatta. We have Mr. Shaw. Lo logramos. Lei aboli. Wonderful. Biz bundan ayrı olduk. Proud to die. Biz bunu jassadık. Het is ons gelukt. Biz gered. Intasarım. Vi gjorde det. Amerika. Mi smo to učinili. Dokazali sme to. Angažnaha. Sewaynaha. Congratulations. 축하합니다. Felicitaciones. Mazal tov. Congratulazioni. Shate lavorisce. Selamat sukses. Parabéns. Ongera. Omedetou. Anguida. Onexovo. Mabruk. Japan. Aiko. Felicitations. Congratulations.
So there you have metrologists around the world getting about as excited as they can. And I hope you agree that we now have a universal language that's based on what are now universal standards, and we can talk to mankind through the ages and to infinity and beyond. And that this is essentially the culmination of this quantum dream. All of our measurements are quantum now. So if people talk about, we are entering the quantum age, you can remind them, actually, the quantum age has been developing for over 120 years now. And I hope I've shared some of my enthusiasm for measuring stuff and that about how important that is to all of us. And now I will move on to the second talk. Let me, how much time do I have?
Dr. Migdall, we are a bit behind the schedule before, and I just would like to double check with Dr. Soderberg if we can, if available for another 30 minutes to start, if possibly, if she is available.
Yes, okay, I'm here. That's no problem.
Thank you very much.
Yep.
Okay. So I will make it as short as possible. Let's see. Oh, wrong one. Hold on. Stop sharing. Share screen. Window. This one here. Okay, are we seeing the right talk now?
Yes.
Okay, so this is a review of multiplexing and how this was multiplexing is a scheme to get to an ideal single photon source. And in the interest of time, I'll point out that what I'm doing here is actually just a review of a review paper that we put out last year. And I will just point out some of the highlights and direct you to take a look at it if you want to know details. So the idea here was to give a a bit of the history of multiplexing and how multiplexing addresses a problem, how multiplexing is accomplished, and some comparison. And as you know by now, I'm a metrologist, so we have to include a section on definitions. So the prehistory of multiplexing, that is before multiplexing, was highlighted by this quote out of Nielsen Schwang from now 21 years ago, pointing out that the production of single photons has been a difficulty, particularly producing them on demand, that instead experimentalists use scheme that produce single photons every now and then at random and wait for such an event to occur. So that's the problem. And what did people do initially? They would take a laser and attenuate it so that there are very few photons, but it's a random process. You don't know when those photons are going to occur, and you don't know how many there are. The next advance was the two photon source that we saw a lot about in the last talk. This is a crystal, you pump it, and incoming photons effectively, some small fraction of them, break into pairs under the constraints of energy and momentum conservation. And if you place a detector to intercept one, when you get a click on your detector, it tells you that its twin also exists. So that's effectively a heralded single photon source. But again, it's not really, it's either not single photon or not on demand. The way to make it more on demand was to limit the time at which you can produce the light. So that means pump it with a pulsed laser or pulsed laser in this pair source. But again, it turns out that that's not really on demand because you can't operate with a high probability of producing a pair every time. And that comes from looking at the statistics. In one case, for laser light, you're governed by Poisson statistics. What you can do is you can make the average number of photons in a pulse low, here, say 10%. So you can get the probability of producing one photon is about 10% here, but you'll notice that the probability of producing 0 photons is very high, and there's still finite probability of the producing higher numbers of photons, which you don't want. But you can adjust this mean photon number and dial that up, but what you'll see is that the probability of producing just one doesn't rise to 100%. And for the pair production source, that's governed by Bose statistics, and that's even a bit worse. And the best you can do for the Poisson is about 37%, and for the Bose, in an ideal case, would be 25%. So the problem is that the probability of producing more than one goes like the square of the probability of producing just one. So if you try to make P of 1 high, you necessarily make P of greater than 1 high. So it's either photons but not single photons, or single photons or mostly no photons, which is not a single photon or on demand. So why multiplexing? So here, this is some work out of Christine Silberhorn's group, where they've mapped graphs here showing the probability of heralding a photon and the single photon fidelity on the horizontal axis. And the thing to realize is if I have a point along that's 1 in fidelity, that means when I get it, it's, well, what I get is a single photon. I want that to be 1. And then I want, with a heralded source, I want to have a high probability of producing a herald each time I push the button. And over here in the upper right would be a ideal such source, but it turns out heralded source using a detector that is what's called a click or no click. That means that when it clicks, you've got a photon, but in fact, you don't know if you've got one photon or more than one. So such a source, depending on how efficient it is limited to this lower left triangle. If I have a photon number resolving detector, so that's better than a click, no click, I can tell you how many I've got. I can get a different distribution up to this 25%, but again, I can't get to this region in the upper right corner that I want. That's what multiplexing gets you. Let me just quickly run through some flavors of multiplexing. You can multiplex a number of degrees of freedom, space, time, frequency, or combinations of those. And actually from Alan Willner's talk, I remembered to put in other degrees of freedom like orbital-angular-momentum modes. So how does multiplexing work? Here was a simple example of what is effectively spatial multiplexing. You have an array of down conversion crystals, each pumped by essentially the same laser pulse simultaneously. And you have an array of detectors looking at the herald from each one of those. And what you do now is you operate the pump power such that the probability of producing a pair in any one crystal is low. So that means the probability of producing two pair is even lower, but you have enough of these crystals, they're in sources, that you can be guaranteed that, or have a high likelihood that there will be a pair produced somewhere. And you use the information of which one to switch you to an output. And that's the basic multiplexing scheme, spatial multiplexing scheme. And an example of an implementation of that in a scalable system is shown here, where this is a bunch of sources all pumped from initially a single laser, producing multiple sources with multiple detectors and a switch system. And in this case, they talk about the enhancement they get over a single spatial source. And over here is an example of a temporal multiplex system. And critical to these things are, what are the switch losses? Because if you have too much loss, your deterministic high rate single photon source becomes more probabilistic, again, on the output. And a temporal system is shown here. This is showing one of the earliest proposals. The idea, you produce a pair, you have a detector telling you when you got one, and then you switch that into a storage loop and release it when it's desired. And then here's another scheme using a series of fixed switches and fixed delays to adjust the timing of what comes out. And here's what the details of what such a thing might look like. You set up your system so you got your herald here. The photon that you're going to store comes in, gets reflected off the polarizing beam splitter, goes around. You have a Pockle cell which switches the polarization so that now that photon goes straight through and will continue to go straight through until you reverse the polarization and direct it to the output. And here's an example of what that looked like in this early setup. Here they've intentionally delayed the that stored photon by 1 or 2 or 3 or 4 loops around, and you see that you are able to delay it, but you've also reduced the output probability because there is some loss in these systems. There's another variant which is called relative multiplexing. That's where you don't synchronize, you don't require the photons to be synchronized at a fixed clock time, but it's some convenient clock time, which could have some advantage to minimize switching. And here's a schematic of that. Here you have 2 separate heralded sources, and you don't know when you're actually going to get that herald. And in this case, it turns out you've got one here and one over in this time bin. And in a full multiplex, you would arrange to adjust both of those to your desired output, which might be indicated here by T3. A relative multiplex is an example where you just shift one of them to line up with the other, wherever that happened to be. And that can have some advantages in terms of loss. Here is an example of spectral multiplexing. The idea here is your source produces not just a fixed pair of colors. It actually, what's shown here is what's called a joint spectral distribution of signal frequency versus idler frequency. And this green indicates where a pair could be produced. So in other words, you could produce a pair that had a signal at this frequency and an idler at that frequency, or a signal here and an idler there, etc. And in this case, by using a herald, which tells you which color you've got, you know what the color of the other photon is, and you can actually shift that frequency back to a common frequency. And that has an advantage that this switch really doesn't have additional loss if you try to switch effectively more sources. So that can have an advantage in your system. So what we did in this review was try to catalog all of these various types of sources, and you can't possibly read this, and it's meant to show that it was a challenging effort, but you should also notice that there are a lot of blanks, and that's because the publications didn't give enough information to figure that out. Even when you look closer, you can't, it's still impossible to digest this in this format. But what we did is try to present it visually. And what we have here is a plot of the brightness. So this is the probability that you get a photon every time you push the button. You want that to be 100%. And the heralded fidelity, you want it to be a single photon when you do it. And what we're seeing here is this black line indicates the theoretical limit for a single heralded photon source. So you're limited to this gray region. And what was achieved with integrated multiplex sources is this region over here. Bulk spatially multiplexed is here. A single standard source is confined over here. And bulk time multiplexed, such as spectacularly done out of Paul Kwiat's group, is shown over here. And for completeness, I have quantum dots, which appear to be better, but have the issue of you need to make different dots indistinguishable, and that's become a challenge. When here the goal is, of course, to be in this upper right corner. And then over here, we're similar kind of graph showing the heralding probability, which you want to be 1. And this heralded G2, that means effectively that you're not getting more than one photon out. And in this case, the ideal case is to be down in this lower corner. And again, you can see the usual suspects, the bulk time multiplex and this quantum dot. And I will stop here, pointing out that if you go look up this paper, in the end, we end with a series of definitions that are hopefully well defined and will encourage people when they publish to actually use these terms and fill in the data so that I don't have to pull out my hair to figure out what was actually done. And I will stop there. Paper. And I hope that didn't take too much time.
Thank you so much, Dr. Migdall. That was a great presentation. Is there any question? Let me see if is. I think there is, might be one question. How about, there's a question in the Q&A, if you can see that.
We got, so terahertz single photon sources. So question of what is meant by terahertz single photon sources. It could mean that a single photon source that I can push the button at a terahertz rate. Right now, I believe the fastest that people are pushing is a goal of maybe 10 gigahertz rates. Things at issue are you have to have detectors that can count at high rates, and that's actually for single photon detectors, that's a challenge. I can imagine counting at gigahertz or maybe 10 gigahertz, maybe counting at terahertz. That would be awesome. And tell me where I can get it.
Well, maybe I can't tell you where to get that, but the question that I have, I think, an answer to is, what about changing the central frequency so that instead of 400 nanometers, it's at, it's operating at 250 gigahertz or operating at a millimeter wave?
Okay, so you're talking about frequency.
Central frequency,
Yeah. So with the optical crystals that we typically use, we often are limited in the visible, but we push things out to nearly 10 microns, which is not as far as you're asking. But one of the big goals is to actually make a frequency converter or a frequency transducer to go between those frequencies. And there are a number of schemes to do that using various technologies. The challenge is to do it with high efficiency and without losing any of the quantum information that might be stored in this state. But yeah, there are efforts to entangle mechanical or acoustic frequencies even with optical visible photons.
But in that setup, you'd still start with an optical single photon source and transduce it or something.
Yes, like I say, the with the parametric downconversion, you can go far from the degenerate case where, say, if you pump at 400, you get a pair at 800. You can actually, with those crystals, produce, a visible photon and one as far as 10 microns.
10 microns. But one millimeter would be impossible, right?
Well, I'm not going to do it next week, that's for sure. I don't know how to do that.
I think I have an idea, but we can talk about it offline.
Okay. Great.
Thank you so much, Dr. Migdall. I'm not sure if I can see maybe more questions in the...
But I hope everybody now appreciates that they are metrologists themselves, because everything they do is measuring something. And please consider working in the field of metrology. It's we are in the flowering of the quantum world, and we want more students to be part of that. And that watt balance fits well into an inexpensive university lab, I would think.
There is one question. Are there any single photon sources for quantum educational labs?
Yes, there are. As an employee of NIST, I cannot endorse, but there are. You can Google. Or if you send me an email, I can point you in the right direction.
Thank you very much. Okay, thank you so much, Dr. Migdall, for the excellent presentation, very interesting. And for the interest of the time, I would like to introduce the next speaker. It's my great pleasure and honor to introduce Dr. Katian Brickman Soderberg. Dr. Katian Soderberg is a principal research scientist at the Air Force Research Laboratory, AFRL, Information Directorate in Rome, NY. Dr. Soderberg is the primary investigator and group leader for Trapped Ion Quantum Network Group. Dr. Soderberg received the Bachelor of Science in Physics from College of William and Mary, and Master's and PhD in Physics from University of Michigan, and was a postdoctoral researcher at the University of Chicago. Dr. Soderberg has over 15 years of technical experience in atomic physics and quantum information processing. Her graduate work focused on trapped ion quantum computing research and included key demonstrations of photon-mediated entangling gates and proof of principle quantum algorithms. Her postdoctoral work focused on novel neutral atom quantum computing and difficulties associated with targeted atomic interactions and optical lattice translation and control. Before joining AFRL, Dr. Soderberg was a technical consultant for quantum information sciences. Dr. Soderberg's talk is on quantum information science, and the abstract of the talk is recent advances in quantum information science indicate that future applications of quantum mechanics will lead to disruptive advances in capabilities for U.S. Air Force controlling and exploiting quantum mechanical phenomena will enable initial sensors and atomic clocks that provide GPS-like positioning and timing accuracy for extended periods of time in degraded environment. Communications networks with provable information security, unprecedented sensor resolution, and computers with exponential speed up in processing speed. To ensure that the future Air Force warfighter maintains a technological advantage, the AF must implement a QIS strategy that leads to robust and deployable quantum systems. This invited talk will discuss the AFRL QIS strategy that encompasses timing, sensing, communications, and networking and computing along with related capability development. Dr. Soderberg, I would like to welcome you to the talk.
Thank you very much. Can you hear me okay? Yeah, okay. I don't have any video capability today, so I apologize for that, but let me try and share my slides. Okay, can everyone see my slides? All right, wonderful. Yeah, so thank you for the introduction and thank you for the invitation to speak today. I'm excited to share our work in quantum information science with you. So at AFRL, we're a multi-directorate organization and we're spread out across the US and abroad. So I've shown here where all the different directorates are, and then along the bottom, I've shown which ones have quantum work going on. So I'm not going to go through all of these in detail, but we're up here in Rome, New York, not far from Colgate, where Professor Galvez spoke about. We're just neighbors to him. And we do quantum networking and quantum computing. The group down in New Mexico at Kirtland focuses on quantum timing and quantum sensing, and then there's a scattering of quantum research at some of the other directorates. And I'll say probably people on the line are most familiar with our basic science office, the Air Force Office of Scientific Research, which is in Arlington, Virginia. So at AFRL, we have active research. This is how we break up quantum into the main 4 areas shown on the outside of the puzzle pieces. And we break it up by timing, sensing, computing, and networking. And then in the middle, some other areas that we're focusing on are things like supply chain and the enabling technologies that make the quantum work. And also a big one for us is workforce development. So at the Air Force, this slide shows some of the reasons that we're interested in quantum technologies and the potential payoffs for the Air Force. So again, here I've broken it up by quantum timing, quantum sensing, quantum comm and networking, and quantum computing. And then I've shown some potential applications that we're interested in. For timing, it's things like fewer timing updates and improved navigation. In the sensing, you want to be able to do an enhanced inertial navigation. And then advanced low swap means low size, weight, and power. You'll hear me talk about that quite a bit through this talk. Low swap sensors. And if you are able to combine the applications of timing and sensing together, you can push for things like self-sustained PNT. That's another way to say GPS-like accuracy and GPS-denied or degraded environments, where PNT here means position, navigation, and timing. For the comm and communication and networking work, we're interested in looking at things like entanglement distribution test beds, and also, again, these fieldable low size, weight, and power systems. For the computing, like everyone, we want to data process faster, and we're also interested in asset optimization, things like scheduling problems, and image and object recognition. And again, if you're able to combine quantum networking with quantum computing, you can push for things like distributed quantum computing. That's not the only benefit, of course, but it's just one potential application of merging these two subfields together. And then, of course, the kind of underlying piece of all this is our workforce and enabling technology foundation. So now I'm going to step through each area one by one and give you an overview of what the current situation is, what we're working towards, and show some recent results for each area. And I'll start with timing. Here again, we're pushing, when you combine with sensing, for GPS precision and GPS denied environments. And currently, you can get a stability of about 10 to the minus 9 seconds per day under static conditions, and the volumes are typically about 10 liters. For GPS updates, you currently need to do that several times a day. And so what AFRL would like to push toward are very small, lightweight clocks, like the CSAC. So I show the chip scale atomic clock up here. This is a vapor cell clock that I believe has an accuracy of around 10 to the minus 6 or so, that are less accurate than research grade demonstrations like at NIST. So what we want to do is get closer to the NIST clocks, but have the size, weight, and power of a chip scale atomic clock. So the best clocks in the world are at NIST in Boulder, and they get to 10 to the minus 18, 10 to the minus 19 accuracy, which is amazing. If you walk into their labs, they take up an entire room. And so that's not really amenable. For the DoD, we have to think about putting these things on aircraft. So it's not amenable to put it on an aircraft. And so what we want to do is get more toaster oven or shoebox size clocks that have better accuracy than the CSAC, but don't quite get to the accuracy that a research grade demonstration can get to. So what our team is working towards is improved stability under static conditions, and they're shooting for a volume of about 500 liters to start. They want to push for fewer timing updates, so they want mobile clocks that can hold time for weeks to a month. And in the short term, they'll go for larger clocks. This is a pretty large volume compared to the 10 liters, but that allows for more stable systems. And then once they have the system stability that they want, then the focus will turn back to reducing the volume to something more amenable to putting on an aircraft. And so right now they're testing the next generation of atomic clocks, the performance. This is a recent graph that shows the Allen deviation versus the averaging time for one of their ORAS is just the name of the clock that they're working on, the performance that they got. And also I should note that across all the research technologies recently, we had what we call the Quantum Collider event, which was a phase 1 and phase 2 effort. This was to fund small business initiatives. The Air Force funded several small business initiatives to further develop quantum technology. And last summer, we also held an international quantum event where we also offered some grant money in a competition to the attendees of that event. So now I'll move on to the sensors. And here again, we want the GPS precision and GPS denied environments. Much like in the clocks, the story here is to reduce the size, weight, and power of these systems and also get better performance. So right now, sensors can operate over hundreds of meters per hour in a volume between 100 and 1,000 liters. And the picture I've shown here is a ring laser gyroscope. That's, I believe, a naval gyroscope. It's a strategic grade. And you can get GPS-like accuracy for much less than an hour. So our focus is toward low noise sensors with reduced size, weight, and power to maintain GPS-like accuracy for longer than an hour. And they're shooting for a reduced sensor noise with moderate volume. Another thing that we're involved in is we're part of a quantum-enabled strategic challenge with Australia, Canada, New Zealand, the United Kingdom, and US to field quantum technologies in a 2022 shipboard platform. So this will be a combination of either sensors or clocks, and each country will bring a device to test on a ship that New Zealand's providing next year. And the part that AFRL is bringing to that is we're bringing a clock, and we're also working on the open source software that will be used to run that demonstration. And then again, they have some recent results here of an ultra pure rubidium source that they developed at AFRL. So these sensors are also cold atom based, much like the clocks, and they're using rubidium for most of the sensor work. They have some papers where they've gotten some IP for critical quantum sensing technologies for low size, weight, and power quantum sensors. And they also, the team was also involved in the small business initiative that we had last year. So now I'm going to move into the networking. There's two slides on networking. One is on satellite-based quantum networks, and the other is on ground and low-lying aircraft-based networks. So for the satellite-based networks, they're working on field experiments to simulate a space-to-Earth link. They're working on prototyping and field testing the components now and designing a quantum ground transceiver. What they're working towards in the short term is they're looking at the optimal wavelength for quantum communication study. So most folks that think about quantum communication over long distances want to push up into 1550 because that's where all the fiber technology is. But the AFRL group is looking at closer to 800 nanometers, 850 for this ground to space link, because they think that's actually a better wavelength to transmit through the atmosphere to go between ground and space. They're also developing entangled photon sources for these links, and they're demonstrating entanglement-based quantum networking applications. Like I said before, they're building the ground transceiver. And then one key point to all of this is that a lot of the quantum communications demos that have been done recently have been done at night, and that's because you don't really want to fight against the background of the sun with your detectors when you do this. But the AFRL group has figured out a way to filter out the sun, the background from the sun, and so they're able to operate these both at daytime and at nighttime. And that was primarily done using adaptive optics. And so these recent results show that this is the experiment they did during the day, and it just shows that they were able to get good results despite the sun being up. They did not do this at night. And then they've also procured and characterized the entangled photon sources that they'll use for this ground to space demo. And they're looking into small business initiatives for pulse entangled photon sources. Does someone have a question? No? Okay, I'll keep going then. I'm happy to answer questions either now or after my talk, so jump in if you'd like. So now I'll go to the quantum networking for ground and air-based quantum networks. So this is the work we do in Rome. We do this ground and air-based quantum networks, and also the quantum computing work that I'll talk about next is the work that I'm primarily involved in. So currently we're pursuing trapped ions, superconducting qubits, and quantum photonic integrated circuits for quantum networking applications. That's what these pictures are for. We have trapped ions. We just added a superconducting qubit capability within the last year, and then we have an integrated photonics team. And then the trapped ion group is the one that I lead. So our push is to move beyond point-to-point demos to distributed entanglement across a multi-node, meaning 3 or more nodes here, network. And we want to focus on entanglement distribution both in a homogeneous system, so a network that's composed, say, of all ions, and also in heterogeneous networks. So that would be a network composed of some combination of ions, superconducting qubits, and integrated photonic circuits. So really the motivation here is that the ions provide the long-term memory in the network. The superconducting qubits also provide memory. So the memory is not as good in the superconducting qubits, but with the ions, the operations tend to be a little bit slower. And so the operations are faster in the superconducting qubits. And so that's why we've chosen to pursue two matter qubits, if you will. And then of course, the photons are going to be the natural information carriers in all of these networks. And so what we're working toward is realizing a 3-node network with the ability to distribute entanglement both within the nodes, so to do quantum information processing locally at a node, but also between the nodes, the distant nodes of the network. We are also planning to do a field demo with a memory-based ground node connected to an unmanned aerial vehicle or an unmanned aerial system, or some people call those drones. So we would like to put one of our photonic processors, which is shown in the upper right of this middle box, one of those chips on an unmanned aerial vehicle, and then connect at the single photon level to a trapped ion system that sits on the ground. And then just one note, why would you want to do this? You know, one benefit to doing quantum networking is that when you have fully quantum transmission, you can ensure data integrity throughout the network, and it also provides intrusion detection. So if you have quantum nodes, if you don't have quantum nodes, but you're trying to connect classical nodes with a quantum signal, then you have to convert the information back to classical information when you get to the nodes. So if you have a fully quantum transmission across all the nodes, then that gives you a little bit more security in your system. And then some recent results. So we've demonstrated all 3 of the technologies independently. We have trapped ions, we have superconducting qubits, and we've done demonstrations with the integrated photonic circuits. And now we're really pushing toward connecting the 3 systems together and everything that goes with that, including quantum transduction between the very different energy scales that these all want to operate at. So now I'm going to move into the computing piece. So that the Air Force has decided that we are not going to build a quantum computer because there's lots of folks working on building quantum computers, and it would be a duplication of efforts and probably not the best use of resources for the Air Force to do that. But what the Air Force does need to do and needs to understand is how these computers work. So what we're doing is that we're building a team to develop algorithms for these quantum computers. And really the current situation is that users are coding to the specific hardware, as each system is unique. So even systems that share the same underlying qubit technology are often programmed differently because there's not yet a universal quantum computing programming language. And so, you know, even if the underlying hardware is superconducting qubits, it very much depends on which machine and which version of which machine you're using will dictate how you program it. And then if you go to a different qubit technology, for instance, IBM has superconducting qubits, they're programmed much differently than, say, a machine from IonQ or Honeywell, which are based on trapped ions. And so we're exploring the different programming languages that are available, as well as the commercially available devices that are available, to see what are the benefits and drawbacks of each, so that we can start to run some algorithms to see currently what can be used for Air Force relevant problems, but more likely than not in the future, as these systems become more powerful, which ones will be able to be used for Air Force problems. And so we're primarily operating on the IBM machine right now. We are a hub member. That means we have access to their commercially available devices, and we can also get our collaborators and partners access to these devices. And so we're growing that network. In the future, we would like to expand to other commercially available devices, maybe like IonQ or Honeywell or one of the others that are available. But right now we're on the IBM device, and we're developing, testing, and evaluating algorithms for applications like scheduling problems and testing neural networks. And then we've had some recent results. We published a paper on IBM's 20-qubit quantum computer that appeared in AIP Advances. It was actually an editor's pick, which was nice. And then we have about 9 users on our hub right now. That includes academia, other government labs, and industry partners. And we're growing that network. And so if you're interested in finding out more about that, please feel free to contact me. You can ask me after the talk, but you can also send me an email, and I'm happy to provide more information on that. We also developed a quantum computing short course. This was in collaboration with the Air Force Institute of Technology, NISTech, which is a local company in Rome, New York, and USRA. And we gave that short course at AFIT last year. Okay, so now for the final two pieces, but critically important pieces. One is the enabling technologies. So here we want to focus on reducing the size, weight, and power of these enabling technologies with deterministic qubit design and placement. So really what we want to do is push as hard as we can to get the enabling technologies, things like lasers and microwave sources, reduced in size, weight, and power so that they're amenable to some of these airborne demonstrations that we want to do. And we also need to ensure that the underlying technologies can endure high dynamic environments for future needs. And we want to move from bulky systems that could require things like cryogenic systems or stabilized lasers to integrated photonics and room temperature devices where we can. Then the other piece that we're working hard toward is workforce development. So AFOSR does a lot of this workforce development, although I will say that we have quite a robust summer program at AFRL as well. We can have faculty and students visit us for the summer in internships. And really on our campus every summer, we gain about 200 people, which is roughly a 20% increase for us from where we normally sit. So we have a very active summer program. And if you're interested in hearing more about that or learning about opportunities for your students or yourselves, please also contact me and I'm happy to discuss that. But really what we need to do as a community, I would say, is ensure that we have a quantum smart multidisciplinary workforce that needs more than just physicists. We tend to be physics heavy in the field, but we also need computer scientists, engineers, mathematicians, people that know photonics, material scientists, etc. And we are also working hard to strengthen ties with our international partners. I'll touch on that in just a moment when I talk about our Innovari Advancement Center. And again, there's many ways to partner with us, so if you're interested, please let me know. So in the last little while that I have, I want to show you where we're headed with our networking work. So we're pushing toward building a quantum networking distributed test bed. This is a little bit different than a lot of the test beds that are starting to come online. One is that it's distributed in geography. So each column on this graph, if you will, is a different physical site at AFRL. Right now, they're all in Rome, New York, although that could be expanded in the future. And then it's also distributed in research areas where we can go from very basic research to very applied research. So as a DoD lab, Department of Defense, our in-house laboratories are what we have right now, and we're limited in who we can bring into those labs because you mostly need to be a US citizen to access our facility, which is, a little bit difficult when we're being strongly encouraged and we want to partner with our international partners. And so for a long time, we told folks, we're happy to partner with our international partners, but the most we could do is have phone conversations with them, which is maybe not the most conducive way to do research. And so our leadership decided to have a new facility where we could better partner with both our international and our domestic collaborators, because a lot of our domestic collaborators are not necessarily US citizens, nor are their students. And so we were inspired by what the Army Research Lab did, which is in Adelphi, Maryland. They started an open innovation campus a couple of years ago. And so we're repeating that, replicating that in Rome, New York with our Innovari Advancement Center. So this is an open innovation campus where we will have many of our AFRL technologies, not just the quantum ones. And it will give us a facility that we can partner with our both international collaborators, but also a lot of our students and faculty will spend time in this facility. So for the quantum work, what we're going to do and what we're in the process of doing, it just opened earlier this year, is we're going to have all three of the qubit technologies I talked about earlier, the superconducting qubits, the quantum integrated photonics, and the trapped ions, along with our quantum algorithm work, will also be run out of this center. We want to build a quantum network test bed, a small one, where we can interface all three of these technologies together and work on very basic of basic research problems, like how do you distribute entanglement? How do you verify the entanglement? Things like that. Once you have the entanglement, what can you do with it if it's distributed like this? And so those are the type of research problems we want to tackle. And then not right away, but eventually we also want to have a user-provided qubit technology component to this, so almost a user facility of sorts, where once our network is up and running, we could have our collaborators bring either different types of qubit technologies, or different than the ones we have, like neutral atoms or NV centers, or quantum dots, pick your favorite, and plug it in to our network. So we want to push for a plug and play type architecture so that they could test how their quantum system works on our network. The other thing that you could think of testing here is classical components. I don't think as many of the classical components that you're probably going to have in a network have been tested in the quantum regime. And so that's another possibility for this user-provided qubit technology. And then the intent is that we'll see development into our in-house labs where we'll have similar research labs, but here now the focus turns to more applied work that really pushes on the heterogeneous integration and advancing the networking and algorithm protocols that we'll have. And then viable technologies will then see development out to our test sites, where here we want to do things like test quantum systems on drones. I said we wanted to start with the integrated photonics work, and then, but eventually we want to try and put an entire trapped ion system up on a drone. So that's a little bit of a stretch. If you've ever been in a trapped ion lab, you'll know that it takes up many, many, many tables. But there's really precedent starting to be set. So a company in Boulder, Colorado, Cold Quanta, now makes vacuum chambers that can essentially fit in the palm of your hand. That, along with a lot of the laser development that's been pushed by some of these quantum computing companies that are trying to do trapped ions, have really pushed the industry into a much smaller size regime. And so then you can start to think about putting a trapped ion system up on a UAV. Like I said, that's a little bit of a stretch goal. That's like a five plus year timeline. That won't happen tomorrow. But for the UAV work, we'd like to try and push out to the field sites in the next 3 years or so. And so I should also say that these test demonstrations can be ground to ground, ground to air, or in the future, maybe ground to space. One of our AFRL facilities does have an optical range with a ground station. And then also, we don't want to just test the network itself, but we want to see what you can do once you start to distribute entanglement. So you could think about putting things like clocks or sensors or distributed computing elements on any part of this test bed, not just the test sites, but even in the Innovari Advancement Center. Oh, this one got messed up. That's okay. So this is just, I think this is my last slide on our Innovari Advancement Center. It's supposed to say a bold way forward, but the font got messed up. So here the vision really is to accelerate the development of these, potentially game-changing capabilities. Quantum is one of them. There will be other Air Force technologies in our Innovari Center as well. And we really want to build a better ecosystem where we can truly bring the world's leading experts into our lab to help us work on some of these very hard problems. And so that's all I have. Thank you everyone for your attention, and I'm happy to answer any questions.
Thank you so much, Dr. Soderberg. That was a great presentation. I think we have some raised hand in the attendees. I'm not sure if they're still here. There was one question. Oh yeah, there is somebody raised hand again. Okay. Please go ahead, Dr. Noah.
Hi, Prabhu. Thank you, Dr. Prabhu. Dr. Soderberg, the questions are basic one, just to set the table. What are the 1 qubit and 2 qubit gate fidelities for the trapped ions you have in your lab or that you may have in the next year or so? And the second part to the question, I think it may be related to the first one, is what fundamental limits do you foresee for the number of nodes you can entangle in a quantum network, say a trapped ion node?
Yeah, so the gate fidelities, we haven't reached them yet in our lab, but I'll cite the community. They've gotten 99.999% on single qubit gates, and 99.8 or so on the entangling gates. Really, trapped ions, I would argue. I don't know if there's any superconducting qubit folks on the line, but they're one of the leading qubit technologies to realize a quantum computer, and it's because all the benchmarks that you're asking me about have been, sufficiently fulfilled that that's not going to be a limiting problem for the ions in the foreseeable future. Same is true of the superconducting qubits. Superconducting qubits and ions are neck and neck in terms of their ability to make quantum systems, and so that's a big part of the reason why we chose them as our underlying network. The other part of the question you asked me is how many nodes can you entangle? Right. That's a good question. And I don't think the answer to that is well known at all. It will depend on how fast you can entangle your nodes and also how well you can hold on to that entanglement as you do the other operations. You know, really in the community, there's only been 1 or 2 3-node demonstrations ever. So most people have only gone point to point so far, which is a likely easier and different connection than if you try and do a triangle configuration like the one I've shown here. But the ion connections have been done at something like 10 hertz, I want to say. I think Chris Monroe, who's at Duke now, he used to be at Maryland. Before that, he was at Michigan. Leads the field in that demonstration. It's about 10 hertz. They think they can push it a little bit more. And then the memory time in ions for coherent information, I think the best demonstration recently was an hour. It used to be 15 minutes, but now it's up to an hour. And you can hold entanglement for about a second, which should be enough time to start to do some of these smaller networking demonstrations. But the larger question is still unknown. Hopefully a lot. But I think we need more information before we start to put limits on how many nodes you can entangle. You know, it's also going to depend on what you want to do and how much entanglement you want spread across the network and how you spread it across the network. I think will also inform some of those answers. It's likely going to be very application dependent.
Thank you very much. I think there is a few more questions. One is, would you not say that Q number is more universal? Also, Honeywell, IonQ use same, even usable on IBM.
I missed the beginning of that. What was the question at the beginning?
Would you not say that Q number is more more universal? Q sharp. I'm sorry, yes.
I think that's more used in computing. So whoever asked us to jog my memory on Q sharp, I believe that's more of a quantum computing as the Q sharp language in quantum computing. Are we looking into that? Is that your question? Sorry, I thought you were asking me about Q sharp related to networking. Q sharp, yes, I think our team is looking into that language as well. So there's several, essentially everyone's coming up with their own language now. But did you have a specific question about Q sharp?
Oh, hi there. Sorry, the question was from me.
Okay.
And basically, you mentioned that there is no universal language that you can use across devices because every platform has their own language. So what I was saying is that Q sharp seems to be a high-level language that's sort of more universal, also used by Honeywell, IonQ, as well as MSFT, which is Microsoft, but also it can also be used on IBM platforms. So as in your slide, you mentioned that there is no, so I was thinking, would you not consider Q sharp as that option for yourself? Thank you.
Yeah, no, that's a good point. Yeah, I need to look in a little bit more to Q sharp and ask our team about it. But yeah, I think people are trying to develop, so maybe I should watch my wording is a better, better piece of advice. I think people are trying to develop universal quantum computing languages. That I know of, there's not one yet that can hit all of them, but yeah, people are definitely trying.
And one other quick question while you're on the, on the voice. I mean, are these research facility or, these areas to collaborate open to students who are outside the US? I mean, who are not US citizens? You mentioned briefly that, okay. Okay, great.
Yep.
Thank
so
you.
That was the whole point, a big part of our point. It wasn't the whole point to create this Innovar Advancement Center, but it was a large motivation in that there's a lot of students and faculty that we can't collaborate with as fully as we'd like. Really you want to bring someone into your lab and work side by side with them. That's how true collaboration gets done. And so yes, this Innovar Advancement Center will allow us to bring in anyone. We're not limited to US citizens at all. And so yes, if you're interested in learning more about that, or you have students you think would be interested, please contact me and I'm happy to discuss that more.
Would you be sharing your email in this slide later, or how do we reach out to you?
Sure, I think Bot has my email address. Would
Sure.
you mind sharing it with folks?
Of course, if they email me, I can reply back. I don't know their email. Please, my email is in the chat, and please feel free to contact me. And so there are more questions. If sorry, is there any? Is that we answered the questions? I guess. So could you please elaborate a bit more on your work on quantum networks? What frequencies you said were more optimal for ground station communications? How long to quantum internet?
Yep. So the how long to a quantum internet is an excellent question that I think everyone in the field would love to be able to answer. And what that quantum, I'm going to put it in quotes, quantum internet looks like, right? It's likely not going to replace the internet we have today. It's going to be some complementary layer that does something unique. Yeah, as far as the frequency, so for the ground to space communication, that work's done by our team in New Mexico, and they're looking at somewhere close to 850 to do the ground to space link, because they believe that that frequency will transmit better through the atmosphere. For the types of links that I'm talking about in Rome, where we want to go ground to aircraft, we're really targeting 1550, although we also may look at 800, because eventually we want to be able to put those photons in a fiber to do the ground distribution piece. So we're going to target 1550 for the most part. But depending on how the New Mexico folks do, we may also look at some of the wavelengths they suggest.
Thank you. And the other question is, any comments on quantum annealing utilization in the future AFRL?
Yep. We also, we are not actively looking at quantum annealing right this moment, but we plan to return to it. We did have an effort to look at quantum annealing a few years ago, primarily on the D-Wave machine. And yeah, I think we'll return to that. It's just a matter of bandwidth limitations right now and the amount of people we have on the team and how much they're able to do across a day.
I think DARPA is looking into quantum annealing at the moment.
Yes, I believe so as well.
Yes. Another question is, you mentioned in a training course that developed and gave last year. Is this course open to universities?
I believe it is. I have to look into the details. Well, one of my colleagues is in charge of that. Her name is Laura Weston, and Paul Olsen is also involved. So I can ask them for more details if you send me an email. Yeah, I'd be happy to share that information. We also have a few tutorials on the archive for some of the quantum computing work as well. And so if you send me an email, I can provide those references.
And again, they are asking for your email. I think you mentioned that if they can share your email with them later.
I can put it in the chat, and then you can also feel free to give it to anyone who misses the chat message.
Thank you. So the email is in the chat. Thank you. Thank you very much, Dr. Sadler. I think there is no more question, but I have a question myself. You mentioned about UAVs. So are you considering a quantum communication like photon entanglement between UAVs or this type of research?
Yes, that's exactly what we want to do. We want to distribute entanglement to start a UAV to a ground station, but in the future, yeah, we'd like to try and go UAV to UAV as well.
In fact, one of me and a colleague, myself, and a colleague who is actually very experienced in quantum area. Myself, I'm an engineer, mechanical engineer. I'm not quantum physicist. We tried to submit a proposal to you, but you rejected it. So
you can always try again.
Yes.
And I know Paul Qwiat was on the line earlier. I'm not sure if he's still on the line, but I know he's done a lot of work recently too with quantum
definitely.
systems
Actually,
on drones.
we are following his work. We are trying to follow his work, and one of the reasons that we actually organized this workshop is that we would like to bring more mechanical and aerospace engineers to the field of quantum, because we have already a lot of electrical and computer engineers who are contributing significantly to this field, but we feel that maybe more mechanical and aerospace engineers also can contribute. And we are also doing that, but at the moment, we are trying to start really, like we are following some work that Paul Kwiat has done, and we are trying to learn and implement those kind of technologies.
Yeah, no, that's wonderful. Yeah, send your mechanical engineers to us after they graduate. we're always looking for good engineers. So
we also developed a course for the first time for mechanical engineers. So we traditionally teach mechatronics for engineers, and we integrated some quantum, fundamental of quantum, like photon quantum mechanics, like quantum entanglement and quantum cryptography, into our curriculum. And we actually published that, and we are hoping to promote this area to mechanical engineers.
Oh, that's wonderful.
Thank you very much. And I'm not sure if there's any other question. If not, let me just double check. I think there's no. Thank you so much, Dr. Soderberg, for the excellent presentation. I really appreciate that. And I think if there's no other question, we can move to the next talk.
Thank you. Thank
you so much. Okay, it's my great pleasure and honor to introduce Mr. Doug Fink, who is the managing editor of Quantum Computing Report, which he founded in 2015 so he could apply his wide breadth of experience to help accelerate proliferation of quantum computing to the general marketplace. He started his career as a mainframe computer design engineer at IBM, and subsequently served in a variety of executive roles in marketing, engineering, and operations at Intel, Western Digital, Corning, and several startup companies. Doug holds degree in computer engineering and management from University of Illinois and MIT, respectively. Doug's talk is on a tour through the quantum ecosystem. The presentation would show all the different industry players and how they can work together to provide a complete solution to an end user. It shows a model for the complete solution stack from user community down to the chip of what is needed to make quantum computing a reality. I would like to welcome Mr. Doug Fink.
Thank you, Farbad. I appreciate the introduction, and it's been a very interesting day so far. So my talk will probably be a little bit different than some of the others. Won't be quite as technical, but it will still be quite complex. There are hundreds of organizations working in the quantum field right now. And what I will try to do, I will be focusing on quantum computing. I won't spend so much time on quantum sensing or communications in this presentation. That are involved. I won't cover every single one. If you have a favorite, my apologies in advance if I don't cover your favorites, but this should give you some ideas. Let me start with this picture here. This is, I would call a quantum computing stack. Professor Oliver did a very good job of talking about at the chip level what is needed to build a quantum computer. But the point is to really deliver something useful to an end user, you have to do a lot more. Chip is where you start, as you can see in the very bottom of this picture, but you have to package that chip, you have to control that chip, you have to have all the various software layers for that chip. You have to make that quantum computer available in a cloud. And at the very end, you need to have a lot of education and user communities and things that allow people to understand how to use that capability. So being successful in quantum computing, what I tell some of the companies in this industry, you can't just stop at the chip level. You really have to think of the whole solution. And sometimes not the best technology will win. It may be the company or the organization that can put together the best collection of all these items. So I will go through these and just talk about each of these sections and who the various players are. Besides the people who actually build hardware or software and actually build things or provide things, you also have support organizations, of course, the universities, investors, governments, trade organizations, and they are important too. Many of them, of course, supply money, and money is always important, but they also help promote the industry and promote the technology, and they play a very key role in the ecosystem. So let me start on the hardware side of things. And I will start at the component suppliers. All these quantum computers are built with lasers and refrigerators and instrumentation, cabling, all sorts of things like that. And they are very important. Many of them are focusing now on the quantum industry. One term that you'll hear quite often is this thing called a dilution refrigerator. That is the refrigerator that will cool your superconducting chips down to 50 millikelvin. And these refrigerators, by the way, cost somewhere between $500,000 and $1 million. So it's not something that you would buy at your local Sears. They're very expensive refrigerators, very, very exotic. But then you have a lot of instrumentations. We talked about microwave pulses. Companies like Zurich Instruments and several others will do those, as well as lasers, single photon detectors, single photon generators. We had a few talks talk about that. Even the cabling is important too, because in these superconducting systems, you have to figure out how to take thousands of wires and route them from the electronics, which operate at room temperature, down to these the chip at the millikelvin temperatures. You also have wafer processing. There is at least one company, and probably others, that are semiconductor foundries that are now starting to process chips for these quantum companies. Two that I know of is company called PsiQuantum, which is a photonics chip, and Equal One, which is a chip based on spin qubits. And probably the most interesting one is a component supplier in Italy called Gopian. Gopian's primary business is to make the glass cases that you would see in a museum. You go in and you see a piece of artwork or a sculpture or something like that. It's in a glass case. Well, IBM hired them to create the glass enclosure for their quantum computer, the IBM Q System 1. You may have seen some pictures of that. And that was made by this Italian company. But getting back to the chip level, there are one thing I should point out, there are many different technologies that people are using to develop quantum chips. And we've talked about superconducting, we've talked about photonic, but there's neutral atoms, there's trapped ions, there's the quantum annealing, NV diamonds, topological. And we are tracking right now on the Quantum Computing Report website 92 different organizations that have various development projects to develop some form of quantum chips, and with a total of 121 projects. So some organizations are doing more than one technology. At this point, you can see that superconducting is the most popular, but it's followed closely by trapped ions, spin qubits or quantum dots, and photonics. So there's a lot of different approaches that people are taking to quantum, which is actually one of the reasons I'm most optimistic. Even though it's a very difficult technology, the fact that we're trying so many different things to be successful at it, I'm sure many of them will fail, but I'm sure a few of them will succeed also. So that's why I'm optimistic about quantum. Some large companies, of course, that are developing chips. IBM has superconducting. Google's also doing superconducting. Honeywell, an aerospace company, is working on ion trap. Intel has a major effort in Oregon, research in Oregon. They started with superconducting, but actually now they're focusing more on the spin qubits because that's very, very similar to the semiconductor technologies they're using today. Microsoft is doing research on something called topological qubits, which is a very difficult technology, but if they are successful, they think those qubits could have a higher quality than any of the other different approaches. I would also point out there's lots of startup companies that are developing worldwide, that are developing technologies. And again, we keep track of all the different companies, what they're working on. Many, it's a worldwide effort, US, Canada, Asia, Europe, and all of them are doing these. And these are all private startup companies that are working on developing technology specifically for quantum computing. Again, I'm not including the quantum sensing or quantum communication companies. Maybe I'll save that for Farbad's next workshop. But once you have the chip itself, you need to control the chip. And typically, is the way you would control the chips, as we've seen earlier in some of the presentations today, you either use microwave signals that allow you to manipulate the qubits and implement those gates that we've been talking about, or you use lasers in order to do that. But the key is, how do you actually control it? If you use a microwave signal, what frequency do you use? How do you pulse it? How do you control the frequency? All of those things. And all these computers, and there's similar things for lasers, all these require some very specialized hardware and software to figure out how to do that. And it turns out that the control, the way you shoot those microwave pulses down to the qubits can have a very, very large impact on the qubit fidelities and the quality of the qubits. So, and there are actually companies that specialize in providing this type of technology. There are some large companies that do a number of different things, like Keysight is the spinoff of Agilent and HP that does electronics instrumentations. They've been in business for years, but they are now making a big effort on quantum computing. In fact, I think Professor Oliver is using some of their equipment. There's a company in Switzerland, Zurich Instruments, that has hardware controls. Quantum Q-Blocks also has these. So these are all basically electronic instrumentation, arbitrary waveform generators, and various detectors and sensors to do that. But associated with that, there are companies that are also working on software. You may have the capability to use an arbitrary AWG or arbitrary waveform generator to control a qubit, but how do you figure out which ones to do? How do you calibrate these things? It's very, very tricky. And there are companies that specialize that. There's a company in Australia called Q Control. And Quantum Benchmark was just in the news yesterday. They specialize in this software. They were just acquired by Keysight. So Keysight is trying to not only supply the hardware, but also supply the software too. And there's a lot of papers, a lot of technology on this, but it's, again, very critical because if you have the right software and the hardware to control the qubits, it'll do wonders for improving the qubit fidelities and the ultimate quality of your calculations. Software is also an area where there's a lot of different people taking a lot of different approaches. If any of you have taken a quantum computing course, or even if you saw the slide that Professor Oliver put up earlier this morning, there's standard gates. Of course, they always use in the textbooks, the Pauli gates, the Hadamard gates, C-naughts, et cetera. But it turns out that the actual hardware itself actually typically implements what are called native gates, which in many cases are lower level, or they're different. So one of the things that is really critical, and a lot of research has been put into this, but I think even more still needs to be done, is how do you take a quantum program and translate it from, we'll call it the classroom gates, the X, Y, and Z, Hadamard gates, et cetera, to these native gates that you may have in the machine. And again, each machine is going to have a different set of native gates. So the program that does that is called a transpiler. And what's really critical is to be able to optimize it. Just like in classical computing, you always want to take a high-level program that may be written in C or Python, and ultimately it gets compiled down to assembly language. You want to do the same thing in a quantum computer, but I would argue that in a quantum computer, it's even more critical because the resources are very limited today, only a few numbers of qubits. You want to do everything you can to optimize it to reduce the number of gates, reduce the number of qubits that you use, to reduce the circuit depth. That's the number of gates, periods you have, and to get the lowest error rate possible. So there's a lot of tricks that people play, and there's a lot of research being done on that, and it's getting better. Now, one thing I would also point out is that many of these platforms that we've been talking about, like Q-Sharp and Qiskit and many of these others, many of these platforms will have a term that you'll see is called hardware agnostic. So you could write a program on Microsoft Q-Sharp, for example, and they can actually compile that down to run on one of the machines that they currently support, like the IonQ machine or the machine from Quantum QCI or some of the others. Qiskit also has a number of things. Some of the others, independent software vendors, can also do that, and they boast the fact that they provide hardware agnostic backends. And as a user, this is actually helpful because you can write one program and you can actually try it on different types of quantum computers and see which one gives you the best results. Various types of platforms. These would be the overall platforms that people have. IBM has Qiskit. Google has this thing called Cirq. Rigetti has Forest. D-Wave has Leap 2. And they can also do these backends. As I was talking about before about hardware agnostic, you can see that QCware for Rigetti. CQC is Cambridge Quantum Computing in the UK. They can support, they have a
Not hearing this.
This is one of the things that many of the companies are doing in order to be as flexible as possible. As was said previously, there is no universal language right now, but people are trying to be as compatible as possible by supporting multiple backends. And then you have frameworks to be able to pull all this together. Again, you have IBM, Qiskit, Google, Rigetti, Microsoft has theirs. There are new ones being developed. One in the UK is called DeltaFlow OS. It's like an operating system for quantum computing, which is intended to support all the quantum computers, different quantum computers in the UK. Amazon has theirs, Amazon Web Services. their what's called the Braket, B-R-A-K-E-T service. You also have quantum simulators. So many people, before they actually, they'll write a quantum program, but before they run it on an actual machine, they'll want to simulate it either on a classical computer or a dedicated box. Company in France, Atos, has a dedicated box that allows you to simulate up to 40 qubits. So that allows you to debug your system or your program before you actually put it on the quantum computer. And then a couple companies have what I call workflow managers to be able to organize your programs, allow teams to work together, to submit jobs to the various quantum computers, to get the results back, put the results in a database, and allow you to do that. And the company in Boston called Zapata has a program called Orchestra that allows you to do that. And Strangeworks in Austin, Texas can also provide that capability too. And then going towards the top of that stack that I showed you previously, one of the things that people are trying to do is make quantum computers easier to do. A lot of the end users are what you might call subject matter experts. They may be a chemist or a data scientist or an operations type executive who understands their problem, but they don't really want to program the computer down at those low-level gates that I was talking about before. So more work is being done to develop libraries that will allow them to just plug in their problem and specify it at a high level and then have the library then get it compiled and run on the quantum computer. So there's a lot of work being done on that. IBM has several that they've been adding. They just added one for AI. If you're into computational chemistry, there's one called Open Fermion that's supported by both Google and Rigetti. Microsoft also has a chemistry library. TensorFlow Quantum is a Google product that does quantum machine learning, and Chinese company Baidu also has one for quantum machine learning. And there are others too, but this is a big area of development right now. And then you have, we'll call it general purpose or many different software companies that will work with end users to either provide platforms or consult with them or focus on specific segments. And each of these companies has a different focus, or many of them have different focuses. Some of them are more general in nature. Like, as I said, CQC, Cambridge Quantum Computing, has their own programming language, Ticket, which can be used for any type of application. Zapata also can do that, and the others. But there are others that say, well, we don't want to be necessarily generalists. We want to create software that focuses on specific segments. And you can see, here's some of the most popular segments. Finance is a very important segment for quantum computing. People believe that the type of computational finance, which is used very heavily, the term is called quants, which is used on Wall Street and in the financial community, they could take advantage of quantum computing, and companies like JP Morgan and Goldman Sachs have significant groups that are researching this right now. Computational chemistry is important. People, again, believe that if you could do drug discovery by replacing the trial and error that people do right now to figure out the best drug and be able to simulate it, you'd be able to reduce the time and the expense of developing a new drug from, let's say, 10 years and $1 billion to maybe something, a tenth of that. So that could save a lot of money. And again, all the major drug companies have efforts there. There are various logistics efforts. A company called Qubit Engineering that's doing that, as well as, of course, various types of artificial intelligence. Some companies are focusing on that, like Qubit Logic. The one that I think is most interesting, or actually the next two are the most interesting. There's a company called Boxcat, which is trying to use quantum computing for image rendering. They're working, for example, in the video world. There's this technology called upscaling. You may have a TV show that was originally filmed, many years ago in the NTSC standard, which is like 480 lines, and now they want to upscale it to HD TV, and there are computer programs that will do that, but right now they run classically, but they take a long time. So Boxcat is working on technologies with some of the people in Hollywood to try to do that much more efficiently with quantum computing. And another one, excuse me, that's very interesting, company in Singapore called Horizon Quantum is working on a program where you would input a standard MATLAB program that you originally developed for a quantum computer, and then recompile and reconfigure it to run on a quantum computer. And again, this is part of the effort that I see more and more of being able to provide a capability so that people can use the quantum computers at a higher level, so that you don't need to have a PhD in physics to use it, but a lot of things can get automated so that if you're the subject matter expert, you can use it. IBM has a term called frictionless quantum computing. So you'll see more of that as time goes by, as the industry matures. And then you have all sorts of miscellaneous tools that are available. Again, simulators, design tools. IBM actually released about a month or two ago a tool that allows you to design your own qubits. It's called Qiskit Metal, that allows you to put together the various structures, the metal and the layers, to develop your own qubits. So there's a lot of different software. It's a big field. But to make all that available, you need to have, right now the predominant mode is a cloud infrastructure. You build a quantum computer and you put it on the cloud. So this is actually pretty challenging. Once you have a computer on the cloud, there's a lot of just operational things that you have to worry about, that you have to get right in order to make it usable so that your users don't complain. And it may sound like nuts and bolts things, but it's very important. Things like billing, user permissions, how do you queue jobs, how do you schedule jobs, how do you maintain the uptime of the machines? One of the big things that people are doing right now is how to integrate a hybrid computer with a classical computer. One of the big areas that people are doing a lot of research in right now is called hybrid quantum computing. There's various algorithms where the hybrid computer and the classical computer are working very, very closely, and they iterate back and forth to provide you with the solution to the problem. So this is a big area, and again, there's a lot of work involved in making this happen. In terms of who's offering stuff on the cloud right now, IBM, of course, put the first 5-qubit computer on the cloud. That was 5 years ago. And now they have over 20 computers available on the cloud, both what they call free service as well as premium service. And they're actually running roughly about 2 billion quantum circuits every day. So, they've done very good. They have very good uptime, but it's non-trivial, and it takes a lot of resource. And they've set up their own design center their own computing center in upstate New York to do that. D-Wave does the same thing. Their facility in Canada, Rigetti, has one in Berkeley. QTech, Quantum Inspire, you may not have heard of them, but that's a group in the Netherlands. They've put up a couple small ones. In China, CAS is the China Academy of Sciences, and Alibaba have what's called the Quantum Cloud. And now the two big cloud players within the past 18 months, Amazon Web Services, and Microsoft with their Azure service have interfaced various outside quantum computers to run with their systems. So the cloud is right now, it's the predominant way of accessing a quantum computer. Sometimes people talk about what's called on-premise. You actually buy a quantum computer and install it in your thing. That may happen, but that's probably several years out, maybe 5, 10 or more years out, just because just keeping a single quantum computer up and running with good uptime and the spare parts and the calibrations and all the maintenance is a significant effort. And to be able to do that, at a user site is quite difficult. Most companies would prefer to do it inside their own facilities, just a little bit more convenient for them. So finally, a lot of these vendors have efforts to educate the user community. Of course, the universities do a good job. Organizations like AFRL do a good job, but a lot of these companies will have things like webinars, constant webinars. They'll have hackathons. IBM right now is running what's called a quiz kit challenge, where they put 5 different problems together and they've challenged people to do that. IBM also has quantum summer school, Qiskit camps, videos. Many of them have, most of them have what are called partner programs, where they will partner, the hardware vendors will partner with the software vendors. So there's very significant efforts on what I would call the marketing side to be able to educate people and get people who are more familiar to how to use their stuff. So this is a key tactic that people are using, and we will continue to see that. This is actually nothing new in the classical computing world, but the quantum computing people are also doing similar things. And then, to talk about the supporting organizations, we do keep track of all the various supporting organizations that are out there. Right now, we have a list of universities. Right now, we see 158 universities worldwide that have various types of quantum computing programs and quantum computing education, as well as research. About almost half, 63, are in the US. There are a lot of government labs, of course, like AFRL, but many of the ones that are most predominant in the US are the Department of Energy labs like Fermilab, Lawrence Livermore Lab, Los Alamos Labs. Those labs, they all have quantum computing research going on, various types of programs, and some of those programs, they partner with people. There are many different trade organizations that have been formed. The one in the US that's perhaps the most well-known is called the Quantum Economic Development Consortium, or called QEDC. But there's similar ones in Canada. There was one that was formed recently in Europe. There's some lobbying organizations. Quantum Flagship again is in Europe. And if any of you are familiar with meetup groups, there are meetup groups that are also organized and have regular meetings, either on a week, some on a weekly basis, some are on a monthly basis, some are on a quarterly basis. So many different groups that are doing, and I would certainly encourage you to join some of them, and you'll be able to network with people and find out more about what's happening in the quantum world. And finally, let me just turn to investments in dollars. Quantum computing is now regarded as a very strategic technology by almost all countries worldwide. And many of them are investing large sums of money with grants and other things to be able to have a very strong quantum technology within their country. Here in the United States, there's the quantum initiative is about $1.3 billion, but that actually is being matched by many other countries. The UK has similar amounts. France has more than that. Even India's matched that. Germany has $2 to $3 billion. The one that stands out, you might say, is China. China has said that they're going to be investing $10 billion into quantum research, although we can't exactly pin down exactly where that's going. Again, these dollar investments will be split between quantum sensors, quantum communications, and quantum computing. And I would point out that China has been very aggressive about research into quantum communications over satellites, and satellites are expensive. So some of that money, of course, will go into that, as well as establishing a quantum communications network. They currently have a quantum communications network between Beijing and Shanghai. But this is something, and you will continue to see investments and announcements from the various governments. And several of them have put together quantum strategy documents that sort of give an overview of what they want to accomplish with their investments. And then finally, can't ignore the venture capital world. There have been a lot of venture capital announcements. There's actually one this week of $100 million in a company called Xanadu in Canada. This is actually a summary of the venture capital investments coming from a company called PitchBook that tracks these things. And you can see the comparisons between 2019 and 2020. The amount of venture investments has roughly tripled, although the number of deals is only increased slightly. Basically what this means is that the size of the investments are much getting larger. Some companies are going from Series A to Series B. As the technology matures, they're putting in more. There is a lot more excitement. Some people would argue that there's a lot of hype. Hopefully, these investments will pay off, although I can't say that all of them will pay off. Some of these companies won't make it, but that's, of course, the way the venture capital world works. So anyway, it's a large community out there. I would say it takes a village to build a quantum industry. You do need to have there are a lot of players, but those players need to be working together. The hardware companies, the software companies, the governments, the investors, all of them have to, and the component suppliers, all of them have to be worked together. So partnerships are very important. And we've seen some people mention those again in some of the earlier presentations today of various different organizations that are banding together to try to develop something. So that's a very quick overview. There's a lot more I could talk about, but I know we're sort of limited in time. But I would say thank you. We do have this publication, the Quantum Computing Report, that I established in 2015, where I track what's happening in the quantum world. We have thousands of people visiting it. I would encourage any of you, we have a free weekly newsletter that you can get. Just go to our homepage at quantumcomputingreport.com and you can see the sign up form. And once a week, we'll issue a newsletter that talks about all the new things that we've seen over the past week in the quantum world. And you can sort of view each one, and the ones you're interested in, you can click on the line or click on the link and see more about it. So with that, again, I want to thank everyone for listening, and I'm available for questions if we have time.
Thank you so much, Mr. Fink, for the excellent presentation. Any questions? So let me see. Any comments regarding quantum computing libraries or software for the telecommunications sector?
There's not necessarily libraries, but what people are starting to look at is various quantum computing simulators. How do you set up the networks? How do you figure out what the error rates are? How many nodes do you have? All those types of things. There's one company that I know in Boston, it's called Aliro, A-L-I-R-O, that is developing that type of software. So, you know, if you're interested in understanding a little bit more about them, go to their webpage, and you can see their software that will help you design quantum networks.
Thank you. Another question is comments regarding why Google does not figure more prominently on the middle or higher level of stack.
So, you know, every company has their own strategy. Google has what I would call a technology approach. You know, they've done really, really good work to develop their quantum computer and to have it available, you know, on the stack. But they also believe that it's still at an early stage, that it still requires a lot of testing right now. And rather than opening it out to the world and having hundreds of users use their thing like IBM is doing, which has its own things, right now they're in what I would call a beta mode. They are working and they're making their computer available on the cloud, but they're working with maybe a half dozen different you know, very sophisticated users to be able to shake out their bugs. That they see this as a long-term play. You know, you don't need to get, you know, dozens and dozens of customers immediately. They just want to do everything they can to advance their technology as fast as they can. And they think the fastest way of doing that is really through focusing with a smaller number of customers, as opposed to making the whole thing open, available to you know, hundreds of users.
Thank you very much. I think we answered. Okay, any comments regarding funding levels going to universities, national, international? Any comments on talent pipeline growth?
So that is a big concern everywhere. You know, people realize that this is a new field, that there aren't very many quantum engineers out there. You know, people who really understand this technology may be only in a few, in the hundreds. That is actually one of the areas of investment that I was talking about, particularly from the governments. A lot of those dollars, for example, from the US government, the National Quantum Initiative, is being put into various educational programs. And all the US government agencies like NSF and Department of Energy and NIST, all of them have substantial programs in order to encourage that. And that's actually one of the areas that the Quantum Economic Development Consortium that I mentioned earlier is working on. There is a group inside that organization called the Workforce Technical Advisory Group, Workforce TAC. I'm actually a member of one of those, and that's one of the things we're talking about right now is what can be done to encourage people to study quantum computing, as well as helping professors put together quantum computing courses to develop the workforce. There's a lot of work being done in that area, not only in the US, but also in other countries.
I think we answered all the questions. I don't see any other questions. Thank you so much, Mr. Doug Fink. I also have a question myself. You mentioned about the hybrid systems like hybrid classical and quantum computing. As you know, you visited our lab and you're familiar with what we're trying to do. We are trying to basically integrate physical, mechanical systems and the quantum technologies. And just wanted to get your opinion about it. Do you think there is a future? So for example, we use quantum communication. So we heard from Dr. Soderberg from the Air Force that they are actually interested in quantum communication between UAVs. But it's interesting that I forgot to ask her, because as I said last year, when we applied for an opportunity, they were more interested in algorithms and computing, I felt, rather than anything physical, an actual, basically placing such like a quantum technology on actual physical mechanical system. So just wondering if you have any comment on that.
Yeah, there certainly are a lot of areas where we'll call the quantum computing and we'll say mechanical engineering or other types of engineering will meet. You know, of course, you did talk about the quantum communication aspects of drone to drone or through robots, that type of thing. But as a user, there's a lot of areas where people can use quantum computing potentially. And I'll give you some examples. Airbus is very interested in doing airflow simulations, finite element analysis using quantum computers to come up with better wings, to be able to figure out how to design the shapes of their aircraft. Boeing is doing similar things. Another area in the transportation industry, one of the major areas, there's several research projects going on right now to come up with a better battery. Again, that uses quantum chemistry. How do you come up with a battery that has more lifetime, that's lighter weight, that can go through more charge cycles? And people are trying to use quantum computers to actually calculate the chemical reactions. Another interesting thing, Volkswagen has done a lot of research as well as others on traffic routing. You know, we're in Southern California, so you all know about the the traffic jams we get here occasionally. But Volkswagen, one of the things you can do is you can somehow come up with sensors that figure out where the traffic is, and then if someone wants to drive from one place to another, let's say from Pasadena to LA, you take the current state of the traffic, you feed it into a quantum computer, and it'll tell you the best route to take. And it's very complicated because there's, of course, many different routes, but there's already lots of cars that are already on the road. So there's a lot of work being done in terms of traffic analysis. I think Volkswagen is even talking about possibly having that capability as a production thing sometime in the future. And then anything where you want to optimize something, or where you have a lot of data, particularly if you're designing something mechanical and there's a lot of data and you want to optimize something either for lowest energy cost or that type of thing. As a user of a quantum computer, you want to run through various types of optimization type of algorithms so that you can come up with the most efficient design. So there's certainly a lot of potential things. I would say perhaps many of them actually would fall as with regard to the mechanical engineering world as a potential user and using quantum computing as a tool to help you design something and make it better.
Definitely. Actually, I've looked at those articles on quantum annealing for traffic, but I think there was no proof that quantum optimization may perform better than classical, or maybe there was or I missed it. So I wasn't. So I'm not in the quantum computing area, but I've just read about it. So I haven't seen any proof yet.
Well, I mean, that's a general issue right now is that I don't know of anyone who's actually using quantum computing in a production mode right now. Because if classical is better, if you're an IT manager or an operations guy or data science, if you can do it better with classical, you will. People are predicting probably within the next couple of years, you'll start seeing people are definitively showing that they can actually use a real world application in production and do it better on a quantum computer than a classical computer. But today, I don't think anyone is doing that. All the work that's being done is still experimental, developmental. Some of the buzzword that people use is called toy models, where they may create a model of something and simulate something that's smaller, like IBM, for example, has plenty of papers where they simulated a lithium hydride molecule very, very accurately on a quantum computer, but you could also do that on a classical computer, but that's a very simple molecule. But try simulating something like penicillin or a drug, you would use very similar algorithms just on a larger quantum computer, and that's what people are waiting for.
Thank you. And by quantum technologies becoming more and more accessible, I think we should think about maybe integrating them to like more system application, like autonomous systems maybe. And I think about it sometimes like how electric vehicles are becoming more and more popular. So maybe at some point nobody thought about electric vehicles, but these days, because they are there is a need for it. So maybe integrating quantum when it becomes more accessible, such as systems, I think will be really inevitable.
Yeah, I mean, vehicles are very interesting. I think the dilemma people have right now is that the quantum computers are not small enough to fit inside an automobile. So, you can't fit those big dilution refrigerators in your car. You
mostly
could have
quantum, photon quantum kind of.
Yeah. I mean, you could have possibly a radio link, from your car to somewhere in the cloud. I think the problem though is the latency, the delays are too long for it to be used in a, actual traffic situation where, you may see a kid running in front of your car and you want to slam on the brakes. You really need some very, very small, millisecond or microsecond reaction time. So it may come, but I definitely think quantum computers can be used in the design of the car, but to actually be used in the operation of a car, I think ultimately you're going to have to try to fit something that goes on the car or inside the car, and that's still probably 10 to 20 years off if it ever happens.
And there are proofs for scheduling on D-waves, such as vehicle routing, hospitals, staff, etc., done by different teams. Thank you for that. So there's a comment about there are proofs that D-wave can actually do a scheduling.
Yeah, there's a lot of papers on that if you search the web.
Thank you very much. Okay, thank you so much, Mr. Fink. I think there's no more questions here, and I really appreciate your great presentation and your time.
Okay, well, thanks, Farbad.
Thank you so much. The last thing I would like to share with you is we mentioned about hands-on. There is a video I would like to share with you from Professor Enrique Galvez, who has done hands-on remote quantum experiments. And I will share it with you now. And I think after that, if there's any question, we answer. And that's the last part of the workshop. I hope you can see the video. Just make sure. Share sound.
Hi. So this is a video to demonstrate how we use a remote desktop to run this lab on the quantum eraser. So first thing I'm going to do is I'm going to move the screen so that we get into the lab computer. And so I've already signed in via remote desktop. So we're going to, there we go. So that is the screen of the desktop in the lab. And you can see the view from a webcam, and then that's the lab. And okay, so the laser is not on, but we can turn the laser on. So I'm gonna go to the lower left screen and type 1, that's the instruction for turning the laser. And you can see there in the webcam, the laser is hitting a beam dump right there. And then this is a crystal. So at this point, down-converted photons are coming into here. One is going to a detector. There's actually to a collimator, preceded by a filter that sends light into detectors that are hidden somewhere back there. And then the other member of the pairs comes into an interferometer. And then here's a beam splitter, a mirror. There's a mirror back there, not seen very well. Another beam splitter, so it's a little rectangle, it's a Mach Zehnder interferometer. Here we have some wave plate that we don't touch. And then here we have a wave plate that we can rotate remotely. And then after interferometer, the light goes out here, also towards a detector, our Bob detector. And so we have a filter and then a collimator and then sends the light to a detector back there. This is Alice, so we have Bob. And then on the other output of the interferometer, we have Charlie and another detector. So, okay. So at this point, we could just turn on the detectors. So I go down here, and then I type 3, and then that turns the detectors on. And then the other thing that you see here is a little green light back there, showing that we have connected the power supply to the detectors. And then here, this display is showing us the voltage applied to the detectors. It should be about 5 volts. And you can see it's 5.111 volts. Okay, so everything is ready to take data. Now, in the experiment, we have a program that scans a voltage that gets applied to a piezoelectric, and then the piezoelectric is somewhere in here, and it's a spacer to a translation stage. So when we apply the voltage to the we apply the voltage to piezoelectric, then the piezoelectric effectively pushes the translation stage and changes the path length of the interferometer, and we're going to scan the phase of the interferometer so we can see interference, maxima, and minimum. Okay, so we have a program that scans that. And then we also have the ability to rotate a half wave plate there to control the degree of distinguishability of the two paths of the interferometer. So I can show you how we do that. So if I go down here, okay, so this little white dot there is specifying that the wave plate has axis vertical, and at a reference point is called 0 degrees, but we can change it to, let's say, 45 degrees. And we do that by entering here. So we go eraser underscore wave plate. Okay. All right. Now the COM number for that is 8. Okay. And so now we need to enter the angle in degrees. So I'm going to move this thing slightly so we can actually see. Okay, I'm going to move it a little more. Okay, so we can see the rotation stage rotate. So I'm going to enter 45. Now, as soon as I hit return, you're going to see this move. There you go. And so that way we can have a variable in the lab that we can change. And then there's a whole set of instructions for the students that are going to do the lab. So I'm going to return that back. So I'm going to just do it the easier way. COM number is 8. And then I'm going to put 0 just to return it back. There you go. Now, and as part of the lab, in one of the steps, we make the paths of the interferometer distinguishable so that there's no interference. And then after the interferometer, in the path of the photons that go towards Bob, we put a polarizer that erases the distinguishing information. And then that polarizer is right there. It's a cube beam splitting polarizer, okay? And it's out of the way, but then we can make it go in the way. So the way we do that is we type in here again, eraser underscore polarizer. Okay, so then it's going to ask me for the COM port, and then for this one is 12. And now I'm going to type I for N. So as soon as I hit return, you're going to see that little polarizer move. There you go. So now the polarizer is in. So I'm going to return it back to its position. So let's see. Do this. Come number 12. And now I'm going to put O for out of the way. Yep, this out of the way. So now we are ready to take some data. So we're going to use now this program in MATLAB, and we go here, and then we just run the program. Okay, run. And here I already pre-loaded the variables. The 1,11 is one of the ports for getting the data. 7 is the one that moves the piezoelectric, start voltage, end voltage. Okay, since this is a demo, I'm gonna just shorten this up to, okay, let's call it 3. Okay, and then the file, you're gonna say test. Just that. I'm gonna hit OK. Okay, there you go. So now you're seeing the counts of the experiment. So in the upper left screen are the photons that go to Alice. They go down-converted photons that go straight there. And then the middle up, this is Alice. Middle, top right is Charlie. And then down here, we get the coincidences. So here you see the data for Alice. Then down here, you see the data for Charlie. Those are the coincidences. And then way down here on the lower right are the triple coincidences. And you can see we get pretty much nothing because, of course, the photons don't split in going to A and B, A and C, sorry, B and C. They go either to B or to C. Let's put it this way, they get detected in B and C. And then that's how we record our data. And so I'm going to just do this. I close here, okay? And then this data has been recorded in a file called test eraser. So that one there is an Excel file that has our data. And we can just upload it and be done. So the next step here is we're done with our experiment and we want to now turn the detectors off. So I go to this screen, and then I type 4, and then you can see the reading up there of the voltage that is applied to the detectors, 0. Detectors are off. And now we want to block the laser. And to block the laser, we type 2 here, and you can see the laser is blocked. So we are done. And the screen. There we go. So this is how we can do this experiment on the quantum eraser remotely. Okay. And we are done.
Okay, thanks so much. This was from Professor Galvez, and there's a question I can just check if there's a question. Is it possible to use these remote access labs? Could you please share the contact of the speaker? Many thanks. So I think that's for Professor Galvez.
I'm still here.
Yes.
But I can say that, oh, is it possible to use my labs?
I think, is it possible to use these remote access labs?
Well, we would have to make an arrangement, and right now I actually have an arrangement for some other colleague to use the apparatus, but the apparatus that is set up right now is entanglement, polarization entanglement. I took apart the quantum eraser, but we could arrange for something if you are interested.
I just check if there's any other question. All right, thank you so much. I think they wanted your name, but they can see your name now.
And my contact, say, email is initial and last name, Galvez, one word, at Colgate, like the toothpaste, .edu.
Share email. So I type your email. So Galvez
at Colgate.edu.
Colgate. Galvez. Is it okay if I share in the chat?
Absolutely.
So we also followed from what learning from Professor Galvez, we did something similar in our lab. And again, this is for mechanical engineers, not for physicists or electrical engineers. So that's the optimum, I guess. Here we have students accessing the lab remotely. They're changing the half-wave plate, they're rotating it here so they can enter. This is just a zoom, so they can enter some degrees, angle of rotation for their half-wave plate. And here on this side, on the right-hand side, they can you can see AA prime, BB prime for the single counts, and then they can see coincidences like AB. In this case, we have a pair, BBO crystal, and we have 4 detectors. So we're doing something similar. And also here, this is the software that we are using from Professor Mark Beck. If you search Mark Beck, you can find the codes. All the code is available, so we just used the technology that Professor Mark Beck has developed. And he's using also a FPGA for coincidence counting. So again, there's a lot of information about that from Professor Mark Beck. And let's see if there's no any other question. So that's really at the end of the workshop. And we are only here if you have any question. Happy to answer any question. Let me see. Yes, please.
Hi, I would like to ask a question. And, you know, I'm a student at Oxford University in the UK, and I am a postgraduate student. And I studied quantum physics ages ago. You know, and now quantum computing is, you know, for real. But, you know, I've been looking at quantum computing for quite some time now. I mean, going through various seminars and stuff. And coming through this talk and looking at some of the really, amazing minds from the world, what really worries me is that a lot of this investment in quantum computing in particular is going to military tech, because a lot of this is about scheduling algorithm. The traveling salesman classic problem in computing is now solvable by quantum computing. At the same time, you also have, quantum communications. You got, you don't need to rely on satellites anymore. I mean, I'm looking at the future. A lot of this. So what are all the professors, the brilliant minds of the world, really looking at that this technology does not end up in the wrong hands, because it can be super critical that some of these technologies will impact humanity in a very, very huge way.
I leave that for the experts to answer. Anybody would like to take that question?
I mean, also nation states are, and investing in this big time. And there are research that are going from very prestigious labs into other areas who do not share the same value system as an open society. And there's a research collaboration around the world. So if somebody can take that question, please.
I have to ask the experts.
Hey, Farbad, this is Doug. Maybe I can answer this a little bit.
Thank you.
So there are people who are talking and looking about, quantum ethics. Can the technology be used in the right way? There's a lot of concern about getting, women and other minorities to be a larger representation in the industry than they previously have. There's also some discussion about, is this a technology that only the rich countries will have, and the lesser companies, we see that quite frankly with the vaccines we have today, where the rich companies like the US have the vaccines and the poor countries don't. There are people looking at that. Unfortunately, though, I think it's a very similar situation to what we see in almost any technology, where all these technologies are dual use, that can be used both for military as well as civilian types of applications. Even something like GPUs, which do not get as much press as quantum computing gets, but they, in my opinion, they may have as much of an impact, at least over the next 5 to 10 years. GPUs will have a big impact on the computing infrastructure. And the only thing to think about is, rather than trying to focus your ethics type of considerations only on quantum computing, I think it should really be more general. I will say, if anyone asks me about quantum ethics, that quantum ethics and classical computing ethics are really the same thing, because quantum computing is really only an extension of classical computing. And we should really think about some of the issues we have on classical computing, and quite frankly, get those solved first. Because at the end of the day, quantum computing is going to be built on a foundation of classical computing, and if classical computing is in a mess, then you can't build anything on top of that. So, I would say that we should all focus on trying to understand the ethical considerations and doing what we can to make sure classical computing is used and implemented properly. And that will go a long way towards making sure that quantum computing will also be used properly too.
Thank you, Josh. Okay. Let me just check the Q&A if there is anything left to answer. I think we gave the name of Professor Galvez already, if you are asking. It's possibly, yeah. So, I would like to thank very much the speakers and for your time, all the attendees. Thank you very much for attending. And we are going to organize a conference in February, a conference and workshop. I will be in touch to announce, and also we'll send out some survey to receive your feedback if you have any suggestion in future for future workshops. And Marco had a good point. I see in the chat that we never defined quantum engineering properly. Professor De Silva asked this question, and think some of the speakers tried to answer to some points, but you're right. I think, Marco, hopefully next time you can define for the attendees what is quantum engineering. Thank you so much.